All right, welcome everybody at Onward. My name is Thijs van der Storm. I was the PC chair for papers, and I've basically run Onward together with Robert Hirschfeld over there. He did the essays track. I'll be giving a very brief intro to what we have done to compile our fantastic program, if I say so myself. Just like Mira just did for Uppsala. Of course, the numbers are slightly different if you looked at these numbers she showed. So we had a quite standard review process. Both essays and papers were reviewed by at least 3 reviews, and then we're giving a conditional accept or reject notification. We had intensive discussions in the online PC meeting, really influencing the final decision to accept a paper or an essay. And in the end, this resulted in, for the papers track, in 9 papers to get accepted out of 19 submissions. And the essays track received 6 essays, and 4 of those were accepted. This was all due to the hard work of our respective program committees and a number of external reviewers. So I would like to thank all the reviewers for their hard work with a round of applause. So, and then, this has led to a program that roughly looks as follows. We are starting today with a keynote, the Onward keynote by Feline. And then there are sessions in this room, roughly thematically organized. So 2 sessions with papers, and then a last session with essays. And we have a half program tomorrow with 3 more papers and 2 more essays. So also please come here tomorrow to enjoy those talks. So before I introduce Feline, I would like to reinstate an old tradition of Onward that was for some reason skipped a couple of years, and that is the Onward Most Notable Paper Award. This is a sort of best paper award, but 10 years after. And since this is Onward, this is not about the best paper in any kind of hard sense, right? It's the most notable paper. So what is interesting, what is weird about it? And I'm very happy to report that this year's Most Notable Paper Award goes to Usable Live Programming by Sean McDermott. He could not be here, but if you know this paper, it's really very notable. And I want to read a little text about it that was compiled by the steering committee. This paper revitalized the study of live programming, introducing mechanisms that are now standard techniques in the field. The paper epitomizes the spirit of Onward, asking risky questions outside the current discourse. And in its form, the paper was a breath of fresh air, enlivened by the use of comic strips. The work marked the beginning of a rich theme of research that has been productively mined at the ongoing live workshop series at SPLASH', which was last Monday. So to give you an example of how this, why this is notable, or at least one aspect why it's notable, is that it contains these comic strips hand-drawn about, programming experience things and how live programming could help this. So big applause for Sean McDermott. All right, so then this leaves me with the happy task to introduce our speaker, keynote speaker today. Note this is a combined keynote by from SPLASH''E and Onward, because SPLASH''E is computer science education, and this is one of the topics that Feline is working on. So she is a full professor at the Free University of Amsterdam in a sort of dual chair with computer science and computer science education. She obtained her PhD from Delft University with Arie van Deursen, bringing software engineering techniques to spreadsheets, winning multiple best paper awards already during her PhD. She wrote a book on the programmer's brain. You see it over there. And she is also at the table of TC39 monitoring and guiding the evolution of JavaScript. In the meantime, she also teaches programming at the high school in Rotterdam. She is the designer and maintainer of the Heady programming language, which we will hear about more. In 2021, she won the Dutch National ICT Prize, which is awarded every year to recognize excellence in computer science. She is a well-known speaker in both academic and developer practitioner conferences, also recognizable from her signature handwritten slides, which I hope we will see a lot of them. If that's not enough, she also writes columns for developer magazines or on the radio, but basically she's an all-round good person fighting for more inclusivity in programming and research. So, without further ado, Feline, thank you.
Yes, this is working. Not so inclusive of small people. Maybe this is better. Let me move a bit so I can see the room. Good morning, everyone. So my name is Feline Hermans. I'm a full professor at VII in Amsterdam. My chair is in 2 departments, so partly it is in computer science, and partly it is in the educational department, because my research sort of combines those 2 things. And I want to talk today about creating a programming language for humans, for people. And I want to take you back into my personal story of designing the Heady programming language and all the things that I've encountered in that, story of a few years. So one of the things I really very much believe in is that everyone needs to have some programming skills. Not everyone needs to be a programmer, even though there's also a shortage of programmers, but everyone needs a little bit of programming skills. Just like we say, everyone in our society needs to have writing skills. Not because everyone needs to be Agatha Christie, but because everyone needs to be able to write a poem, or graffiti, or a love letter, or a pamphlet. Right? These skills are needed to participate in society in a valuable way, and in the same way, everyone needs a little bit of programming skills so that they can do data analysis about things that they care about or about in their jobs. Programming skills are important. And to me, they're so important that actually a long time ago, about 10 years ago, I started to teach in a high school. And in my country, high schools are a little bit different, so I'm teaching 12-year-olds because that's for us the beginning of high school. This was also, by the way, there's other stories to be told about this, that this was when I was sort of in the middle of my tenure track as an assistant professor, and I was not so happy with academia. I was sort of almost burned out. I thought I want to do something of value, and if I teach in a school, then this will also be of value. And I thought, okay, this is going to be great, right? I'm going to teach 12-year-olds programming, which is going to be easy because I know everything about programming. Like I have a PhD in programming, so this is going to be easy. They're 12-year-olds. Their questions will be easy. I will answer the questions. They will be impressed. They will learn. Yay! And then what happened, not explicitly, but subconsciously, I remembered how I learned programming when I was a kid. So this is me when I was a 10-year-old behind my dad's big computer. Well, actually, the big thing was a monitor, and somewhere there was also a computer. And I was learning programming when I was about 10. But in those days, there weren't programming clubs or programming lessons. I didn't know any adults close that knew programming. So I didn't have a programming lesson. What I did have was this. A book, Basic Computer Games. I see some people nodding in the audience. So this was a book that was allegedly going to help me make games, which I was excited about. There was no Steam, right? There was no internet, no Xbox. So if I wanted to make a game, this is how I would make a game. And this book was not a book that would teach me how programming works. It wasn't like, this is a variable and this is a loop. If you would open the book, it would be this. Printed out source code. And maybe young people in the audience would be like, wasn't there a download link? Wasn't there a CD-ROM? No, there were none of these things. You would just manually copy this into the computer, and if you can read really well, you can see that this is even in English, which is not my first language, so it has words like velocity. I have no clue what I'm doing, but there's no Steam and no Xbox, so what else am I going to do with my time? So you just copy this into the computer, and then sometimes you would make a mistake, and then the computer would be really helpful with tips, like syntax error, or expected comma or semicolon or end of statement. Remember, I am 10, I do not know English. I have no clue. But ultimately, of course, I did learn something. I figured out many things, and one of the things I figured out is I like this. Right? I like to make stuff, even though it's sort of painful. So as I said, I saw some people nodding in the audience who would say that this was also generally their experience in learning programming. Yes, so quite a few people. Yeah. So the sad news for you and me and all of us is that in this process we have incurred maybe some mental damage, right? Because we have come to believe that compilers are lovely teachers. We think that because this is the way we learn, that this is the way learning is good. Like this is a good way of learning. It's like we have no friends, right? So it's like we start to identify with this compiler, even though it keeps shouting. It's like, oh, you are my friend, compiler, even though you're mean, because I have no other way of learning. This was definitely the way I was thinking when I started teaching. And again, not explicitly, but implicitly I thought, well, I will just give the kids programming booklets. They will copy them into the computer if there is a mistake. They will not be sad and frustrated. They will just plow on like I did when I was their age, and everything will be fine. So just to give you a little bit more context about the programming club. Initially, we started not with textual languages, but with visual languages like this, like Scratch. I guess many people are aware of the visual language Scratch. This actually worked really well because Scratch doesn't have syntax errors. It hardly ever shouts at you. So this was quite a good way to get started. But as these 12-year-olds were aging a little bit, they started to say, this is for kids, right? This is a toy language. And specifically the part of the Netherlands where I teach is very much what you would call in America an inner city neighborhood, where kids are also very motivated to do programming because it will get them good jobs. And then if you see this doesn't look like something that would get you a good job, even though the skills might. It doesn't look like the type of thing they're looking for. So I said, don't worry kids, we're gonna do Python. Python is a very easy to learn, very user-friendly language. This is gonna be a breeze. Don't worry, this is Python. Look, this is Python, so you just put a text there, a print, and brackets, and quotes, and then if you execute that, you'll have text on a screen. I was very excited about text on the screen when I was 10. So I was like, that seems like a lot of work to have text on a screen, right? There's quite some things you have to know. And of course, sometimes kids make mistakes, like this. They accidentally put an uppercase P in the word print. Then, does Python understand this? Is Python like, no biggie, I know what you know? No, it says name error, name print is not defined. And you see some tension where kids don't understand what a computer can do, right? It can multiply 17 and 341 in 1 second. And if you ask it, who was the emperor of Rome in 300, then it will know, but then it cannot fix this. This doesn't fit what computers can do, right? Once you're in the world of programming, computers can do nothing for you, basically. But everywhere else, more and more, computers are sometimes quite helpful. Sometimes like, yeah, a computer is really precise. But then they're working with ChatGPT, and then the computer doesn't have to be very precise all of a sudden. Here's another one. A kid has just forgotten the final closing bracket, right? It's very clear what this program is meant to do for any human. And then the computer says, syntax error, unexpected EOF while parsing. So the kid is like, teacher, what is parsing? It's like, don't worry, kid, I have the Dragon book right here. Like, I don't want to talk about parsing. Like, I want to talk about parsing, but not to a 10-year-old in the first lesson, right? They don't want me talking about parsing. So you see these programming concepts, they jump into your room, into your classroom, and you cannot keep them out. Here's another one. So this kid is like, teacher, I've learned from my mistakes. Everything is perfect. This is the perfect program. It has quotes. It has brackets. Everything is there, including this thing. A space, like literally an invisible error. How can Python not compile this? How can it not just ignore this error if there's not any indentation? It would be trivial to just run this. But of course it doesn't. Indentation error, unexpected indent. teacher, what is indentation? Like, I don't want to talk about these things. And then you get into the situation, if you're a teacher, where either you have to explain what indentation is and why the computer doesn't do this, which is not going to be so interesting, or you have to say, which I also hate, just remove the space because I tell you to, because the computer tells you to. And then I want to go like to the bathroom and wash my mouth with soap, right? I don't want to say to kids, I cannot tell you the answer right now. I really believe that at every level, you should be able to clearly explain everything to everyone. And then this, I cannot explain this in words they know, and the only solution I have is like, just do it. So this is more or less the situation of my programming classes after the first few years. Not so many kids were so interested in continuing with my lessons. One of the kids actually came up to me after a few months, took the book and sort of dumped it on the table and said, I'm never coming back to your stupid programming class. But it was useful feedback, like it helped me shape my career. But to be honest, not everyone left. Actually, there were a few kids in every generation, like tiny Felines, that were actually interested in pursuing this. But after a while, I realized almost always they're boys. And why is this the case? Like, you could say, well, boys have more stamina and motivation. Like, that is maybe a reason. But I think one of the things that I also saw is that girls in my classroom would typically always come in with very low self-confidence because they have already grown up in society if they're 12 for, let's say, 10 years or 6 years, where people were telling them programming is hard. Programming is going to be hard. Programming is not for girls. Programming is not for you. I have literally had dads bring their daughters to programming club with the words, I don't think she'll like it, but. I don't actually think she'll be good at it, but. This is the society that girls grow up in. And imagine you are already a bit scared and everyone is telling you this is not for you. And the first thing you see is unexpected EOF while parsing. Then you're going to be like, well, you know, they were right. My dad was right. My brother was right. This is not for me. And I think if we talk about inclusivity in programming languages, we talk about doing fantastic things like having dinners for female grad students and professors, which is very good. We talk about role models. We talk about explicit discrimination more and more. We never talk about error messages, where I think this is also so important that if you know some parts of the population are going to have lower self-confidence, then it really, really matters what their first experience with programming is in a very different way that someone that comes in, a little boy maybe saying, oh, I'm going to be a programmer later and nothing will ever deter me, right? Then this matters a lot less. So at this point, after failing for a few years in my school, I thought, okay, this is actually an interesting research area, right? I used to research end-user programming in spreadsheets before. I thought, this is actually interesting. How do people learn? How do you get that syntax into your brain? How does this not become frustrating? And I started to read a lot about educational theories, not about computer science education, but specifically writing education. Just really, really diving into this world of how do people learn stuff. And this was in the middle of my tenure track. So this was not smart. If you look me up on Google Scholar, you see this dip like around 17, 18, where I just have not so many papers because I was learning together with people that actually know a lot from education. And this was not an easy stretch of my career because it's really very hard in the academic system that we've created together to say, I need to learn. I cannot produce anything now because I'm learning. And then sometimes I was like telling myself, don't worry, thinking is your job if you're a professor. You are learning, you're thinking, this is going the right way. But of course, there were also days where I was like, I'm an absolute failure. They should have never hired me. This career is not going to go anywhere because I'm not producing anything, which of course is very much a perspective on academia that producing is success or that knowledge is paper writing, but this is the dominant thinking. So this was not a great part of my life, actually, because I thought, I feel that I'm doing something valuable, but the system I am in is not valuing what I'm valuing. Anyway, after a few years of not doing much, I did learn much. So one of the things I figured out is that if children learn to read, we are very, very soft with them because learning to read is very hard. So if you have a 6-year-old and they've written this, you're not going to say, syntax error, floating I. Like, this is funny, but this is what we do literally, right? You're going to say, well, good job, buddy. Some of these things are letters. Here's a sticker, right? This is correct. This is not wrong. This is their level, and we're meeting them at their level. And then of the age, then the rules change. After a while, we say, oh, you know, if you have a bunch of letters, if you put them somewhat close together, they can form words and different sounds, like a little sentence, cat in tree. And they practice that in that world where this is correct. And then after a while, we say, well, actually, sentences are not just groups of words. They have to start with a capital letter, and they have to end in a period. That's actually the rule, and there's stuff like articles is there. And then they practice in that world. And actually, this difference going from here to here is not just a syntactic difference. It's also adding expressive power to the language. Because once you can start and end sentences, you can make sentences that span multiple lines. Whereas initially, a line and a sentence for a beginning writer is just the same thing. So we're changing the syntax and also adding concepts and expressive power into the language. I thought, this is an interesting idea, where the rules slowly change in terms of syntax and the things you can do and the things that we believe are correct at that level. Programming languages could be like this. And then I sort of, from all this entire story of learning about learning and figuring out stuff, I thought, well, you know who can make a programming language? Me, right? It was like, now, this was, first it was the bad part of the Hollywood movie, and now there was the part like, I trained for this. This is my destiny of building a programming language for this. So that's what I did. The heady programming language, here you see a little bit of the heady language. This is heady level 1. So we start simple. You just type print, and then whatever you want. So you just hi splash, and then it says hi splash. It just outputs that. No brackets, no quotes, nothing, doesn't matter. What I also said in the beginning, what I saw in the school is that kids didn't really understand why they were doing this. Kids would ask me if I would show them this program, but why do I do print? I can just type the text in Word. Why do I need to put the print there to get this? Right, this program doesn't really explain what programming is for, like why you would do this. And I thought this was quite a deep question from a 10 or 12-year-old, that, yeah, you know, why am I doing this? So from the beginning, we add this idea of user interaction. So we also have this in level 1, where you can say, ask, how are you? It will give you a pop-up box. And then with echo, it will repeat the answer back to you. So this is what it will execute to. It says, how are you? It also makes it really clear that that's where the text goes. If you do this in a command line interface, then sometimes kids don't even understand where they have to type. So how are you? And then you type great, and then it will say, okay, so you are great. So there is already state, there's this idea that the computer can store this value somewhere. You don't have to access it, you don't have to give it a name. But now kids think, okay, so now I'm creating a program that is for someone. Someone is a user of my program that is maybe not me. And you can even, with that green arrow, you can remove the code from view so that you can have someone play your story or your program without them seeing the code so they don't see where it's going. So this is level 1, and kids can explore just a little bit, this is what programming is. Also the mechanics of it. I type on the left. There's a green button that I have to press to get the execution on the right. Some kids in my school, 12-year-olds, have never used a computer before. They have a tablet or a phone, but why would you go in a computer if you're a kid? The computers are for dads with emails, right? Or for your mom with video calls. They're not a thing that kids necessarily interact with. So just the mechanics of using the keyboard, clicking with the mouse, is so much easier if there's not also syntax involved. So, warning, trigger warning. Some people are really upset with the next piece of code I'm going to show you. Just if you're easily worried about things, you might want to close your eyes. Because this is level 2, and this is actually valid heady code. So it assigns Feline, the value Feline, to the variable name, and then it prints hello name. I'm waiting for the tomatoes. Some people get really angry because they're like, oh, but hello is a plain text string, but name is a variable. And now how would kids know the difference? It just works. And you know why? Because I parse twice, and first I collect the values of the variables, and then I put them back in the parse tree. It's actually not very hard. But for kids, this is so very useful, because I can teach them about the idea of a variable. This is the idea that there's a value that you can give a name, and then later in the program, you can actually reuse this name, and the computer will remember. And you can use it not once, but twice. It doesn't wear off or something. They can really very much focus on learning what the variable is. Whereas if you want to do this in Python, you have to do this, right? You have to do so many things. You have to use quotes around the value. You have to have prints and brackets and distinguish between a value and a variable. This is just too much for some kids. And I saw some kids struggle with this for a few weeks, just only trying to get the syntax right and never getting to the point where they were actually reasoning about what a variable is, because they were just, there are errors and the computer keeps shouting at me in red letters, so I just add symbols until it stops shouting. So this, even though some people would be like, this syntax is so weird and it makes me feel a bit itchy, it is actually very, very useful for learning. And one point that's interesting is now that I often use this, I'm also trying to see, hey, even in Python, sometimes I would be happy, maybe not in the big code base, but in a little script, I would be happy if I don't have to tell Python what the string variable value is and what the variable name is. I have to, even in Python, I have to put an F there and quotes. It knows what a variable is because it's parsing the program. Why am I doing this work telling the computer what it already knows? So this is level 4. In level 4, we introduce quotation marks. Because at one point, you have to learn that, yes, there is a difference between a string value and a variable name. And because the language is so small, because we have so few concepts, it's also a lot easier to generate error messages that are more readable. For example, if you would forget a quote, then Heidi will tell you, be careful. If you ask or print something, the text should start and finish with a quotation mark. You forgot that for the text, how are you? So it's very actionable. It tells you what the mistake is and why. So this is level 4. Slowly, gradually, in 18 levels, we actually bring children to Python syntax. So our level 18 is actually functioning Python code. So from there, it is very much like trainer wheels on a bike. You put them on, and then you practice a little bit, and then at one point you're like, oh, we take off the trainer wheels. And now you have a real bike. That's how we also see Heady, that slowly we bring you to Python, and then at the end, well, it's Python. So now you can move and live in the Python world. And this also executes. So I built this as a small prototype in one Christmas break 4 years ago, just because I wanted to try this in my own classroom. I wanted to see if I could build it, and also I wanted to see, would kids like this? Would it be better? Would it work? So this is actually my school, the name of my school, and after half a year I said, okay, let's try this in the classroom. Let's see what happens. And one of the things that I saw, and also my colleagues very much saw, is that the classroom atmosphere was just changing. It's not necessarily something you could maybe measure with a questionnaire, but we could just feel stuff being different. In the Python world, all the time, kids would be with their hands raised and frustrated. And as a teacher, I would be running around. Even as an experienced teacher, you still have to read the error message and figure out what's wrong. And in the meantime, I have 32 12-year-olds, right? So they're all shouting, and if they're not helped, then they will annoy each other. So just it takes so much energy running around in the classroom, figuring out what's wrong and what's going on. And then when we switched to Heady, just the calm appeared in the classroom because they would get fewer error messages. But also, for the teacher, if I see an error message that is like a bracket is missing in line 4, I can just say, oh, you just have to check line 4, right? So I don't have to process a lot myself. I can just see, this is what's wrong. And also, this is something I used to do all the time. I would tell kids if there would be an error message, hey, you just read the error message. But if the error message is unexpected EOF, what is the kid going to do? A Dutch speaker that doesn't even know what those words mean. Well, probably English-speaking kids don't know what EOF means. But now I could really say, hey, just read the error message again and walk away in confidence that I have given them a helpful tip. So it really, really, really changed our perspective of if you have better error messages, it's not even necessarily for the students because a lot of the time they don't read it, but for the teachers, it gets so much better if they're good because it saves you as a teacher time. And the cool thing about using your tool like all the time, every week, is also you get to see the tiniest things. Like here's one of my favorite examples where kids would say, well, teacher, we don't love these error messages. I was like, have you seen Python? I think we're actually pretty good, my child, but tell me what the issue is. So you cannot put a comma there because it confuses our parser. And I think actually our error message is quite good. It says, the code you entered is not valid. There's a mistake on line 1, position 12. This is exactly what the error is, and then it tells me what there's wrong because you cannot put a comma there. So I said, okay, read this error message aloud to me, because I think this kid has not read the error message, and this is why they're confused. So I asked the kid, read this error message to me. So the kid says, yes, line 1, position 12, you typed, but that is not allowed. So the kid's like, why can't I type? I'm typing all the time. Why can I not type? So I was like, because this is a 12-year-old. What have we told 12-year-olds for 6 years? If you see a comma, you take a little pause. So it reads, you typed. But that is not allowed. It is the most sensible thing. And of course, we have statistics, right? So I could have seen in the database that this wasn't an excellent error message. But without a kid telling me why this is confusing to them, I would have never guessed. Like this is even before level 4. So it's before I have told them that quotes mean a literal character. There's no way that they can know this. There's also another one which was exactly the same, but they didn't have the comma, but it had just a space there. So you cannot type. So the kids were like, I don't get it. It was valuable feedback. So this is what we do now, actually. Instead of having the character there, we actually vocalize all the symbols. So it says, you typed a comma. But that is not allowed, which is just, it is a tiny, tiny change. But clearly, it's a lot better. What I also saw, not necessarily in my classroom, but in other teachers' classrooms, is that kids would very much struggle with what am I supposed to do? So one of the teachers in my school, in another class, the kids would say, okay, teacher, I think I know what a print is. But now, what do I do, right? What is my assignment? And I think a lot of you that raised their hand when I asked you what was your experience in learning to program were people that had many ideas of what they wanted to build, and they just wanted to put them in the computer. But there's also many people that if they start programming, they don't know what programming is. They don't really know what programming is for. They don't know what they're supposed to like. And this is also a perspective of gender. So by and large, we know from research that men and boys very often like to try out stuff. Like if you buy a new microwave, then the guy is more likely to throw away the manual and just to start pressing buttons. And women are more likely to actually want to read the manual, want to figure out what is going on, and only then start. This is like an established way that male and female people have preference in learning. So just saying something like, you don't have to write documentation because no one reads that, without you knowing, that's actually quite a gendered statement because women are way more likely to actually be interested in reading. if you know that this is a thing that exists, then if you look with that view at programming environments that we have, like a Python environment, it doesn't tell me what to do. It doesn't have a button to help me get started anywhere. Even a programming language like Scratch, sort of by design, doesn't have built-in tutorials or manuals that I can read. So if you know this, and then you look at these tools, you're like, well, they're manly, they're boyish, even if they don't have, I don't know, robots and stuff that boys might like more. Just the way the UX is designed only caters for people that want to jump right in. That's what it's for. And from this, I think I learned that tools for learning are really, really, really different from tools for teaching, right? What I was experiencing in the programming club, specifically when we're still doing Scratch, is that kids do everything. Like one kid might do this, right? Look, teacher, I made a very reasonable program. But another kid might be like, well, teacher, I have this, and I need more help. And this is just more likely to be a female student that doesn't know what's next. In the same classroom, you might also have other kids, more likely to be boys, that are like this. Look, teacher, I made this fantastic program. It's very messy. It's also very clear and very well organized. And now what I want is I want the palm tree to be blue instead of green. Now I, a person that holds a PhD in software engineering, has to be like, that's a great question. I don't know how to do that, right? I have to sit down with you and figure out what it is that you have created. And then this creates a situation in the classroom I only realized after a few years where I was always engaging with these kids because they had interesting questions. Those were the kids that had a lot of interest in program, and all my attention would go there upon reflection. And the kids that were just not so far, I didn't know how to help them. They would come to me and say, what should I build? And then I would also be like, whatever you want, which is just not helpful. So in Hedy, we have this interface in which in the UI, it tells you what you're going to do, which is very weird in programming languages for children. It's like, this is what you're going to do. Are you ready? Let's go. Go to the first step. And then you go to the first step. What we also do is we give teachers the power to customize this experience. Because if you have 30 children in your classroom, you might want to limit the distance between them. You might want to say, I want everyone in level 1 and 2. I don't want people to advance because their excitement is going to take away my energy of teaching the kids that don't have so much knowledge yet. And kids without prior knowledge is maybe more likely to be girls, but also kids that come from lower socioeconomic families where they don't have computers are just less likely to have background experience. So if you want to, as a teacher in the teacher's back end, you can customize everything for your classroom. So you can say, well, you don't see all of this, which can be a little bit overwhelming. You just see this. And then you can also upload your own lesson plans as a teacher. And then you can block off levels. So you can say, well, go to level 2, then this doesn't work because your teacher hasn't made this level available. And this allows you as a teacher to keep kids closer together, and this helps you maintain your energy. And as a teacher, this is really a feature that many, many teachers very much like about our UI, being able to customize what goes on in your classroom. Okay. So after this free-form exploration, we actually did a user study in which we asked kids, okay, how can we make Hedy better? And it's so cool to engage with your users, even if they're kids, and hear from them what they want. So then they said, the kids in my classroom, we want to program in Dutch. Which I thought was remarkable because the whole UI had always been in Dutch. All the explanations, the error messages had always been in Dutch. The only thing that wasn't Dutch was the keywords. And the kids would be like, yeah, why not also the keywords in Dutch? You made this, miss. Why don't you also make that? Like, well, because it's a lot of work. But I was actually really surprised because Dutch teenagers, I was like, well, you know, we are very good at English. Why? But then I realized that, you know, why are programming languages in English? It's a really great question. I think one reason is because the people that know programming can already do English, or they have learned English through learning programming. So they're like, well, I don't see the problem. And also, some people object to languages in different natural languages, because then if people program in different languages, then maybe they're not able to understand each other's programs. But I built it anyway, partly also because it was a pandemic. I had a lot of free time. So we built this multilingual keywords in Dutch. And then the interesting thing is, many other people started to contribute translations. After Dutch, which is very similar to English, we also got German and French and Spanish. And the farther away we were getting from English, the more I was seeing the value. We started to get weird, from my perspective, languages like Hindi and Bengali and Chinese. I was like, wow, this is so cool. I'm so proud of myself. I'm like, yay, I built a localized programming language. But then in your life, often, if you're lucky, you have people that hold you to a higher standard. One of those people is here in the room with me. He's Aladdin Sweetan, my co-author on much of this. And he's like, yeah. So, well done, Hermans. Very impressive. Those left to right languages. Well done, you. What about Arabic? I was like, my good sir, must you really? He must really, yes. I was still the pandemic, so it really gave me this new perspective. Like, imagine you're teaching programming in Palestine, right? And you're teaching kids programming in Python, and you're like, print, and it starts with a P. And kids that grow up with Arabic, they're like, what is a P? And how does a P differ from a B and a D? It's like the same letters. I'm learning Arabic. Now I have a deep, deep understanding of how hard it is, because all the letters are really quite similar if you don't know them. So I was like, yes, we must also have keywords in other languages. And one other argument that I didn't think about, so my first argument was, no, this is about fairness, right? This is about inclusivity. But it's also about very practical things, about ergonomics even. Because if you're programming in Arabic with English keywords, or you're doing Arabic strings, which just makes a lot of sense, you have to first set your keyboard to English with a key press or a mouse click. Now you're typing in English letters the keywords, and now you have to again press a button, and then only can you type an Arabic string. So every line that you're switching between keywords and strings, or variable names, if your programming language also supports that, is an extra button press or an extra mouse click. And this is, even for professional programmers, it's like taking away your flow, right? It's very annoying, but you can imagine for beginners specifically, continuously they're frustrated about what keyboard am I in, which I think is really an amazing argument that me, a Westerner, would have never been able to come up with. So we actually had English keywords. So this is the turtle that we also have in Hedi, where you can simply just create forward and turn in Arabic keywords. So again, I'm like, well done, me. We have Arabic keywords. This is going great. That guy was like, yes. And what about Arabic numerals? It's like, Arabic numerals? These are Arabic numerals. Right? These are not Arabic numerals. I learned this at the age of 37. Maybe people younger in the audience, they learn it now. These are actually the numerals that Arabic uses. I didn't know. Fun fact about the Netherlands, all 12-year-olds in my country have to learn Roman numerals. This is the law of my country. So we have to use Roman numerals to interact with clocks and buildings, but we don't learn Arabic numerals that are actually used in Arabic. So I thought, this is easy. This cannot be a problem. We simply put those numerals into Python, and this will work, right? It does not work. So if you add two numbers in Python, this works, of course. If you add two Arabic numerals in Python, it doesn't work. And it tells you this, invalid character. So who is Python to tell someone that their actual numerals that they grew up with are invalid characters? Right? This is quite sort of interesting. And there's actually a lot of philosophy about this. So there's a researcher, a philosopher called Miranda Fricker that has this whole book about epistemic injustice, which is the injustice about knowledge participation. So we often say as programmers that programming languages are a representation of knowledge. So who was involved in creating this knowledge? Who was involved in making decisions about these programming languages? And really, if you think about it, what problems are we solving programming? Like at this point, there are 6 robots running on Mars with software, which is like, it's amazing, right? It is fantastic that we can use software to put robots on Mars and control them, and they send images to us. It's like, wow, I wouldn't know how to build this. But in the same universe where software is everywhere, Python doesn't let me add 2 numbers, right? This is a very, very weird and large contradiction. So yeah, I know it was still the pandemic, so we also support Arabic numerals. So this is printing 2 numbers. You can add the numbers. It outputs it. This is a for loop with a loop counter that goes from 1 to 5. This also outputs it. If you want to, you can get your output also in Arabic numerals, which was, of course, it was a little bit of work to build this, but it was doable. So we're getting slowly towards the end of this talk. The thing I built, the heady programming language, went from something 4 years ago that I built for my own classroom, in my own school, sort of for my own enjoyment, into this massive project that is now translated in 47 different languages. We have hundreds of thousands of users. The last 2 months, we had over 1 million users on our website. Yesterday, I was sitting at breakfast with random people that I had never seen before, and they're like, yeah, we use Heady in our Coder Dojo. It's like, yeah, this is pretty cool that so many people are leaning into this idea that localized and easy-to-learn programming languages are of value. So I want to look at the future of programming. But before that, I want to look a little bit at the past, my past also in academia, in this community, because I started in PL. Maybe some of you were there and remember this, that my PhD thesis all the way in the beginning was supposed to be about building programming languages. And then when I was very young and I had cool hair, I was at eCoop in 2010. Anyone in the room that was also at eCoop 2010? This was in Slovenia. 2 people, cool. So I was also there. This was my absolute first conference, and I was working on spreadsheets. My advisor sent me there alone, so I had no clue what I was doing, and I was presenting a paper about how spreadsheets are programming tools. And no one really was explicitly mean to me. There wasn't like real harassment, but still I ended up thinking, I don't think I belong here. I don't think this is a community where I want to be. And then, when I was 25, I didn't have the words or the vocabulary to really understand why I didn't feel at home there. And some of the people in the audience have seen this talk before with a different ending. I changed the ending based on my experience over the last few days. So the last few days, I've been telling everyone, what do you work on? I work on making programming languages that are not English. And what I was ready for was the question, why? Because that question I get a lot, like, why would you do that, right? And I can explain why, because all of the things I just said, the inclusivity, the philosophy of it, the ergonomics, but that wasn't the question that people were asking me. Anyone want to do a guess what the #1 question I got over this week repeatedly about my work? How? Cool. Half points. No, surprisingly not, no. So the question I got all the time was, why is that hard? Why is that hard? This is trivial. This is just a replacement. You can do it in English, so why couldn't you do it in Chinese? Case closed, right? And I realized what was happening to me was I got really defensive. I was like, yeah, but it is really hard. It is really hard because have you heard about quotes being different in other languages? Keywords, numeral, word order, diacritics, all these things that are really hard. If you're interested in knowing all these things that are really hard, today at 12 in SPLASH', me and Alanin are actually presenting a paper that could also have been titled 12 Reasons You Didn't Know English is Actually Different from Other Natural Languages. Many things that English does, other languages do not. And all our parser frameworks are made on English. But so as I realized, I was getting so defensive, like, but it is hard. Trust me, I am smart. I am part of this community because I do hard things. Then I was thinking, what am I doing? Like, I seriously, I felt my soul leaving my body. I was like, because I'm leaning in to this perspective that in the PL community, to be important means to do hard things. This is what we believe. And if I explain why the things I'm doing are very hard, then I'm buying into this dominant perspective of we want to do things that are hard because, well, it's enjoyable, and also maybe it makes us feel really good about ourselves because we feel so smart. So just to show you how easy it is, yesterday night, I have looked at the entire top 10 of all the TIOBE index programming languages, and the simple thing I tried to do was put Arabic numerals in. Do you want to see my results? This is C. It doesn't work. This is C++. It doesn't work. You get not one, but 2 error messages. That's nice. This is Java. This is C#. This is JavaScript. This is Visual Basic. The build failed. Fix the build errors and run again. Thank you. Visual Basic. This is PHP. Undefined constant. It's nice. It takes the constant and then it assumes it is that string of that constant, but it doesn't do anything else. It will just throw an error. This is SQL. I had my hopes up for SQL because it's such a user-friendly language. No, it doesn't. And then this is assembly. It was actually quite hard to try to get the language in even. It doesn't work. So this is a paradox, right? And I think we can sort of look at this problem and conclude that it's not done not because it was too hard, but it's not done because it was too easy. Which is a problem, right? No one does this because it's easy. It is just different numerals. It is a simple change to your parser. But if it's so simple, why don't we fix this? And the most fun thing I saw this week was this badge. This is an actual Splash badge. I was walking around. If you see this guy, say hi to him. But this is easy, right? This is just encoding. This is all very easy. But it is so easy that no one is working on these problems. Why? This is just very weird. So I would hope that in the future, if I say I work on localizing programming languages, people cease to say, why is this hard? Also to other people, specifically young faculty that are working on things that they care about, do not ask them why it's hard. Ask them why are you excited about this? Why is this a worthwhile cause? Who cares if it's hard, right? Because you are all like this, well, it works on my machine, it works on my character set. But it's just very important. So I think the question that the PL community should start caring about more is not why are you doing this, but do you care enough about this specific topic to do the work? Also, if it is easy, and I trust you, again, we have a nice session at 12 in SPLASH'23. It is not so very easy, but it also happens to be very important. So what I hope, if we're creating programming languages of the future, is that these programming languages will serve different perspectives. If you look at C++, whose perspective is in this language, right? Certainly not the non-Western perspective, because it doesn't allow for any of that. But maybe also not the female perspective. If you teach C++ to 18-year-olds in university, the female part of your students will have, for 10 years, been exposed to, hey, this is really hard. Are you sure you can do this? If that is your perspective, if this is your lived experience, like it is my lived experience, probably you wouldn't design a language like this, because it sort of drives the point home that programming is really hard and somewhat unreasonable, right? Because why do you have to do all these things to just print something? It also has a perspective of a certain ableism, because if you think about people that consume programming languages with a screen reader because they're blind, think of how this sounds like with a screen reader. It would be like std : out, smaller than, quote, hello world, quote, semicolon. So it's also not made from the perspective of someone that's blind or visually impaired using a screen reader. And of course, it's not a problem that this language doesn't do this. But if you look at the TIOBE index, top 20, all the top 20 is made by male programmers. And only 2 are partly made by non-white programmers. So this perspective, there's nothing wrong with this perspective, but it's just the only perspective on building programming languages that we have is this male perspective of, oh, let's just try stuff out. Is this Western perspective of, wow, it works on my character set, which is just a perspective. But we really, really need different perspectives. And if you take a few seconds to look around in the room, look around you, right? This perspective is not here. And again, there are many reasons for this. Reasons are discriminations and role model, but this insistence that here we are doing things that are hard, and this is why we're doing that, just that is the dynamic of this community, is already excluding some people, probably more likely female participants who are more likely to care about like making the world a better place. Minority people that grow up in lower socioeconomic families are also more likely to care about making the world a better place and less likely of, how do I have fun on this planet? So thank you for listening to me. If you're interested in contributing to HEDI, if your native language is not in the 47 languages that we support, you can totally go to hedi.org/join and join as an open source contributor, or if you want to as a translator. We're always very happy to get new languages in.
So thank you, Feline. There's some time for questions. So.
Hi. So I wonder about like, do students ever get like inundated by levels, rules, and changing rules? And so there are like, I saw 17 levels, right? And
yes.
These levels has like different rules. Different constructs. Some constructs are kind of like throw away, like the echo and ask and stuff like that. And the semantics also change, like the string literal and not there. And so I mean, do they ever get inundated with
yes, so they get confused in between levels. One answer to that is, but this also happens in math, for example, where in math, first subtraction cannot go below 0. So initially, kids would learn 5 minus 3 is 2, but 3 minus 5 is 0. Because you cannot go below 0, and then you can go below 0. Or first you only do integer division, and then you add floating points. This is one answer. Another answer is that we're trying to do hard stuff with parsing, where we're trying to guess which level a line is, and then if you accidentally mix levels, then we know, oh, this is this level and this is the other level, so we can still run the program, but give you a warning that you're accidentally using a construct from a previous level. That doesn't always work, but in many cases that does work, and that is helpful as well, but also changing semantics is also part of learning in other fields. So this is frustrating, but it's not a frustration that we necessarily introduce. We basically take a model that's very common in other areas. It's a great question.
So earlier on in the talk, you started talking about bringing programming to the masses and how not everybody needs to be a programmer, they just need to have some programming ability. I'm confused with the goal of HEDI here because you were basically making people programmers. Is HEDI also the solution for bringing programming to the masses? And if not, do you have opinions on that? Yeah,
it's a great question. I don't think necessarily HEDI is made for building programmers. I mean, the level of Python you're at the end is still like a small subset. It doesn't do OOP programming, for example. So I think more the goal of HEDI is to get your toe in the water. Oh, this is what programming is. Oh, I understand a few concepts now. So that if later you become, I don't know, a dentist or a hairdresser, then you recognize a little bit of programming. Or if you want to synthesize a script with an LLM, at least you have an understanding of the concepts. So that's also one answer. Another answer that the way HEDI is now is it's really geared towards kids. We very often get the question from adults, oh, could I also learn programming with HEDI? And then they can, I'm like, yeah, it's free, go ahead. But then the exercises and the way everything is laid out is very much aimed at kids because, well, you can't do everything, and kids are actually more enjoyable to work with than adults. So that's what we focus on now. But the techniques, of course, could easily also be used for end-user programming.
Thank you. Loved your talk. So I gave a talk at the doctoral symposium yesterday, and I'm already regretting some of my advice because I told the students, when you give a talk on your work, you should explain why it is hard.
Yeah. Well, this is the community that we created.
This
so
is
I
the
don't think
community
it's
we
bad
created.
advice.
So, and there were other parts of my talk in which I talked about some of these contradictions between our ideals of our research and the reality of what actually happens when CVs get looked at and so on. But I just wanted to get maybe a little more of your ideas on what should we be doing as a community. I mean, I think we talk about novelty, but we mean hard. Is it enough to just say no, novel doesn't mean hard, or how do we change this in program committees and?
Yeah, that's really, changing a community is really hard. So one thing really where you can go from two ways. Like one way we can do is just in conversations we have in the hallway, which is very powerful. And another way is to have something in the steering committee or in the program committees where there's a track maybe about real world impact, where we take a paper, our own paper or someone else's paper, and we just implement it in a context with users, right? Or show some real world impact. Usually if we want to do so, if we want to value something more, we do a track. Like it used to be really, really hard to get academic brownie points for programming. And then we say, oh, we have an artifact track where you can build something and you have a small paper and still it counts as a publication. So an impact track is maybe something you could do, but I think the biggest change is coming from the outside where I don't know, I haven't asked many people, but my suspicion is many people like me that so much care about real-world impact go to a PL community, to a conference, or interact with people, and they think, okay, I don't see how my world values are aligned with this community. And as I say, I have these words now. I didn't have these words then. Like literally yesterday, I was in a talk, and people were joking about a Popple paper not having enough Greek symbols to be accepted. This is literally something that was said in this venue the other day. So I don't know.
Hi, thank you for the great talk. So one other place I've heard some similar ideas is very old. It's from it's the logo work of Seymour Papert, right? And so I thought it was similar because they targeted the same sort of audience of middle school children. They had many of the same concerns about inclusivity and girls and lower income students. And they had this, the turtle model, and you even had some slides with the turtles on it. So my question is, I guess, what's still relevant, and what ideas have you carried forward in HEDI, and what's different, and what does our modern computing environment give us a better ability to do?
Yeah, okay, so this will be the final question because my answer will be really long. My answer could be a 45-minute lecture, but I'll try to be brief. So this is a fantastic question because so much of the work in programming education has been informed by the logo created by Seymour Papert, and also Scratch, for example, comes from the same line of reasoning. What people tend to not know about the group of people that have created those tools, because we don't read the history of that, is that Seymour Papert was very, very much anti-school. If you read the first few pages of the Mindstorms book, he says in those first pages that he played with toy cars as a toddler, this is his words, and he learned more from playing with toy cars than in the whole of elementary school. This is literally in his book. And this perspective is in those programming languages. So Logo, but also Scratch, really, it's a tool for learning. It's a tool to teach yourself programming with, because you shouldn't need a teacher. I once wrote a paper about detecting code smells in Scratch programs, and the Scratch team, some people got really mad at me because there cannot be a code smell in a Scratch program because whatever the child builds is correct, basically, was the idea, right? So those tools we don't really realize, but they are tools for building, and they don't take into account the reality of school, right? I would also like to live in a world where I have 3 students and sit next to them and say, what do you want to build? And then I will help you build what you care about, and I will help you care what you build, right? I would like to live in this world, but I live in the world in which governments around the world give teachers 30 kids, right? So then I cannot have tools that do not help me to manage classrooms. And specifically, Scratch is a tool that's not built for the classroom, because ultimately the people that build those tools think classrooms shouldn't exist in the most extreme form of their thinking. So they're just not made for reality. And I know some people say, well, you know, Feline, then you're just leaning into how bad education is. You should also try to overthrow the system, which I sometimes do, right? I mean, you heard me speak. But in this case, I think if we want to help teachers manage classrooms, we need to have tools that are very, very simple and that allow for a lot of customization. And this is also what we just hear from people that use our tools. So in terms of programming language design, those ideas are still very valid. But in terms of editor design and the whole ideas of why are you doing this, they're just really in a different philosophical stream than I am. Oh, we do have time for one more question.
Well, yeah, I'm from Japan, and we have a pretty long history to develop our localized Japanese version of programming languages.
Yes.
So I totally understand. You know, I totally agree that localization of programming languages is so hard because we have more than 20, 30 years history. But unfortunately, those efforts are not successful from my viewpoint. And there are many reasons, because it's a difficult work. But one of the reasons I see is, some kind of people do not like localized Japanese programming languages, because at school, now the government, also adults, and some kind of people from industry say, hey, every Japanese kid should speak very fluent English, right? And now the programming language is also kind of mandatory language. Every kid has to learn. And that language has to be, well, in English.
Yeah.
So have you encountered such kind of pressure from the local government or adults or some people from this industry?
Yes, this is also a great question. I'm really having fun. So one of the things we do in Hedy is we are a multilingual programming language. So if you program in Japan and your program parses, I can look at your program in Dutch, because you just take the parse tree and you print it with different keywords, which is very easy. And we're even working on a project now where we're also trying to, using machine translation, translate strings and variable names so you can really consume the program in your own language. So I do think that's one of the key things that make Hedy maybe more likely to be more successful, because you can look at programs from different natural languages, and ultimately it's Python just with a Japanese layer or a Dutch layer. But also one other answer that I'm seeing in interacting with teachers is, yes, this pressure that you talk about from governments, that exists, but also many people really, really want to speak in their own natural language. So for example, a few months ago, I was in Botswana, which is a bilingual country with English. So they're definitely not using Hedy because it's easier, because all their kids can do English. But the teachers are very excited to do Hedy in Botswana, because now they can show their students, look, our language that you don't want to speak because English is more cool, is also the language of technology. Look, you can use your own, our language in the computer. You do not have to follow the imperialistic narrative that English is the world country, because this system allows you to bring programming close to you. So interestingly enough, many of our bigger user bases are in bilingual countries, the Netherlands, but also Indonesia, Puerto Rico, where many people speak English, but they don't want to. And then our system allows them not to learn programming necessarily in an easier way, but in a way that they want, that is close to their heart, which is also worth something.
Okay, let's go to the final question.
Okay.
So thanks for a great talk. I guess I was one of the people who asked why is that hard?
Sorry,
question.
man.
I guess, sorry for that, but it
You
was
were,
quite eye-opening. So I have a similar question, which is that yes, it seems right that it makes sense to have these multi-language versions of educational languages. But you also talked about the TOB indices and like the languages that are used in actual software engineering. And so, do you think that those languages also should be multilingual, or would that not? It seems to me that would create problems with with people being able to understand each other when they collaborate across the globe, right? When we have code samples on Stack Overflow that you might want to copy and all those things.
Yes. Again, this is a great question. So of course, localization is also many things. Like just supporting different character sets for numbers is something that I think also professional languages could do. It's just easier also because of the ergonomics. Also quotes, right? So French doesn't use these quotes, but uses these quotes. Your parser is not going to use these GMS probably anywhere, right? So it's sort of, there's a few things you can do that don't cost you anything. That's one answer. One answer is there already are a lot of code bases that are localized, maybe not open source projects where people collaborate internationally, but in companies, if you're developing software in Dutch for the Dutch government or for Dutch companies, then the keywords might be in English, but the strings and the variable names and the comments are already going to be in Dutch. So in that, or Chinese or Japanese or Spanish. So in that context, maybe purely for the ergonomical reasons of not having to switch keyboards, maybe then if you're already in this world, then it might be nice if your keyboards are also there. Of course, there is some tension that, yes, but then I will not be able to understand their code snippets on Stack Overflow, but then this question is almost always asked by, this is literally also in my paper, is almost asked from a Western perspective, because people that do not speak English or do not speak English well, they already live in this world where they do not understand code snippets on Stack Overflow, right? So this is just going to enable to them in an easier, better way to have maybe their own Stack Overflow. And also, one more thing, it is not hard to build a tool, if the code doesn't have a syntax error, to take it and to parse it and to output it in another programming language. And you all doing smart things about programming languages probably can also figure out a way to do something with something that has a syntax error, so it translates what it can just in time or something like that. So there's so many solutions, but the perspective of this question in the most mean way is like, yes, you are asking, but how can I still enjoy the free labor of other people solving my problems, right? And maybe other communities are also just served by communicating in their own language, and this is we already live partly in a world where not everyone can easily read Stack Overflow questions.
Okay. Thank you, Feline, for a great keynote. Let's have some coffee after a big round of applause for Feline. And I
Okay, good morning everyone. Welcome back to the first onward session with accepted papers. My name is Thomas van Binsberg and I'll be the session chair. Our first speaker is a remote presentation. So please, so we'll have a presentation by Christophe Chide on time awareness in object or exploration tools toward in situ omniscient debugging. So when you're ready, Christophe, the floor is yours.
Yes, I am. You can hear me?
Yeah.
Can you hear me?
Yes, we can hear
All
you.
right. Yes. Very nice. Then welcome to my presentation. I'm Christoph. I'm a master student at the Software Architecture Group at the Hasso-Plattner Institute in Germany. And yes, welcome to the paper. Let me start with a short motivation. We are talking about exploratory programming systems. So we are talking about programmers who are exploring running systems by their space and by their time. So they are asking different questions such as, what does the state of an object look like? What is an object currently doing? What has it been doing in the past? Or also, why does the variable or the value of this variable have changed in the past? And to answer this question, programmers can use different tools and workflows. For spatial questions that relate to the state of the system, they can use typically inspection tools. For temporal questions that are about the behavior of a program, they can use debugging tools or also omniscient debugging tools that allow programmers even to go back in time to explore the historic program behavior. But it already brings a challenge to programmers as they have to choose between different tools and they also have to switch between these tools. And especially for omniscient debuggers, this is a decision that also has to be made in advance, because if I do not use an omniscient debugger in the first place, then I am not able to go back in history at a later point in time. So these are some challenges to programmers, and this also leads us to our research question, which is how can we design tools for program exploration that supports both space-related and time-related questions, and that thus combine historical information about the program execution in a single workflow. And to answer this question, we make three contributions. We propose a universal tracing mode that makes it possible for exploratory programming systems always to have the historical information about the program execution available. We propose a space-time exploration model that brings together object inspection and debugging in a single workflow. And finally, we apply these concepts in our prototype, which we call the space-time inspector. But before we can get started, I also need to introduce some background to you. The first part is exploratory programming, which I already mentioned before. In general, this means we are working on a software system where the system or the requirements are not yet fully understood. And so programmers are working with a lot of trial and error to figure things out. And this also involves asking a lot of questions. And these questions can relate to the space of a system. So programmers ask questions about the state of the system, about the meaning and structure of data. But these questions can also refer to the time, to the behavior of the system. If programmers want to learn how something is working under the hood, or also how data is constructed and manipulated. And then we have object-oriented programming systems, which is just one application of exploratory programming, but in this case, everything is an object. Objects communicate with each other to form large systems. And importantly, programmers can access and manipulate all objects in the system while the program is running to explore and change the program. And one example, one application of object-oriented programming system is Quick Smalltalk, which is also the system that we used for our prototype. And another important theory for us is the experience of immediacy, which has been proposed by David Ungar and others already 20 years ago, but this is still relevant for us. So we have three dimensions of immediacy here that should be reduced, or that should be maximized as much as possible to increase the experience of immediacy. And the first dimension here is the temporal immediacy, which basically means if we want to enable users to recognize causality, then we need to avoid or reduce delays between an interaction and the response by the system. And then we have the spatial immediacy, which tells us basically that we should minimize the physical distance between things or events that belong together. And also the semantic immediacy is important, which generally means that we should minimize the conceptual distance. So for instance, we should try to avoid different representations of the same artifacts if possible. And then we have different program exploration tools, which usually, at least to some degree, adhere to these principles of immediacy. And we have object inspection tools here, which can be used to explore the state of a system. So we have different representations here, but usually we have something like a property sheet or also like a domain-specific visualization. And on the other hand, for exploring the behavior or the time of a program, we have debugging tools where we can execute a program step by step, and also omniscient debugging tools which record a trace of the program, which can then be explored independently of the original execution order, and where we also can use different means for navigation, such as events or changes to states and so on. But then we can also localize these different tools in this coordinate system of time and space. And there we can see that inspection tools typically only display an object at a single point in time, so they are constrained to the spatial dimension. And on the other hand, debugging tools are time-centric, but they only give us access to a small portion of the state, which is relevant to the current method execution. So they are both limited in different ways. And in the background, you can see our vision of a space time exploration tool that brings together both dimensions within a single workflow. But to achieve this, we have to face the different challenges of immediacy. So the temporal immediacy is a problem mainly because omniscient debugging is technically slower than normal debugging. And if I decide later to use an omniscient debugger, I need to start all over the program execution. Spatial immediacy and semantic immediacy are also problems because the different tools which we have with inspectors and debuggers are not related to each other. They are different tools which we need to switch between, which use different representations. And to solve these problems, our universal tracing mode aims to avoid the first two kinds of immediacies, because we can make the historical information available at all at once, so that there is no technical overhead anymore. And with the space-time exploration model, we also avoid the overhead of switching between different tools. So let me start with the first contribution, the universal tracing mode. And here the main problem, as I already mentioned, is that there is a technical overhead of program tracers, which is required for omniscient debugging. And so here we collect 3 strategies that are helpful to avoiding or minimizing this overhead. The first one of them is the efficient trace model. So many program tracers actually create a full snapshot of the memory, of the entire memory at each point in time, which is obviously inefficient. And so what we instead suggest is that we detect fine-grained side effects in the bytecode and store the previous values as only when they are changed. And this massively can reduce the memory consumption and also provides an efficient access to read and append operations in the data structure, which is basically a map of sparse collections. The second strategy are explicit exploratory interfaces. Here the observation is that in many cases we have large systems where a lot of things are going on at the same time, but only a small part of this behavior is actually relevant. So for instance, we might have a graphical user interface with different objects representing the widgets on the screen, and each of these objects has one responsibility for rendering itself onto the screen and another one for reacting to user events. And in many situations, the programmer might just be interested in debugging and exploring these user interactions, but not in the rendering logic. And so here our idea is that we define system boundaries, and whenever these boundaries are crossed, then we enable or disable the program tracers. Some example of such explicit exploratory interfaces include the accesses to a model in an MVC application, or also custom expression evaluations in an exploratory programming system. And so we can avoid tracing a large irrelevant portion of the program trace. And the last strategy, that also is an option, is program reproduction. And so actually some omniscient debuggers do not create a trace of the program at all, but just rerun the program on demand many times to collect further information as requested. But this requires, first of all, reproducible entry points, and second, also deterministic behavior of the program. The first requirement can, with some effort, be achieved. So we could, for instance, log all invocations of our explicit exploratory interfaces, and in many situations there are also existing log sources available, such as the command history in a REPL. On the other hand, deterministic behavior is harder to achieve. In many situations, there could just be any kind of global state in the system that might affect the behavior of the program. And so we recommend to developers to use heuristics to detect such deviations and ask programmers how to proceed. But in general, we also recommend that we should try to prioritize upfront tracing over program reproduction to avoid this challenge at all. All right, so that was the first contribution, which allows us to always have the historical information available, but then we still need to find a way to allow programmers to explore these collected data at once in a single workflow and tool. And this is our second contribution, the space-time exploration model. And here we start with something like a spatial view on an object, which could be something like a property sheet or a domain-specific visualization. And we combine that with another view, a temporal view that displays us a call tree, a time slider, or anything else. And both views refer to an object and to a program trace. And we can combine them in a single tool, which we here call the space-time inspector, and which allows programmers to interact the system and explore it by both dimensions on par. And importantly, both dimensions are linked to each other, both views are linked to each other. So the programmer could select a portion of the state in the spatial view, and this selection will then influence the granularity of the temporal view. What does this mean? For instance, I could select a single variable in the spatial view, and in turn, this will make it unnecessary to display the entire call tree, and we only need to display a small subset, a small slice of the call tree, which only contains Z methods that are relevant for changing the value of the variable. This also works in the other direction. If the programmer selects a slice, so a subset of the time, then this selection will influence the informational density of the spatial view, so that we do not display the entire history of the state, but only the history within the selected time slice. And because this is pretty abstract, I'd like to give you a concrete example of this, and I would like to show you our prototype, the space-time inspector in Squeak Smalltalk. And the example which I would like to present to you is a runaway. A runaway is a class in Squeak which represents a sparse collection object. And now we would like to find out together how this class is implemented, how it is internally structured, and how we can use it and how it implements an addition operation. For that, I have a very small program here in Squeak which basically creates a new runaway and adds different values with different numbers of operands. And I can run this program here, which will automatically trace everything in this so-called omniscient workspace. And finally, I can explore my constructed runaway object in an omniscient inspector. And this gives me this view where we see on the left the temporal view and on the right the spatial view. And at the moment you can note that the temporal and the spatial granularity are very low. And I can change that by expanding the spatial view on the right, which then gives me an overview of the different properties of the different items in the runaway. So we can see the first item was present in this interval, the second one in this interval. And here we can also see that the interval or the length of this value has changed over time due to different addition operations. And so we also have these inline summaries here. And I can also select a single point in time to explore the state of the object at the single point in time. I can also use this time slider on the bottom to travel through the history of this object. But this is just a snapshot of the object for the now, or whether this only gives me a high-level overview of the object. If I'm actually interested in its internal structure, then I can choose a different representation. And instead of exploring the items, I can also explore the instance variables of this object. So in this spatial view, I now can see that the object consists of 5 different instances variables, 3 of them are none or null, and the 2 others are different arrays which have been reassigned multiple times, as we can see. And again, I can display the values at a single point in time. I can also expand this here to view, to watch the different items in the array and scan into the object tree. And yes, and another feature which also exists is this blame feature here, so I can select a single variable and then all method invocations on the left will be highlighted that have changed this value. And thus this also allows me to further slice or drill down the different context trees for different states. So in general, what you can see from this example is that space-time exploration allows us to explore an object by its evolution and by its internal structure at once to figure out how certain operations are implemented. And how this works under the hood is that the space-time inspector is a small framework which combines different spatial and temporal views and synchronizes the selections with regard to time and space with each other. And this is actually a pretty generic model, so we can also use this for any kind of other models, of other views. And for this, I have a second demonstration for you, where we are going to explore how regular expression measure in Squid works. And for this, we can combine different domain-specific views that already exist. And this is how this looks like. So the first view is pretty simple. This is a string here on the top, which displays the input string we are trying to match with our regular expression matcher. The second one is a graphical representation of the NFA, the automaton which is used inside the matcher. So we see the different states and the connections here. And the third one is a temporal view. This is this blue line in the foreground, which displays the call stack, which is mapped onto this automaton. And so by combining these views, we can display the current state of the matcher here. We can see that the matcher is currently scanning into this automaton, that it is currently trying to match the first character of the string. And if we go forward in time, then we can see that the match is rejected because no underscore was found as accepted. But in the end, we also can find a complete match with a much deeper call stack. And the takeaway of this demo is just that we can build new space-time exploration tools by combining different space-time agnostic views. All right, so much for the demonstrations. Now I'd like to briefly talk about the evaluation of our ideas, and we start with the tracing. In general, we have to note that for our selected programs, we can indeed see a huge runtime overhead, which is because our program tracer is not yet fully optimized, but still the absolute numbers are pretty small in most situations thanks to the explicit exploratory interfaces. And also the historic memory, which is incremental, allows us to maintain a very low memory footprint, and in general we can say that the universal tracing is responsive at least up to medium-sized workloads. With regard to the space-time exploration, we have measured the delays for different navigation operations in our prototype, and we can here see that the temporal navigation was responsive for all considered use cases, while for spatial navigation and also the inline summaries that we have seen in the first demo, the temporal granularity matters indeed, and for larger workloads there might still be noticeable delays, but it is important to note here that there are no domain-specific optimizations that have a lot of potential. For instance, our regular expression visualization, which has a pretty large temporal granularity, only took us about 2 seconds to compute because we made manual optimizations such as manually accessing the call tree and others. And then we can conclude with a discussion, first of all, about the programming experience. So we could streamline the model for program exploration by allowing programmers to answer questions that relate to both the space and the time of the system within a consolidated tool. This reduces the gulf of execution for programmers and also allows them to reflect on their own understanding of the system using a more consolidated vocabulary. So also we reduce interruptions and thus increase the experience of immediacy. And something which I also found very interesting is that we can provide programmers with richer contextual information using space-time exploration. So if I only am interested in learning about the structure of this object, just for free by accident, I also can learn something about the evolution of the state, and in many situations it can improve my understanding of the semantics of the single variables. Also, there is an impact on tool buildings with space-time exploration. So through this framework, we can reuse existing space-time agnostic tools and combine them into new space-time exploration tools. And still there are some challenges. There is still an intrinsic complexity of tool building, or in many systems, not many views are available initially. And programmers are still required to make their views space-time aware if they want to use advanced space-time exploration features such as inline summaries, or also if they want to scale them up for larger workloads with manual optimizations. And also, finally, I'd like to share some interesting questions for future work with you. The first of them is, how can we integrate data flow into the space-time exploration model? At the moment, our notion of time in the model just refers to the evolution of state, but in many situations, the origin of state of values is also interesting if they want to if they want to find the cause of a bug or something like that. And another question of ours is, how can we use space-time exploration as an overarching concept for all kinds of exploratory programming activities? So at the moment, we have combined object inspection and debugging, but we could build further features such as allowing programmers to dynamically compose different views in the inspector, or to filter the system by the space and by the time. And eventually we could even express an entire symbolic debugger or omniscient debugger just as a composition or as a combination of different space-time views, and such makes the make the information about the history, about the time of programs even more omnipresent in the entire debugging or exploratory programming session. So finally, let me conclude. In our paper, we have taken a look at how we can make object exploration tools aware of the temporal dimension of programs, and for this we have made 3 contributions. The first one is the practical universal tracing mode, which uses an efficient trace model, explicit exploratory interfaces, and program reproduction to always have the historical information available in the system. We allow programmers to explore the system by both dimensions on par at once using the space-time exploration model, and we tested out these ideas using our prototype in Squeak. We found out that the performance was usually already promising, but yet for larger workloads, the spatial navigation still requires domain-specific optimizations. And with regard to the programming experience, we found out that we could streamline the program exploration model and provide programmers with richer contextual information, and also were able to build a framework that allows tool developers to combine existing domain-specific views to build new space-time exploration tools. And with that, I thank you a lot for your attention, and looking forward to any questions which you also can ask in the Discord channel later. Thank you.
Thank you very much, Christoph. Are there questions?
Hi there. Thanks for the talk and the interesting work. So I'm interested in the principles behind the visualization, but and the interaction. But what I'm specifically interested in here is how much that kind of a system's availability might affect the design of the actual program. Whether being familiar with how you can explore it after the fact might change the way you program it in the first place. So my specific question is that when you showed the examples there, when you made those examples, did you take code that was already written beforehand, or were you thinking about how it was going to look in your system when you wrote the code for the examples?
Yeah, thank you for the question. I would say it is a combination of both. So the first example, which was a very simple example, was just assembled for this demonstration. But the second example was a real system in Squeak, which we did, which was already existing beforehand. So it was not tailored to this kind of exploration. But in general, we also found out that it is easier for space-time exploration if we have if we use a lot of intrinsic states. So data flow is something which is not covered by our model. So if we have a program or an architecture where you are using a lot of functional behavior, a lot of extrinsic states that they are passing from one object to another, then this is something that we cannot cover with space-time exploration. And so systems that use side effects are definitely better suited for this kind of exploration.
Right. So potentially a different style of programming might make this kind of tool more effective.
Yes, I think you could say so, but side effect programming is already is a popular style, I think.
Okay. Thanks.
It's time for another question.
Hi, thank you for your talk, very interesting. Maybe this style of programming could be live programming. I was wondering though about how you propose tracing the historical information. That, do you represent the changes explicitly, or do you suggest capturing snapshots of the states? This might impact the amount of memory you use as well in your experiment. So I'm curious what the data structure should be and yeah, how they support the different features of omniscient debugging.
Yes, I will back to the relevant slide. Where is the slide? Ah, yes. Generally, we store or each variable in the system. We have a separate collection of values that have been changed. So, for instance, if this variable color here, or if the variable submove here is changed, then we store the previous value, and we use it again when a new value. Every time a new value is assigned to the variable, we preserve the previous value in this data structure. And this means that we do not store any redundant values. But this is not a differential memory if that was a question. So every assignment will store the entire value. If we have a string and add another character, we will still write out the entire string at each chance. So I'm not sure whether this answers the question.
Yes, thank you.
Final question. Then let's thank Christoph again.
Thank you.
We will proceed with a joint presentation by André Telesh and André Santos on code merging using transformations and member identity.
All right. Good morning, everyone. Thanks for coming to the session. So we are both here. I'm going to start off, and then I will pass the word to the other André. So what are we addressing here? We're addressing three-way merge scenarios. You all know what is this, but just a recap. So we have a stream of software. At some point, someone branches. During the paper, I'll use the term left and right branch. So let's say we did a branch to the left, and then the original base keep on evolving, and we got the right branch. And we are addressing this process of getting these two left and right merged. This image, many of you should know, is from GitHub. So when we have a pull request and we have the chance of merging it automatically, but we can get this message, okay? And why is this happening? It's because the two branches that are involved, the git merge algorithm is saying, okay, there is a conflict, so I'm not going to merge it. And because we'll get this result. Git merge uses text-based merging, and so the regions clash, and that's why we have this problem. And in the literature, this has been referred to as a false positive. Why false positive? Because this situation, in fact, you could merge the two methods in the same class, and that will not be actually a conflict. On the other hand, we might have a message saying, okay, yes, you can merge, but this doesn't come free from problems. Let me get another foobar example. So let's say this is our base class, and then the left branch renames the method foo. Okay, the right one doesn't touch the foo, but adds another method in a different text region. Okay, Git says there is no conflict, but in fact there is. If we try to merge, that foo reference is outdated, okay? And this has been referred in literature as false negative because the tool is not pointing out the conflict, but in fact, when we merge, we get not working software with compilation errors. Okay, now an example we will use during the talk. It's also very simple, but it will be hard to explain these things properly without a very small piece of code. So let's look at this very creative point class. Okay, let's say the base at this first version, 2 fields, 2 getters, no modifiers, nothing. And then the left version has added final modifiers, has added a constructor, renamed the getters to the get pattern, and added this isOrigin. Okay, very trivial. You can. And the right version has added different modifiers. There were no changes here, and also added some isOrigin, but using the original getters. Okay. When we go and merge this with git merge, so diff3, we get these conflicts. I'm afraid. Yeah, you can see like very light gray, which I see okay here, but in those regions you get some conflicts. I will point here just to be easier. So here we have a region conflict, and also down here. This is the same case as I showed before, so I'm not going to lose time on that. But then if we start applying research approaches, like for example JFST merge, which was published here at UPSLA, they do structured merging, so they are aware of the language structure, okay? But still, at some points, they cannot do a good merge. So for example, here in the modifiers, we have a clash. It's identified as conflict. And also here in the method body, we have a clash. In another research approach, also published here at UPSLA more recently, IntelliJ, it does a similar job. So we also have conflict in this area, okay? But then isOrigin is not reported as a conflict, but the resulting code gives us compilation errors. So this X and Y are broken references, okay? So somehow the rename was not well handled. And we also run this case in JetBrains MPS. So MPS makes a model-based merging, okay, using the proprietary tool merge, using their models. And so here we got no conflict, but here still, like it failed to see that these two isOrigin are in fact expressing the same thing, okay? We could also force, I had the idea, okay, let's force the case that MPS also doesn't work in the modifiers, but we didn't do it because it would seem that example would be contrived. But if we do like a static final, we also get a conflict up there, although those modifiers can be combined. Okay, so having this scenario, what we would like to achieve, so what we call the ideal merge, is this scenario. So all these changes are compatible and they can be merged into compilable code. This is what we would like to achieve, and that's what we can achieve with our approach, okay? And so we're going to use this example throughout the whole presentation. But nothing comes for free, right? And one of the keywords of the title is identity. So what we mean by that, when we have classes and their members, we rely on a form of making some precise matching using universally unique identifiers. And our implementations, we did them as source code comments. So it's like the class and their members, they come with these comments attached, and that's the information we use to match, okay? For those you know, for example, NPS or back in the days, the intentional domain workbench, their models, they also have this sort of universal IDs to do the matchings. But here we are in a format that is still regular valid Java code that can be used with the regular tool chains. Regarding the other keyword of the title, transformations. So when we have changes, for example, this branch, this version has evolved from the left side, we encode the transformations as the changes as a set of transformations. So for example, this one up here, okay, we encode this as a modifier remove in that element with a certain UID. The second one, we encode it as a rename method in the method with cert UID. And this one is a new method in the class with a certain UID. So notice that this one is not yet with ID. Why? Because These IDs, they're not managed manually. They are injected once the class gets version. So once I first do a push to the class, that injects those IDs. And they are supposed to kept coherent as software evolves. This case we don't have because this will be a new method that is about to be pushed to the repository. All right, so now it's time to pass the word to Andrea, which will explain details of this merging.
Thank you. The first step of our approach is to parse the 3 versions of the code to an abstract syntax tree. After that, we extract the transformations between the left and the base version. As we can see, and Andrea mentioned, we have transformations for the change of modifiers, the addition of the constructor, renames of the methods, and the addition of the method isOrigin. The next step is to repeat the previous step, but now between the right and the base version. And once again, we have less transformations, but we have the change of modifiers and the addition of a new method isOrigin. After obtaining the 2 sets of transformations, we check for shared transformations, that are transformations that are redundant. Okay, having these 2 sets of transformations, we can see there is the potential that the first 2 transformations might be redundant. However, as we have seen in recalling the 2 branches, one has final modifier and the other the private one, so they are different, they cannot be considered redundant. In addition, we have the add method isOrigin that also has a potential to be redundant. As we can see, their body is textually different, although we need to do a special parenthesis to explain how we handle body comparison here. Our body comparison starts by getting the UIDs of the elements that the references point to. After obtaining these UIDs, we replace the identifiers of the body with them. And as we can see, now they are textually equal, and we consider it to be redundant, and we factor out these 2 transformations into one new set of transformations, which we call the shared set. After obtaining the shared transformations, we start the conflict detection phase. So having these 3 sets, for each of these 3 sets, and for each transformation in particular, we check each transformation against the other transformations of the other sets. As Andrea presented, we have no conflicts in our approach. That's why we have an ideal merge. But for example, if left would add a public modifier and right a private one, that is a conflict that needs manual intervention to be solved. Okay. Next, we have the merge process. Since there is no conflicts, we start by grouping the 3 sets of transformations, and we rearrange it in a special way. We separate the addition transformations, that are transformations that add new nodes to the AST, and the remaining transformations that are transformations that make modification to the existing nodes. We start by applying these addition transformations to the base version, but as we can see, we have broken references here with the addition of the new method isOrigin, because getX and getY are not defined in the merge version. So we do one intermediate step here that we have called the translation of identifiers by reference. That's the merge version we have. And we start by recalling what was the branch that originated the transformation isOrigin, the addition of method isOrigin. And that was the left version. And once again, we get the OID of the elements that the references point to in the left version. We find the matching elements, the elements that have the same OID in the left version to the merge version, and we apply their identifiers to the method is origin. After that, we continue the application of transformations, and we apply the remaining transformations in any order, but explaining special that the renames transformation, in particularly, rename also all the calls to the method or the element that is being renamed. Finally, after having the merge version in AST, we have to generate the source code based on this AST. Here's again the ideal merge with the OIDs attached. Okay. We developed Jade, that is a prototype merging tool that has support to Java, but only covering the more common elements in Java, methods, types, fields, etc. And it has 35 different transformation types, and is a prototype with around 6K lines of Kotlin code. Java parser is an essential library that we have used because it is used to parse the source code and also to make the necessary transformations. Okay, we also conducted an experiment to prove the feasibility of our approach. To our knowledge, there is no real merge scenarios that have any form of identity attached to them, so we had to fabricate ourselves. So we start by obtaining the merge scenarios from the material of the JFCT merge paper. We then find the matching files between the three versions by path. We parse them using Java parser, and we compute the matching element using GUM3, that is a code differencing tool. And to the matching element outputted by GUM3, we attach the same OID to simulate that element was the same throughout the development cycle. We have obtained merge scenarios from two projects, Bucket, that is a Minecraft server API, and JSoup, there is an HTML parser. From the total of 63 merge scenarios, we had to exclude 6 of them because in these 6 merge scenarios, at least one of the left or the right set of transformations were empty, because the only modifications we had in that branch was in the elements that Jade was not covering. So we had to exclude them, because there is no point in doing the conflict detection phase when one side has no transformations. We split the results in 2 groups, the conflict-free group, which we aimed to search for false negatives, and in a total of 43 merge scenarios, 34 have built successfully, but 9 of them had compilation errors. That happened because since we have in one of the versions, the left or the right, we had transformations that in members that are covered by Jade, but we also had some other changes that are not covered by Jade. And when applying only the transformations that Jade covers, created some broken references and the code would not compile. However, since we did not find in these 9 merge scenarios, they all had compilation errors, not due a malfunction of Jade's implementation or a shortcoming in our approach. So we did not find any false negative. The other group, that is the conflict group, we have found 40 conflicts in 14 merge scenarios. We have checked each of these 40 conflict groups one by one to check if they were in fact real conflicts, and they were. They all needed to have some manual intervention to choose which version to apply. So we also did not find any false positive. Finally, we also explored the execution time. We have obtained around 3 seconds for bucket and 14 seconds for JSoup, in which 50% and 70% of this time, respectively, was in the parsing and indexing phase. We also tried to find a relation between the size of the project and the overall execution time. Bucket shows that they are linearly relationable, although in Jade there is something that is not so clear. Now I'll give the word again to Andre, so he concludes the presentation.
All right, so I will just wrap up by discussing some drawbacks and the respective benefits or workarounds. So you probably, when you saw the first slides about UIDs, you're like, okay, so now the source is going to have all that stuff. Of course, this is not ideal. First, because we have to see it, so it's verbose. And then also, because, most important, because they are fragile, right? If someone moves the method and doesn't come with a comment attached, there it goes, the UID. So that's a problem. Okay, but possible solutions would be, okay, on a heavier scale, if we use projectional editors that completely hide that information, that problem gets potentially mitigated. But in a lighter version, we could just at least have some IDE plugins that fold those parts and you don't have to see them. And it's already an improvement, but the fragility will be still there somehow. Okay, so I think this could only be fully addressed with some sort of specialized editor, projectional or not, that really hides that information. Another criticisms could be like, okay, your implementation and approach is language specific to Java. So now if I need something to other language, I need to do all this stuff again, okay? But being language specific also allows for more precision and some semantic awareness of the language, okay? Which modifiers can be combined? Does my language allow method overload or not? And all those fine-grained details, you can have more conflict detection or not in a more precise way. So the disadvantage is somehow an advantage. And then you also, if you compare those merge times with other papers, you can say, okay, it's a bit slow, 10 seconds, okay? But then do we merge that often? And like having merged code with compile errors also takes a lot of time to fix. So if we take a bit longer, but we avoid less errors, that's a good thing, and we can live with the 10 seconds. So I don't think that's really an issue, if we improve the other side, right? And yeah, so we managed to do proof of concept with more precise merges, so less false positives and less false negatives. And that's future work. We envision, so we don't approach this in the paper, just in a speculative form. So improving Jade coverage, that would be an obvious improvement, and this is doable. Like, for example, we don't cover things like the static initialization blocks or methods inside the enum constants. You know, these little corners of Java, for pragmatic reasons, we just focus on the essential. So we could improve here, and that's feasible. In a more in another aspect. So we just discussed the happy path that we have the ideal merge. We kind of skip a bit the conflicts because we envision that once we have a set of transformations that is not compatible, we could have a tool that helps the developer to select among alternatives. Of course, this will not solve all the things, but sometimes, you know, someone renames the same method with different IDs. This requires manual intervention, and then one could go there and select which version he or she wants. And yes, we'd also like to test this with people, okay, and especially this part of conflict resolution to see how that could be handled. Yes, and we are happy to take questions. Thanks.
We have time for several questions.
Thank you for the nice talk. It's an old school topic that is still hot, I would say. So you addressed this challenge that let's say the textual representation and the models you want to differ, difference and merge, they are not in the same world because the text lacks stable identity. So could you store them in a table outside of the source code, since programmers don't like to see that in their source code?
Yeah, we got that comment in the review, actually, if we could use some sort of external stuff. But aren't they still fragile anyway, or?
I don't know.
Yeah.
I guess if you have a source code location table, your editor can then help you, and then at least it will be sort of transparent, and maybe your algorithm can perform better when this information is available, and when it's not available, it falls back to the inaccurate behavior.
Yeah, I agree with your suggestion, but we really didn't, sit down and think how could we do this as an external representation. The source code was mostly like the, let's say, the most obvious way to attach things, and it was a bit pragmatic. Okay, we didn't explore much there. Yeah.
Thank you.
Welcome.
Other questions? So a question from my side. So you mentioned reducing or having fewer false positives and false negatives. What were you comparing against with that statement?
Okay, Tricky, do you want to answer this one, or?
I can answer it. So we did not compare our approach with other approaches, false negatives or false positives, because there are some, just a moment please. Sorry. Okay. Here, as you can see, in many approaches that we have presented, we have, I would say we have different granularity of conflicts. I mean, in the Git merge, as you can see, the bracket is inside the conflict. But in the JFCT merge, it has, the conflict is more localized. It's between the method, its origin. And it's difficult for us to compare to other approaches because we don't have this format of showing conflicts. We can have 3 conflicts or we can have 1 conflict. And for example, we only have 1 body transformation. We can change a lot in the body, but it's only 1 body transformation. When in other approaches, if the body of the method is so long, we can have different conflicts, it's localized. So we didn't find it's always useful, but it's hard to compare our approach when we handle body has a single transformation and then has a single conflict, and when other approaches in a long method have 1, 2, 3 conflicts.
Yeah, it's like the unit of measure is not the same. But when we claim that we have less false positives and negatives, we are showing situations that the tools don't handle. So it's these ones we are reducing. We could not do like a thorough comparison.
But would it be possible to argue that you don't introduce new false positives or false negatives?
Yeah, that's what we tried to see in the study, to see if our thing was not doing that, and no false positives, right?
Yes, no false positives and negatives, because we think that having a large database of conflict types between pairs of transformations and that is well implemented would avoid false positives, because it has a list of rules that the members have or not. And also about the false negatives, the application of the transformations, when well applied and well implemented, the application of transformation, that should not introduce any compilation error, at least syntactically. Semantically, it's a whole world.
Final question from my side. So you mentioned being specific to a particular language with your implementation. So maybe you can reflect a little bit on the sort of the key insights that would transfer to other languages.
Yeah, maybe I can take that one. Okay, the idea is portable. The implementation not, because, you know, for example, so we parse all the Java, we have this Java-specific nodes, and some things in the details is where the detection goes into the details, okay? So, of course, all methods have, all languages have functions and methods and so on, so that's the easy part. But then, for example, if you do this for JavaScript, JavaScript has no overloading. So in our case, if we see one branch has one method, the other with the same name, with different signature, that's okay, it's compatible. But in JavaScript, that stuff would be a conflict because it's not allowed. So it's those kind of, the devil is in the details. So, but the whole approach, I don't see any why shouldn't this be portable? The idea, not the implementation. Okay.
All right, please join me in thanking the speakers again.
There is an option to show the mouse on the screen. To show the things. So maybe.
All right. All right. The final presentation in this session will be by Sean Hadar on scalable spreadsheet-driven end-user applications with incremental computation.
Good morning. I'm Sean, and this is the work I've done with Shachar Yitzhaki. We are from the Technion, Israel Institute of Technology. So, as you all know, spreadsheets are electronic grids, and they are used to store data and compute data out of the stored data. Each cell in the spreadsheet is either a data cell or it's a formula cell that computes new data out of the stored data. Spreadsheets are visual and reactive, so they are very useful by both programmers and non-programmers, very widely in applications like Microsoft Excel, Google Sheets, Apple Numbers, and so on. This is an example of a spreadsheet. So as you can see, we have years, quarters, and for each quarter we have a transaction, either incoming or outgoing. And for each quarter, we sum up the revenues and the expenses, and the net income, and then we have the sum for each year of the quarters. When you change one cell in the spreadsheet, it can initiate many other changes, because one change leads to other changes of cells that depend on it, and other cells that depend on those cells, and so on. And when the spreadsheets get bigger and bigger, this is a big challenge, how to do it efficiently. There are two naive solutions for that. One is to recompute the whole spreadsheet every time, but that will obviously take a huge amount of time for big spreadsheets. Another naive solution is to make a graph of all the cells, and for each two cells keep an edge if they are dependent on each other. But that graph would be huge, and it is very hard to maintain. But as you can see in the example, when adding a transaction or removing a transaction or updating a transaction, the quarters sum and the year sums need to be updated, but the other quarters and the other years don't need to be updated. We don't need to recompute them. Furthermore, we don't need to recompute the entire sum. We just need to recompute the delta, and after by the transaction that was changed, and by that delta, update to the new sum. This is a spreadsheet in a framework called Spalier. Spalier is an object-oriented spreadsheet programming environment. So each cell is in an object, and the object has a hierarchy, and each object has a contained objects and fields. So there is a schema which defines the hierarchy and the fields. Our goal in the research was to look for a set, as small as possible, of cells that when we update one cell, these cells need to be updated and no other cells. And then we used the former data to shorten the data computation even more and to make it shorter. We created an algorithm for it, which I will present, and implemented it in Spalier using the schematic structure of Spalier. Our algorithm comprises of two phases. The first is the offline phase, which can be thought of as the compilation time. So before the user uses the spreadsheet for updates, we analyze the structure of the spreadsheet and create data structure that will help us later do fast updates. And then the online phase, which is the running time, can be thought of. It's whenever the spreadsheet is updated. When the user updates the spreadsheet, we use the data structure from the offline phase. In the offline phase, we create a graph of the columns, not all the cells, but only the columns. For columns C1 and C2, there is an edge from C1 to C2. If a cell in C2, some cell in C2, may depend on cells in C1. So if C2 is somehow dependent on C1, we have an edge. But a cell in C2 doesn't necessarily depend on all the cells on C1, but only on some of them. For that, we create three dependencies type, three edges type. The first is horizontal, which means a cell in C2 depends on a cell in C1 only in the same row. Then we have the incremental computation, the incremental dependency, which means that each cell in C2 depends on a set of cells on C1. That's the most complicated type of formulas. It's formulas like filters, aggregations, sums, averages, and such. And the third type is the arbitrary type, which means we don't have enough information in the offline phase. And then we say that every cell in C2 depends on all the cells on C1, which is a fallback to the baseline full recompute. Let's focus on the incremental dependencies. So each incremental formula has this general structure. We take this, which is the the object where the formula exists. And then we go with the function q from x, from this to x, which is a set of cells. And on each of them we compute a predicate, that is the filter. And then for all of the x's that pass the predicate, we compute some arg function. And then we aggregate all of those by sum or any other operator. Let's see an example. So this is a spreadsheet of classes and students in the class. Each student has a grade, and each class has an average and a STDF. STDF is our function phi, is our formula. AVG can be computed automatically from the grades, but for this example, to make it more interesting, the AVG is manual. It's a data cell and not a formula cell. So, so the STDF, the phi, is we take all the students of the class. This is class, because phi is in class. So we take all the students. For each student that has a grade of 55 or more, that's the filter, we compute the arg, so which is x point grade minus x point class point AVG squared. And this STDF is dependent on two things which can be changed. And if they are changed, we need to update STDF. One case is that a grade of some student is updated. And the second case is that an AVG of some class is updated. We identify the read sites. Read sites are areas of the formula that refer to modified fields. So each read site, which we call PI, takes us from X, which is the set of cells to someone, to Y, which is the modified field. So in this example, the X for each PI is student, because the set of cells that we sum on is students. And each PI takes us from student to Y. And what is Y? That depends on which object was modified. So in the first case, a grade is changed. So Y is student because grade is contained in the student. And the grade is found twice in our example. Once in the arg part, in the left part, and once in the right part, in the predicate. So in this case, we have two read sites for grade, which are both the identity functions, with p of x to x. In the second case, some AVG is changed. And so if AVG is in class, so Y is class. And AVG is found once in this formula, in the arg part. So in that case, the read site will take us from X to X point class, because it takes us from the student to the student point class. After we have the read sites, we can find the affected objects by them. So for each read site PI and the modified object Y, we compute E of Y, which is the set of cells that may be affected because of modifying Y. That's all the objects in O that Q of O intersect with the PI inverse of Y. Because there is some cell which is both in Q of O in the sum and in the inverse of the read site. Therefore, EI of Y is Q inverse of PI inverse of Y. And then we unify on all of them and get EY, which is a set of all objects that maybe need to be recomputed, may be changed because of modifying Y in respect to our formula phi. Let's see it in the example. So we did have Q, which is the set of cells. Each Q takes us from a class to all the students. So Q inverse of X is X point class. In the first case, a grade of some student is modified, and therefore, as we computed before, the PIs were the identity, so the inverses of them are also the identity in the left side. So P1 inverse and P2 inverse of Y is Y. Therefore, E1 of Y and E2 of Y are both Q inverse of P inverse of Y, which is Y point class. And therefore, EY, which is the unifying of them, is Y point class. That means that when a grade of some student is modified, we get the class that contains that student, and that class needs to be is affected, and its STDF needs to be recomputed. In the second case, we have AVG of some class that is modified. Therefore, PI was Y point class, so P1 inverse is Y point student. E1 of Y is Q inverse of P inverse of Y, which take us back to Y. And therefore, EY is Y. That means that when an AVG of some class is modified, this class is affected, but only this class. No other classes are affected. So when an AVG of some class is changed, we need to recompute the STDF of this class. Then we have the incremental change. After we find the EY, if Y, which is the set of cells that must be updated because of modifying Y, we don't need to recompute the sum again, necessarily, but we do need to only recompute the items in the cells that changed and update the sum by the delta. So we check for each predicate if it's changed, and if it's changed or the argin is changed, we recompute them, but we don't recompute the whole sum again. So that is the algorithm of the offline phase. We check for each two columns that may depend on each other. We take phi, which is the sum, or any other formula. We compute the read sites of this formula. If all the read sites are horizontal, which means they are all in the same line and don't go to other lines, then we say this dependency is horizontal dependency. If it's an aggregation, like filter, sum, etc., then we say this is an incremental computation. We do need that the Q and PIs are invertible. And if they are invertible, you can say this is incremental dependency. And in the other cases, we say this is an arbitrary dependency. In the online phase, we get a set M of cells that were changed. And for each M, we check the columns of M. For each cell in M, in the set M, we check which columns they are found in. And for each column, we use the graph to get the columns that depend on that columns and check the type of dependency. If it's an incremental dependency, we compute E by the data that we stored in the offline phase and get E, which is the set of cells that need to be recomputed. And because it's an incremental dependency, we can recompute them by the delta. If it's an horizontal dependency, we recompute those cells that we get from the read sites. And if it's an arbitrary dependency, then we recompute all the cells in that column. After we recompute all the cells, we make them the new M, because after we update those cells, there are other cells that are dependent by them. So this is the new M, and then we do this iteratively until M is empty. In the empirical evaluation, we wanted to check how much time we save by our algorithm. So we created a benchmark of spreadsheets. We have 6,215 spreadsheets of 5 schemas with varying sizes and data. And we tested 4 modes of operations on these spreadsheets. The first 2 are the naive solutions. The first one is recompute the spreadsheet after each update. The second mode of operation is a full graph of all the cells and their dependencies. The 3 and 4 is our solution. 3 is our solution, but without the incremental change, without the delta. And number 4 is the full solution with the delta. So these are the results of horizontal formulas. In the x-axis, this is the size of the spreadsheets, the number of the objects. And in the y-axis, this is the running time of updating a set of cells. We can see that mode 1, the recomputation of all the cells every time is much slower than the other modes. We can also see that modes 3 and 4 are quite same because the difference of them is the delta computation, but it doesn't affect here because here we have only horizontal formulas, and the delta is affecting when we have incremental computations, sums. So here we added incremental formulas, and then you can see that mode 3 is slower than mode 4. That means that the delta computation saves us some time. You can also see that mode 2, the graph of all cells, is also very good in running time. But in the next slide, we can see this is the memory consumption. In the x-axis, you can see the spreadsheet size, and in the y-axis, the memory of the data structure. So you can see that mode 2 is much more taking much more memory than our solution. So that's the main disadvantage of it. So to sum up, spreadsheets applications are very useful, and they need to deal with a huge amount of data, which is growing up. In the presence of this challenge, updating the spreadsheet every time needs to be done efficiently, and the naive solutions are not good enough because they are either very slow or taking too much memory. So we presented a new solution for this problem by taking advantage of a schematic structure of the spreadsheet. In Spalier it has the structure, but for every spreadsheet with a structure, this solution can be applied. We focused on aggregation formulas and created a data structure in the offline phase, and then used it in the online phase to recompute the necessary fields more efficiently. Questions?
Question in the back.
Thank you very much. I have 2 questions. So the first is, in incremental computing, you often have this problem with granularity, right? Where you have these 2 extremes, right? Recomputing everything is like granularity, where everything is one unit that can change only at once. And if you have a cell graph, I think you called it, where it's very fine-grained. So isn't there something in between? You present one solution, but like a naive one where just like somehow figure out, oh, there are cells that happen to change together a lot and just treat them as one thing that can be updated, like it's full recompute but locally. Have you kind of thought about what is the right granularity for spreadsheets?
Yes, that's an option, but that requires to analyze the usage of the spreadsheet to see which cells are updates, have a lot of updates, and get to. You can take the full graph of cells and and only save small parts of it. That's a good optimization. But I'm not sure it will do well for any kind of spreadsheet, but it's a nice option to investigate for further research. Yes.
Okay, and the other question I have is, like I'm lucky enough not to use spreadsheets a lot, but when I do, I often have to insert rows or columns, right? And as a consequence of that, the definition of cells changes, like there's a sum over a range of things, and then Excel is smart enough that, I'm inserting a row, so probably now I mean the sum from, this row as well. So how do you handle this kind of change? It's a different kind of change, right? Not the data in the cell, but actually the formula is changing.
Yes, but if the spreadsheet is a schematic, then the sum is defined not for a range of cells, but just to be all the cells in the formula. So for schematic spreadsheets, the syntax of the formula allows it to just contain all, and when we add some row or remove a row, then it's already included in the original formula. Because the formula just says take the whole row.
So perhaps related to those questions, can you say exactly when this static compile time step is being executed and something about the overhead that it causes?
The time measurements were done actually on this computer. We created a benchmark automatically with a script that generates a lot of spreadsheets of different types, and then created a set of cells that are changed, and measured the time that it takes to update the spreadsheet. Is that what you meant?
Yeah, so what is the overhead specifically of the compile time step compared to the incremental recomputation? Is that something that you analyzed?
I don't have it, but it was quite a short time, especially when there are the most important is that it's a static time. It's not growing when the spreadsheet is getting bigger. But I don't have the amount of time, but it's quite short.
Thank you for your paper. I'm glad some people are still doing basic spreadsheet research. You said you focused on aggregation formulas. Do you think that you would still get the same result as far as the memory optimization between the traditional dependency graph and your approach if you just had an arbitrary set of spreadsheet formulas, not just aggregation formulas?
Arbitrary formulas are our fallback when we don't have enough time, enough information in the offline phase. It does better than recompute the whole spreadsheet, because we just recompute this column, the dependent column. That's also that can be also a good start to analyze the columns dependent, but not further save any data. So we can recompute only the relevant columns and not all the columns. So this is actually a first step, and the second step is analyzing the formulas in such a way that we don't need to recompute the full column when possible.
No question.
So I might have missed this. It seems like the compilation phase, the collection of the graph, didn't seem fully precise. I wonder, I guess my first question on it is if that is because of the type of data you receive or that you're able to collect from the spreadsheet that you're working with. And second part of that is if there are improvements that could be made or obtained from that collection of data that would improve the speed or precision of your algorithm.
Yes, if we have more data on the spreadsheet on the specific spreadsheet, we can have specific adaptations for maybe other types of columns that fall to the arbitrary type, but we can adapt specific handlers for them for the specific spreadsheet. Or if we can see that some kind of formula is used a lot and we don't cover it and it falls to the arbitrary part, then we may have in the further research find some shortage for a way to shorten this computation. So that's a nice plan for further research to cover it to more kinds of formulas.
Thank you.
All right, let's us thank the speaker again. So Onward will continue at 2 p.m. In this room. Enjoy your lunch.
going already? Okay. Cool. So we may as well close the door so that when they move the trolleys, it will be acceptable. So welcome to our Beyond Language session, sort of aligned with this morning's Filian's keynote. Remember the weird things that programming language syntax does versus the more normal natural language? It's probably more aligned with that for all the three talks. So first we have Asaf on could no code be code, and we'll just give people a moment to sit down and carry on.
Okay. Could no code be code? In this work, we present our onward vision toward a no-code programming language for citizen developers. I'm Asaf from 2.software, and this is a joint work with David Lawrence from the Open University of Israel. There are a lot of programming languages today. But it's time for a radical change. Why is that? Because software does not meet its challenges. By 2025, in a year from now, or a year and a half from now, for every field programmable position, there will be one unfilled, and in 2023, the situation is worsened, there will be two unfilled. This is causing already a 1 trillion a year in financial losses for companies. And this is like the revenue of Apple and Amazon combined. It's a huge amount of money. So this brings, the scarcity of programmers brings citizens to the stage. In 2022, last year, in large corporations, there already were 4 citizens for every programmer. Which tools do these citizens use? Low code and no code. However, as IEEE has stated, each of these tools solves a subset of the needs. They are not flexible, resembling hardware or modern software. They may provide some programming capability, but they are not a GPL. So there's a gap between the current tools and the citizens' actual needs. You may say that their programming skills are low, but this does not mean that their software needs are low. In fact, from the experience we gained with citizens, I can tell you that their needs are no different. They need flexible algorithms, they need complex data structures, they need a GPL. In this work, we present a powerful no-code GPL. No-code means that the entire development is done by mouse actions only. That is, without typing a single line of code. In addition to no-code GPL, this language has some more important properties, such as cloud development, which means that you don't only develop the program in the cloud, but it also runs in the cloud. And if you have a team, if you have a team, then it means that you know exactly what your team is doing right now. Collaboration, like in Google Sheet and the Google Docs. You can sign in and help your colleague program and overcome an obstacle. Sharing. This means that in a click of a button, you can post your new creation to the cloud, and the platform automatically sanitizes the code from domain-specific information. Live programming means that you can select a specific function or a rule and activate just this function. Native tongue. If you look at English proficiency survey, you'll find out that there are many countries, many modern countries, that are in the moderate or even low group. Why leave so many good citizens behind? Our language can speak their native tongue. And visual coding means that the flow control can be developed with a flowchart. And this is more appealing to citizens. So the motivation. At this point, you may be asking yourself, but how could it be? How could no code and GPL coexist? They are in two different worlds. In one, we have citizens with domain-specific solutions that are simple to develop, but are very inflexible, hard. In the other, we have programmers with general-purpose solutions that are complex to develop, but are very flexible, soft. In fact, if we take the good things from both worlds, we can get a no-code GPL. Programming languages are indeed complicated, but it's not anyone's fault. It has been so for 70 years, since Corrado Bohm invented the first compiled language. You can see in this table that programming languages are still created. Look at TypeScript and Rust from the last decade. However, they are not attacking complexity. Rust, which is gaining popularity nowadays, is one of the most complicated. One notable exception here is Go. One of the goals of Go was to make it simple. The three inventors had an agreement. Each had the right to veto new features. So this kept Go about 2 times smaller than Java and C++ that were used in Google at that time. And this was achieved by 3 superb engineers. One, a Turing Prize winner, Ken Thompson, who invented Unix. So if Ken came in the morning and said, "Hi guys, I've got a wonderful idea," the 2 other guys sent him back, "Come tomorrow with another idea." In a talk titled "Simplicity is Complicated," Rob Pike explains the many complications they had in making a simple language. We continued in this direction and created a new language which is 10 times smaller than Go. Just look at the 2 yellow lines. I want to make an important note here. This project was not motivated by curiosity. It was not that I had nothing to do at home and thought, it would be a great academic challenge to see how far we can get making a simple language. No, this was done already 30 years ago by Urban Müller, who invented BrainFuck with only 8 commands. This is how the Hello World program looks in BrainFuck. Is this appealing to anyone? So, being small does not necessarily mean being simple. We wanted to create a language that will be simple, will be small and simple. Easy to read, easy to learn, and easy to program. This project took 5 years. It's like another PhD for me. My son helped me in the early stages, had a great contribution. And I'm telling you this because it took a long time to, as Steve Jobs said, to dig into the complexities and understand their nature, to be intimate with these complexities. Only when you understand the complexities, you can get rid of things that are unnecessary. So the first version of 2, this is the name of the language, things object-oriented. The first version simply failed to fly, but now we feel that we have an aerobatic plane. So language design. Look here at the 10 syntax rules of 2. Compare it with the 1,400 rules of Java. Let's see a simple example. Let's see what's behind this naive hello program. You see here the hello thing, and it contains a terminal and one rule, notifies up, that is triggered by the runtime system when hello is up and running. So when hello notifies up, the terminal print Qashqaish. Let's make it a little more complicated. Here we see already that print is variadic. It takes a let's see the terminal thing. You can see the print function. It takes a variable number of string interfaces. An interface is defined as in Go and as in other languages. Look here at the 2023. It's a number, but it's printable. It's printable because the number thing implements the asString function. Similarly, the hello thing itself is printable since it implements the asString function. So the result would obviously be Qashqaish 2023 hello world. I want to make a note here. See, the print function is intuitive, but it's intuitive. You can throw anything and it will be printed. But 2 is not, just a minute. Two is not dynamically typed. It would be disastrous to have a dynamically typed language for citizens. 2 is strictly typed. And this means that the conversions that you saw here are resolved already in compile time. Before showing what's in 2, I'll go briefly of what's inessential in 2. So we saw already that keywords are inessential. Basic types such as int and float are simply things, so they are not part of the language. Binary operators are all replaced with functions. Variable declaration, global, pointers, and import section are also unnecessary because in 2, we want to comply as much as possible with the rule-based abstraction. And in a rule-based system, for example, think of a checkpoint router with a firewall. You cannot find their variable declarations, globals, and stuff like that. Let's see what inside. Things-based. This means that everything is made of thing, and this is again because thing or object is an abstraction appealing for citizens. Event-driven, again, a simple abstraction that citizens understand. When something happens, do this and that. Component-based means that it's open for third party, and it uses plug-in. So hot plug-in means that if I have in a factory, I have a conveyor, and I have a feeder, and I want to replace something in the feeder, I can leave the conveyor working. Marketplace is where all the things that were ever posted for sharing is handled. And citizen-oriented, let's see in more detail what is that. So this is the IDE, or as we call it, CDE, because it's cloud development environment where things also run. This is the compact citizen view. This is the expanded citizen view. And this is the classical programmer's view. So you see that the program is segregated into 2 sections of data structure and algorithms. And the algorithm section is further separated into rules, functions, and events. This is in contrast with most GPLs where you have all these sections intermixed in one monolithic piece of text. And we think that this may be will be appealing for citizens. Data structures. 2 does not have multiple data structures, only one. And it does not have nested data structures. See, for example, this course thing. It has 2 arrays. One of numbers, student grades, and another array of student names. We can replace these 2 arrays with one student array. And the student thing will include these 2 fields, grade and name. Expressions. In Go and in many other languages, you have lots of operators. In 2, we replace them by functions because citizens are not necessarily practicing development daily. They can come back after 6 months and they should understand what's going on. So we're not expecting that they will remember all these cryptic symbols. Fluent style chaining. If you were to read this over the phone to someone, how would it sound? A plus B times C squared, right? This is how you write it in 2. A plus B times C squared. Concurrency. In Go, you would write go start. And in 2, you would write go run thread. And I don't think that we compromise here anything for readability. Write assignment. These 2 lines calculate the volume of a cylinder. This is the assignment operator. If I read this, it would be assign something to base or assign something to volume. The roots for this comes, of course, from the math language where we have y equals f of x, but math equality is not an assignment. It would be therefore counterintuitive to put base and volume on the left. In 2, we do it this way, where the arrow stands for go to. And advanced citizens would write it like this. So it's math pi times radius squared goes to base times height goes to volume. Autodependencies. This is our cylinder with mass and 2 numbers. But where are the dependencies? Well, in 2, we don't have dependencies. They are not part of the language. Instead, they're taken care of by path distances in the directory tree. And directory is, again, an abstraction known very well to citizens. So, for example, if the cylinder is implemented under a staff geometry, and the mass and number are in 2 core, then the cylinder will depend on them. But if now I decide to create my own version of math under a staff geometry, it will be selected instead because it's closer. If later on I decide to revert back to the version in core, then I must use an explicit path. Control flow. In Go and other languages, you would use a keyword, if something. And in 2, you would use the question mark. Iterative statement. In Go and other languages, you would use the for statement. In 2, you simply prefix the action with a star. Anything you prefix with a star would run iteratively. Wildcards. In this loop, we sum up the elements of list into sum. This is how it would look in 2. Sum add to it the elements of list. And this is the wildcard operator. So now for the demo. At the top, we see the programs that I'm working on right now. Here we can see the different views that I talked about. the expanded view, the classical programmer's view. Let's go back to hello and make some changes. Let's run it. Qashqai's 2023, hello world. Now let's make a small change. Let's add another line with the current time. So for that, we need to bring in the time thing. The time thing is found in 2 core. And let's create a new action. I can create a conditional action. But now I need only this action. So again, we need the terminal thing. And the print function. Oops, I have here a red plus. This means that this line won't compile. And of course it won't compile because print function requires at least 1 parameter. So let's bring it in. Time. Now, let's run it again. So you see the current time. Well, I'm off schedule. I should be hurry. It's 16:21 in Israel. Okay. Just a minute. So back to evaluation. We evaluated 2 in 3 scenarios. So in one scenario, 2 was deployed in a large agriculture farm with 15 indoor growing rooms. A lot of money was spent on this agriculture farm, and in this farm, we control various aspects of the growing rooms, such as electricity, cooling and heating systems, temperature, humidity, CO2. This system currently handles 100,000 events daily with 100 instances and 25 components. In another setup of a factory that we tried this year, once the IDE was completed, we had a system in a lab scenario with a mixer and a boiler. And this was done by a citizen supervised. And in the third scenario, this was an automation, office automation scenario. We tried it with 6 citizens that had to program unsupervised after watching a movie, a video. They had to create something fairly small with only 2 rules. So the lessons learned. Programming, I'll start from the cons. Programming is fairly difficult for citizens. It's not trivial for them, it's challenging. What seems to be trivial for us might not be so simple for citizens. For example, they had troubles in finding the right objects for the task. They had problems with fluent style chaining, which is not known to them. They know perhaps Excel and Google Sheet, but they don't know fluent style. They had problems with the Boolean algebra because they are not educated with Boolean algebra. The good news is that they can program. Citizens do explore their programming freedom. The playground that we have plays an important role where they can gain confidence. They have no penalty there in making mistakes. And mentoring is very important at early stages to ramp up, get to speed with development. I leave the related work for reading. Conclusion. So we saw software is not meeting the challenges. A new paradigm of no-code GPL is needed. We created a tiny GPL at the core, and with the CDE on top of that, the IDE on top of that, this enables to democratize software use. We show a powerful no-code GPL with many properties that you can find more about in the paper. Future work. Lots of things need to be done. I will not go into these things deeply now. A debugger. Citizens do not know the word debugger, let alone how a debugger works. So you have to think carefully how you create this project to make it simple for them. Documentation framework, very important, and so forth. Citizens need a lot more need to be done, and we can all join forces and help them make a successful entry to the programming world. Our contact is also simple, 2.software.
Thanks, Asaf. We have a few minutes for questions. We're in a very tiny room, so we can run around.
Hi, thanks for the talk. First, a small kind of question, observation, like COBOL, back in the days, it was also a language very verbose, like there was no operators, everything was very literal, like the add and the plus, but somehow that style didn't prevail. So how come you are so convinced that writing add and plus is better than writing the operators?
Good question. It all depends on the projection. So you can decide. We have the AST inside. So
you allow both.
We can project it back with plus and minus and even binary operators. It's no problem. So what I'm saying, is it's just a matter of projection.
Yeah. Okay. And if I'm allowed, how do you relate? Maybe you discussed that in the paper, but how do you relate that what you are proposing with tools such as OutSystems or Mendix, which are also general purpose tools, which people without background in informatics, they are able to use? Do you know those tools?
The truth, I'm not familiar with these two.
Okay. But they are, OutSystems, Mendix, they're quite famous no-code tools, so I think you should contrast, because they're also general purpose, so somehow they are achieving a similar thing. Okay.
I'll look into that.
So if experienced programmers mess up and introduce bugs, I would say that getting a program right for a citizen would be quite difficult, right? What kind of tools do you see that could help to get programs right? So not only debuggers, as you said, are too difficult, but what kind of tools would help getting in an iterative phase to a correct program?
So I think this is a good question, because programming is difficult and you cannot change it. So we see a lot of documentation, and once we have a marketplace where people can post programs, I think that the programs that will be chosen, you can put a price tag on your program, and people will choose it not just for price, but also for documentation. So perhaps there will be a video there, and you'll be able to see how to do things in the right way. So you'll have, as a citizens programming, you'll have to learn a lot. You have to see a lot of videos, short videos that people prepared for you in the marketplace. Otherwise, you can also get some assistance by mentoring, but it's difficult.
So last
Okay,
question.
so how do you compare with the Smalltalk? Like in general, the people from the Smalltalk community were first made a very core, elegant language, and then they spend massive amount of effort into trying to make graphical support of various kind to promote its usability. In some sense, your project seems to be a recreation of the Smalltalk experiment?
Well, Smalltalk is really a good example because it's really a small language, but I think that what we've created here is something that was focused on citizens, all the way thinking about citizens. Citizens in mind makes you come up with something a little different. Okay? Thank you.
All right. Thank you very much. Cool. And now we have Mark with our second talk. Hopefully people have time to, calm down. That's right. All right. Is the screen going to turn on? Oh, great. Okay. So once the door closes so that it's kind of quietly here. And yeah, cool. Thanks, Mark. Please go ahead.
Sure. So thanks, everybody, for coming. I'm really excited to be talking today. And I'm going to take everything down to sort of, I think, the core base origins of programming, at least as I think about it. And the first question I want to ask is, what is the purpose of a programming language? What is its role in software development? Well, sort of early on it was, I have a program and I need to express it in a way that I can execute it on some physical hardware, right? That's obviously a very important thing. Or, if I'm a formal methods guy, I can convert it to some mathematical model and reason about it. So it's a means for expression to some formal or mechanical system. In modern software engineering, I have a team of 40 people or a distributed project. It's a means of communication with other humans who are also working on the program. And of course, recently everybody's very excited about ChatGPT. Well, now it's a medium for an AI agent to, in whatever way it's come up with writing an algorithm, to express what its solution is or its candidate solution is to me, right? And then also, well, that AI agent's going to be looking at my code to try and understand what I want, and so it's going to be trying to reason about it. And so I kind of segue there. Well, what's common about all of these? There's some system that's looking at this programming language artifact and trying to reason about what it means. So, in a sense, it's a little tautological, but fundamentally, all of software development is a problem of reasoning about the meaning of some chunk of code in some context. And, how do we build a language, or how do languages support this reasoning? And it's a broad audience. They're humans, they're automated developers, there are these AI systems now, compilers, like, what do programming languages do that support this? And, kind of the first part of this talk, what are things that programming languages have that are maybe anti-features, that maybe come along for historical reasons, but on some fundamental level, just make it hard for us to understand what on earth is going on with a bit of code. And so I'm going to sort of break it down. I have these categories. So let's talk about, automated reasoning and symbolic analysis of code. This has been a topic of programming language research ever since programming languages were invented. And over the years, we've seen, at least in my experience, kind of a couple of common themes that come up here. Loops and inductive invariance. Anybody who's ever done program analysis knows that life is all good when you have straight line code, but when you have loops, suddenly things become, well, less fun. Mutable state. Everybody loves frame rules and invariant analysis and aliasing and all this sort of stuff. And then identity and equality, right? Do two objects point to each other? If I mutate one, does it change the other? Are these things, what is the structure of this object graph? These are just huge, long-standing research problems. I mean, dating back 40 plus years for each of these. And, a lot of great work in this area. I've done work in this area. I know there are papers here this week in this area that are improving the state of the art, but, the current state of the art and where I'd like to be and able to really reason about hundreds of thousands of lines of code effectively is a big delta. And I think these might just be foundationally hard problems. And, it's a challenge. So humans are much better at dealing with a lot of these things because we don't go and look at every little detail. We kind of make broad assumptions about most likely things that are going to happen. So that makes us really good at dealing with, loops and code that might mutate stuff because we just make assumptions that it probably doesn't. And, that means we do pretty well, but oftentimes if there are these unexpected things, non-determinism, surprising behaviors, they can really throw us for a loop and cause us a lot of grief. I mean, if I log something to, log4j, why would it go on the internet, download code, and execute it untrusted? That would never happen, right? Like log is just to put my message in some stream. So, these things can really blow up. They're simple in hindsight, but nobody knows every line of code of their million line of code application, so it gets us. AI agents are they're an interesting intermediate point because they understand a lot, like they've seen all the code on the internet, right? But they are only going to look at and understand a piece of code based on its syntax. They don't have an understanding of the semantics of a programming language, right? Or the specific semantics of your application. And so this means they can sort of hallucinate unusual things, or if something is in your code but hasn't been in their training set, they're not going to know what to do with it. So, a funny example I have is I saw a great demo. Someone was using ChatGPT-4 to do calendar scheduling with Google Calendar. And so they said, you want to schedule a meeting tomorrow. And it goes and it generates all of the right, RESTful API stuff, the JSON objects, everything. And it has to pick a time for this meeting. So what does it do? Well, everybody who's done a tutorial for how to use Google Calendar just sticks in 10 a.m. So it thought picking 10 a.m. as a constant meeting time was great. I'm in Europe, you're busy at that time, but 10 a.m. So it doesn't have this notion of common sense that I should check availability before I do these things. So they they have this funny, if it's not visible in the syntax, or it hasn't been in their big training set of all the code, they just don't know about it, right? So they kind of have these blind spots that they don't know what to do with. So the takeaway is, I think reasoning for all of these agents is hard. Now, there's some sources that are common, right? Like, mutability is difficult for everybody. But different agents have different bits of struggle there. And at the end of the day, the inability to effectively reason about what this code is doing has real costs, both it makes my life less fun because I got to deal with this. But I mean, real money costs to big businesses. Like, it slows down development velocity. If I have to look at a method and then I have to go and F12 over to some other code and then F12 over some other code and spend 30 minutes trying to figure out, does any of these mutate global state, or can I make this assumption? That just slows down my development velocity, requires bigger teams, right? It prevents the deployment of really powerful tools. There have been great demos of incredible things for bug finding, but deploying them at scale is difficult because they just don't scale to these big code bases. Compilers can't do all sorts of optimizations that they'd love to do. It increases errors and risk, log4j, huge amounts of money lost because, a simple reasoning oversight in the code. And it excludes non-experts. Like the talk before was great about how complexity and some of these subtle semantic things really make it difficult for someone who's more of a citizen developer to use these tools effectively. So what's the vision of this talk? Well, hopefully I convinced everybody that we have some anti-patterns here that we could probably do better about. So it's how do we build this software stack that's optimized for reasoning? Like, I want to go back to the ground level and look at programming language design from the bottom up and say, for every choice I want to ask, is this just a historically convenient choice, or is this choice going to be something that makes it easy to reason about this code, and can I get rid of it if it's something that is not absolutely there and causes some problems? And so kind of the funny thing in this talk is I'm not going to tell you a cool new programming language feature or an amazing new analysis technique. I'm just going to say I'm going to make things as simple as possible using existing ideas and technology for the most part. Like, I don't want to solve the problem of complexity by adding more complexity. So we're just going to go back to the basics here. And so we're going to say, well, let's look at our core IR. The Bosky language that I've been working on consists of a core IR and then a surface syntax. So for the core IR, it's mainly focused on supporting automated reasoning, not surprisingly. And we're just going to eliminate some things that cause us lots of grief. So it has no loops. It's just going to use higher order functions instead. All values are immutable and referentially transparent. Just simple if-then-else based intermediate representation, so compiles down super well to all sorts of reasoning tools. And an important thing is that's fully determinized semantics. So that's not only is there no undefined behavior, but things like the enumeration order of a map or the stability of a sort is always fixed. So you never have to do your funny case split, gobbledygook and consider an exponentially increasing number of options. The other thing that we really put a lot of effort in is in making implicit information explicit. right? So if I'm writing an analysis, I want all sorts of useful information to be immediately available in local context and not having to do lots of global interprocedural analysis and hunting and pulling in information from all sorts of places. So everything's strongly typed, including primitives. We put a lot of data invariants and everything so you can understand what is true at any given point in the code, and you know what things are definitely not going to change. It's very obvious. Now, it's very easy to go and create a programming language that has no bugs ever written in it because no one ever writes a line in a code in it because it's so miserable and painful to use. So the next challenge is, well, maybe I have a language with a core that's very easy to reason about for an automated system, but now how do I connect that core to a nice surface syntax that's very friendly for these human and AI agents? So, you know, it has to be a full programming language. It can't just be a DSL. Like, you should be able to write whatever computation you need in this language. We want it to be very approachable for a modern dev coming from sort of this, you know, line of business, IT industry, small, medium enterprise development space. So I'm a C# developer, a TypeScript developer. I should be able to look at this code. It should take me a couple days, max a week, to be up to speed in using this. Shouldn't be any clever and deep knowledge of you know, proof languages or special semantics or theorem provers required to use this. Like, I should just be able to come in as a somewhat skilled developer and be productive and happy. And so we really did a lot of work to connect things that developers seem to be very attracted to. So like block structured syntax with variable reuse, adding things like typed strings to eliminate a bunch of stringly typed APIs to make it very easy for these types of developers to express their intent clearly and simply. And then we use some clever compiler techniques to connect these down to that nice core IR. So let me just show you a couple samples so you can see. So here's an absolute value function. As you can see, this is almost perfectly legal TypeScript. It has a nice block structured syntax. It allows variable reassignment. So if you were to ask most TypeScript devs write abs, they'd write something exactly like this. So they'll be very happy. Instead of loops, we have these higher order functors, which allow you to just, you know, say all of to map a predicate over all of something. We're a little careful with lambdas. So for example, developers get very confused when lambdas start getting passed up and stored in locations and passed around. And empirically, people have shown that about 95% of all lambda uses are in, you know, a primary argument position. So this way, we force that, you know, in the compiler, and then we can compile them out, and everything becomes first order and super easy to analyze on the back end, and prevents a bunch of confusing software for our devs. So I'll just break down a couple of examples of some stuff in the Bosky language that we do to make it, you know, easy to reason about, both on the front end and the back end. So here's block scoping. We have our abs function. As I mentioned, it has, you know, multiple assignment in here, and we want to have a pure functional back-end language. So the nice thing is we have no loops, so it becomes very nice to, or convenient to do a dynamic single assignment form. We just rename all the variables, put a phi function in there, and now we're just, with a little bit of syntactic magic, we're back to our pure functional let-based language, right? We have a little feature called like ref methods that allow us to fake mutability at a single variable level. So we don't get into a bunch of aliasing and mutability, but users can write nice stuff where they want to say intern a string in some table and be able to process, you know, through data repeatedly. So they can write this ref method, which is basically going to take the argument and mutate it in locally, and then on the return, do the tuple return and do all the unbundling for them. So then you can write some code that says, you know, I have this environment, I call intern string hello, and I'm going to get name ID 1, but I'm going to implicitly update the environment there. I name ID 2, implicitly update the environment. And so I can write this sort of natural imperative style code in the very common case, but prevent it from becoming that, you know, very complicated to reason about thing where I have mutable graphs of references going all over. Another one which has seen a lot of popularity with developers we've worked with is type strings. So especially in the cloud programming space, you have these, what I call them stringly typed APIs, because the only thing everybody understands is byte arrays and strings. And so you'll have a method foo that takes arguments string, 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 right? And you're like, well, good luck swapping them or guessing what they are or guessing what the legal values are. And so this allows you to say, I'm going to have a regex that is a zip code US. And now I'm going to write a method that takes a string, which is a string of zip code US. And this is actually now a typed object. And we do the regex validation as we go. And so you can call this method, and it'll check that the string literal conforms to the regex, and there'll be a compiler error if it doesn't. But then also if you have string literals of other types, these will also be string errors, and we can do all the parsing and validation for you. So this is a really nice way to make this implicit information that appears in a lot of these stringly typed APIs very explicit, both for the programmer to immediately understand the intent, but also for the analyzer to then be able to say, oh, if I want to do fuzzing on this method, I'm not generating random strings, I'm generating strings that conform exactly to this regex, and I can be much more effective in the tooling space as well. So this is a nice synergy where features that make it easier for the developers to express intent, make it easier for our tools to key off that and generate better results, making it developers more likely to want to express their intent, right? So we get kind of this virtuous cycle going. In a similar vein, we provide built-in support for like requires and ensures on functions, and of course invariants on data types as well, right? This is one of the things that brings a lot of value. So I sort of talked about the language a little bit. We've been working on this for several years, and I claimed that this is better for automated reasoning and these other tasks. So one of the things I've been doing is building a couple prototypes of this to kind of validate this. So let me show one of them. So this is kind of goes and says, I want to build a small model verifier. And that is, for any possible runtime error or user assertion or invariant with arbitrary predicates that they've written there, I want to either be able to generate a witness that triggers that error, and then go and actually construct the concrete input that will cause that crash, so I can open a bug report in your GitHub repo, and the developer can go act on that information without having to understand the prover or traces or anything. It's just the same debugging experience they know and love. Or prove that there's no small model that'll generate it. And by small model, I mean input collections with like 5 elements or less. And this is kind of conventional wisdom that, hey, if there's no small repro for your bug, like it's going to be tough for us to fix it. It's going to be a lower priority for us. And empirical studies indicate that this is a pretty common property. So this was a good sweet spot for us. So as you might guess, if anybody's familiar with doing SMT encodings for languages, the way I describe the language, it's actually very simple, and it matches almost one-to-one with the SMT theories you have in a solver like Z3, right, which is the one I use. So a lot of the primitive values map directly across. All of the data structures go into the theory of constructors, and since we have a finiteness on the collections, they map to sequence. These are all decidable fragments, so we actually have a decision procedure, and Z3 is very good at these particular theories, so it's quite efficient. Just for those of you who aren't so familiar with this, let me just show an example. Here's our absolute value function again. And then here it is in SMT-lib. So you see it almost goes directly across. So we can throw this into Z3. It churns away, builds a model, comes up with an unsat core. All good fun. So here's an example of it running. This is a little tic-tac-toe game. You can see I'm going to set a cell mark, and I want to make sure that it's empty before I place a piece there. I have a little test file that has classic unit tests, also has some of these property-based tests where I'm just checking a condition, and then I have an unbound input value that the solver can then go and try and instantiate to cause an error. And so it'll run this unit test, and you see it takes about a half a second for each test, and most tests pass, and of course I have one that fails because it's good for a demo, and you can see it actually generates the concrete input that a developer could go debug. And we're not doing anything clever here. We're just doing the naive, like if you're going to tell a grad student, here's, in a class, like here's how encoding to SMT logic works. You do it, no fanciness, and it's actually very efficient. Some folks at Morgan Stanley thought this was pretty cool. They gave us a couple of examples that they use for their internal tech demos about some trading applications, and we're like, here are some properties we'd like to check. And we could do the same thing there. I talk about this a little bit in the paper for folks that are interested. But this scales up quite easily to thousands and thousands of lines of code. So that was cool from a symbolic analysis standpoint. Maybe for AI, like can we build better AI programming development environments using this sort of approach? Does it help this as well? So here's an example. I just have a function, find max pair. This is like you do with Copilot today. Give it a little comment about what it's supposed to do, write the signature, ask it to come up with a solution, and it comes up with this, which is I mean, it's in the right direction, but for some reason it's not doing the max of the pair. It's just taking the max of the first element and returning the pair that that corresponds to. So, you know, not quite right, not super far off, but as I was mentioning, one of the great things is in Bosky, we make it really easy to explicitly put your intent around in the code. So we support things like you can have an example that's a part of the function signature. And you can go and put in this ensures clause that tells you what the output should be. Now, you know, ChatGPT doesn't understand the semantics of these, but it sees them in the text. And so it can key off of these. And if you ask it now, what is the answer? Well, it comes up with a max of each list, which is not quite right as you see according to the test, but is much closer to what you would want. So now we can go, and since we have these things in here, we can not only use them to key off and try and generate a good example initially, but we can loop back around and say, hey, let me give you some feedback. This fails on this input, right? Can you come up with a fix to this code that will come up with a better result? And then, yeah, it'll iterate around and it'll come up with the correct result or the desired result there. So I think this is a good example of it actually improving what you can do with the AI system as well. Now, one of the things that you might ask is, well, developers hate writing tests, right? They're like the worst, and I hate writing tests too. So, you know, do we really want to go and hand type in like what our inputs are and what the right outputs are, and we do a terrible job? So I'm going to refer back to a very fun paper that I really like called Liberating the Programmer with Probed Programming from Onward 2012, one of my favorites. I've always wanted to do this. So as you notice, I had a keyword defer there. And this is kind of fun because what it does is it allows me to just start running the code without actually filling in the function body at all. And so you can see I have calls to this method here. It has no implementation. And so what I'll do is I'll start, fire this up, and I'll run my video. I'll fire this up. It'll start running. And when it hits that bit of code, it'll pop open a window and say, I got this as the input. Can you give me the correct output? So we can type that in and let it go. And it'll run using that output. And it memoizes it, so it'll reuse it if it hits it with the same output. I get a different input, and I will tell it what the answer is. It'll continue running. And then at the end, it'll basically put all these input-output pairs into a list in a file that I can then integrate back in. So this is a chance for me to go and actually start thinking about writing code, not so much as a developer typing stuff into the application, but I'm sort of orchestrating like what's the high-level structure of the code. I'm going to start running it, start experimenting with it, start gathering basically these requirements, like I'm live requirement gathering, and I can then start feeding these back in a rich sort of multimodal way, examples, constraints, natural language, into this programming language that allows me to express them in a rich way, and that an AI coding agent can go and then consume and generate the code for me. So I become less of a really fast typist and more as sort of a curator of all of these input sources and trying to really build the logic of the application. So, I think this is really cool. So I want to, onward, what's next? Well, I think this is a real paradigm shift from thinking about programming languages as a bag of features that is used for me to type code into to accomplish something, and towards programming languages becoming a substrate for the entire development stack and the basis of communication between many, many parties, humans, automated tools, AI agents, and then you think even frameworks and sort of these microservice architectures, right? It's not about input, it's about communication and collaboration. The key insight, if you take away one thing from my approach, it was, simplify. I'm not trying to be clever and build new things. I'm just trying to focus on solving the particular problem at hand and really create a simple core to work with. And I think there are huge implications. Hopefully the couple of prototypes I showed you, like the goal isn't to build a whole new system, but just show the viability of this approach. But I think there are huge implications for the kind of work we do in building tools, in supporting developers, and driving how software is developed overall. And I'm going to say, even with this prototypes, like I've had to tell people, don't start building anything on this because we're still working on it and we'll yank the rug out from under you. I've had to push people back, but there's extensive industrial interest in this. There's like hit a real chord with a number of people who really want to get on board with this. So that takes me to some links and opportunities. There's our GitHub repo. It's not too exciting right now. It's just basically trying to take a bunch of prototype bits and start assembling it into something that we can go actually give to production developers and ask them, you can start building something on this and we're not going to yank the rug out from under you. And I have people in fintech, startups, big tech partners that are hungry to start using this. So if you see something in your research and you're like, I'd like to be a part of this, I'd like to work with some industrial partners, I'd love to talk to you about that because I have way more interest than I can support. I'm also going to do a quick plug. I just am starting as faculty at the University of Kentucky. Very excited to be moving back into academia. So I am looking for good grad students. If anybody has anybody who would like to work on this, I'd love to hear from them. And our department is also hiring again this year. I thought it was a great department to join, so I'd encourage you to take a look at it as well. All right, and I think that is what I've got. So I'm happy to take any questions now, offline, or if you think it's a terrible idea, you can yell at me too.
So we do have time for questions.
Thank you very much for your presentation. We saw a number of presentations this week in which the idea was presented of having some core language which has multiple front ends for programmers, users with different kind of background or different kind of experiences. For example, localized languages of the keynote this morning, but also maybe widgets in projectional editors. But in some sense, your language seems to be going in a different direction by having a particular concrete syntax that maybe different AI or experienced developers share. So do you think this idea is compatible with your motivation and the work that you're doing and could perhaps contribute?
Yes, I absolutely think so. So a funny story. So one of these industrial partners specifically, they came and talked to me. They were interested in the surface language, and I said, you don't want to start building something on that yet because it's going to change. And I mean, let's do a few prototypes. Let's experiment. I'd love to get your feedback, but I don't want you to take a dependency on that. But they did have another language internally that was actually a different front end, but it was compatible with the requirements to map nicely to that core IR. So we could actually take that, compile that to that core IR, and do the formal validation on their source language as well. So, I think there are two parts to this. One is, what are some of these anti-features? And I think that's an interesting thing from a language design standpoint. And if you want to have a language that does not have some of these, you can map this down to the core pretty well. And then I think the second part is, well, maybe I pick a different surface syntax because I'm targeting, rather than a full citizen developer audience, I'm targeting more of a, an enterprise developer to expert developer audience. And that's just, what kind of user set are you catering to? So I think at the end, yes, I think there are areas where they're compatible. Yeah, definitely.
Hi, Ed Nutting from ViperCore. I'm going to ask a sort of industrially motivated question, which is, languages like this could be very powerful, very useful. How do we, or what's your view on how they would capture the API to existing code bases in other languages?
So this is one of the areas that is really interesting. And I think the rise of microservices and clouds have done a great job. Because 10 years ago it was, well, look, Java has a huge code base and you'll never displace them. So what do? Well, people have started to move them not by rewriting those, but by putting, RESTful APIs in front of them and then communicating across those. So I think the ability here, the interest here is, tying into that ecosystem and leveraging, not trying to replace a huge legacy app, but fill in these gaps and then operate in this microservice space. If that answers your question, I don't know if I got a little astray. Okay. Okay, thank you.
And last question, sorry, Marco.
Oh,
Lucas,
no
over there. Thank you.
Yeah, thank you very much. Very interesting presentation. Yeah, definitely something I'd kind of been thinking about for a while is we have large language models for writing code that somebody should look into designing languages to work better with large language models, and this seems like you've gone and done that to some extent. I'm wondering, large language models, you need to train them on a ton of code in a particular language in order to actually get good performance. And obviously, if you're starting out with inventing a new language, you don't have a whole bunch of code on GitHub that you can train on. Have you given any thought to that, like how bootstrapping to?
Yeah, I mean, there's a couple things. Large language models are good at learning generally how things look. And the convenient thing for me is that Bosky looks an awful lot like TypeScript or C#. So even without any real training, it's able to look at it and say, oh, okay, you want something that has like link-like syntax and has TypeScript-like functions. I know what that should look like. So it's pretty good at generating that. And then on other stuff you can do, in the prompting, they're pretty good at fine-tuning a little bit with, a few shot training just to get it in the right mindset. But that has not, this is an open question, I think, and I think this is an open question in the larger scale. But for me, it hasn't been a big problem yet.
Okay. Yeah, that's what I was wondering if it was through few-shot learning. It is impressive how well LLMs can do it. Few-shot learning a new language, but
yeah,
that only gets you a certain.
Especially if it looks like something it's seen a lot of before, right?
All right, thank you. So, I don't know if you noticed the indoctrination going on here. We slowly moved from the normal no-code environment to the SMT solvers, and now we're getting to theorem provers, so just in case you haven't been watching. So, for the last talk, once the door settles down, we have Colin. So, please, go ahead.
All right, thank you. So I am Colin, not an imposter. This is some work I did with my student Sergey, who's back there. And I'm going to tell you about some of our thoughts on building an approach to trustworthy formal natural language specifications. And so I should start by admitting that there's a bit of a bracketing ambiguity in that title, because we are trying to write formal specifications in a natural language. But part of our approach to making this trustworthy, we need to really understand the language we're interpreting. And so we're working in a formalized fragment, although of course, to actually make that remotely practical and useful, broadly speaking, we need to pick some foundations that we can build on and extend over time. And so a lot of this is going to address sort of what choices we've made to do that. So as Alex was alluding to, we're doing this in the context of, for us, a proof assistant, right, which are now very powerful, widely explored, big successes like verified CompCert, SEL4, CertiCOS, and many other interesting systems. But all of these share this common serious limitation, which is what if you formalize the wrong spec, which we do from time to time. And there have been a number of cases both in academia and elsewhere. And this arises from what we were calling the specification gap. This isn't a term we came up with, but it's not super common in the literature either, which is the fact that there's a gap between what's in our heads or what's written on a piece of paper when we go to formalize these specifications and what actually we give to the proof assistant or related tools, because of course it's a human translation process and we make mistakes, right, even on easy cases. So if you want to convince a less technical user, or even a very technical user who's just not, say, a formal methods expert, you did the right thing here, how do you do that? You basically can't, unless you want to sit them down and teach them how to use a proof assistant. If you are a formal methods expert and you want to audit this, at best, in practice, there's rarely, sometimes there's careful notes about some particularly tricky corner case, but we generally don't take notes about our process. We just do it and then walk away, right? So if you want to audit this, that's hard because you basically need to sort of retranslate or reverse translate and compare one of the ends, right, which is potentially difficult. So ideally, we'd rather have a more automatically checked translation, and we'd have this in a form where we leave behind some evidence, some explanation of why, what is the reasoning behind saying this natural language is connected to this formal statement. And so our goals, broadly speaking, are we do want to write in this ambiguously parsed formal natural language. We want to make it easier to write some specifications. But our real goal is we want to extend the verification of properties we're already verifying by hand for good reasons, up through a form that we can communicate better with others. So something that we can explain more easily to non-technical users to a large degree. To make this practical, of course, we do need to make this modular, right? How many of us have made up a new word while we're writing a paper? Most of us have done it, right? So we would like to be able to say like, oh, I made up a new word and ship that definition in some meaningful way. And I want to emphasize that a non-goal is totally replacing the formal machinery. So especially in proof assistance, you often really need to worry about things like, oh, I need to go generalize my induction hypothesis. Oh, I need to be careful about the shape of this goal when I do induction to get a hypothesis you can use. We can't remove that level, and that's not our goal. Our goal is to be able to extend the connection from these proof assistants that we've spent a lot of time worrying about over the years. How do we trust these proof assistants? How do we trust their proofs? And extend that up into less formal specifications. So this idea of writing formal specs in natural language is certainly not a new idea, right? There's been people working on this off and on since the 70s, and it's coming back around again with auto-formalization and LLMs. You know, there are some notable waypoints on this, right? Like using the proposal to replace first-order logic with English. There was a great FSE 99 paper from the Attempto-controlled English project on that. We've had pseudo-English programming languages, COBOL, AppleScript, some of these other things. So it's reasonable to ask, like, what are we going to do differently? What's the difference? So there's a few things. One, we are doing this inside an existing proof assistant. This is not a bolt-on. This is not a preprocessor. This is not a separate tool that you then have to maintain sort of in tandem in delicate ways. So this is really part of a tool that people already use for verification. There's no, oh, you have to switch to this tool. There's no LLMs. We can talk about that later, but they're big statistical distributions and don't leave evidence. So we're supplementing, not supplanting, the advanced interfaces that are already in these proof assistants. But one of the big things is we want to actively embrace the knowledge of the linguistics community, which has spent many decades carefully studying this relationship between natural language and formal language. And so we want to be able to take advantage of that. The main approach we have to taking advantage of that is by building on this thing called categorical grammars, right? So this is a large family of techniques. I have bumped into a few people who have heard this term before and they think it's just one thing, but it's actually a very large family tree of systems rooted in theoretical formal linguistics and substructural logic, which makes for a nice bridge to people working with proof assistants. So there's a long history here that I'm not going to talk about at all, going through famous linguists and logicians. They've been used to give extensive, thorough treatments of wide-ranging grammatical phenomena in English, German, Hindi, Japanese, Arabic, French, and there's more in the paper. And this is also something I have to acknowledge is not totally unknown to PL people. So there are people here, even at this conference, who have worked with categorical grammars, but mostly going in one direction, which is taking PL concepts and trying to make it easier to do linguistics better, more easily, which is very cool, and I love that work. But we are going the other direction. We are trying to raid this treasure chest of linguistic knowledge and use it to make better proof assistants, right? So the core idea here, what is a categorical grammar, what is it doing, and this is going to sound weird when I say it, we're making a type system for words, right? So bear with me. So the basic idea is we have some sophisticated way of describing the role of a word or a sentence fragment in a sentence, and the combination of those grammatical types, which we'll call categories, and certain logical rules for combining sentence fragments, get us to basically being able to parse a sentence. And one of the things that's nice about this is these categorical grammars in particular are what are called lexicalized grammars, which means not all but almost all of the knowledge for different grammatical constructs actually is localized to what's the grammatical type we give this word. Which means that if we want to support new grammatical abstractions or new grammatical constructions, new patterns of specifications, we just add new word entries. We don't have to revisit things. We don't have to go digging deep in some very funky, carefully crafted context-free grammar. we just add, here's a new way to use this word. And usually, we can read that directly out of the linguistics literature, which is what we've been doing so far. So parsing now becomes proof search, and I'll show you on the next slide in a second. It's proof search in a particular kind of substructural logic. And this extends really naturally to what's called semantic parsing, which is parsing not just the sentence structure grammatically, but parsing out what is the meaning of this by building up the meaning of the whole sentence from meanings of smaller pieces, which actually goes under this banner of the principle of compositionality in linguistics, which is kind of like their analog of what we do when we talk about denotational semantics. So here's the basics. I'll just cover a couple small rules. So the most common rule, the one people tend to start with, is this one. It's called rightwards application. And so what this rule is saying is if we have these two sentence fragments, gamma and delta, they're each some non-empty sequence of words, but we don't know how big they are. We don't care, actually. If we can give gamma, that first fragment, this grammatical type B/A, so B and A are some other grammatical categories, but the important part is that slash. This is like a directed function type. It's saying, if you give me an A to the right, that's why this is rightward application, if you give me an A to the right, you'll get a B. And so that's essentially what this rule says. If you have something on the left that would be a B, but it's looking to its right for an A, and then that delta, if we see that actually that is an A, and it's on the right, we can put them together and we have a B. And not only that, but we compose the semantics as well. So actually the fact that that first fragment has this category B/A tells us its semantics are literally a function from the representation of A's to the representation of B's. So there's a very tight correspondence here between the grammatical types we're seeing and the semantics in a type lambda calculus. So there's a leftward version of this too, because most languages have things that modify what comes after them or before them, which may be left or may be right, depending on what language you're talking about. There is this tight connection between the grammatical categories and the semantics. So the grammatical category literally says this is the type in some type lambda calculus you're using to represent meaning. And if you're worried about, can this really capture all of natural language? Is this really extensible? So these basic rules, if you kind of squint, you can see they're kind of like pieces of CYK parsing. And so these and a couple others get you context-free grammars pretty easily. Most linguists think we need a little bit more than that, and these are more than up to the task. So there are other rules that I'm not going to talk about that can get you well past context-free. So we use this by searching for these derivations, right? So if we want to try to understand the sentence 3 is even, we can do this by just breaking it down into subsequences and trying to put them back together, and we might find a derivation like this one. So if we split off 3 by itself first, we might go look at this circled bit here, where I've assumed in our database of knowledge about individual words, we have an entry that says 3 is a noun phrase and its semantics are 3, which I'm pretty sure is what 3 means. We split the other half down again, and then we have to deal with is and even. So we'll do even because that's a little simpler. So even, we assume we have an entry that says, oh, it's an adjective, and its meaning is the mathematical predicate, even. And then we get to is. And this is where we start to get a little bit of a hint of why these grammatical categories can actually cover a wide range of different uses. So this type, this category for is, this NP/S/ADJ for adjective, it says that first is will look to its right for an adjective, and that's bound with lambda p in the semantics. Then it will look to its left for a noun phrase, which will be the subject, and that's bound with the lambda x. And then the semantics after those two things are supplied is basically the truth condition of is this predicate we bound true of the subject we bound, right? So if we take this and we plug these in and we do the function applications that those rules tell us to, and beta reduce, we get that 3 is even is a sentence, and it means the proposition even 3, which many of you have probably noticed is not actually true, but that's okay because sometimes we try to say things that are not actually true and we want to find out that they're not true. So this is not a proof that 3 is even. This is a proof that that English is interpretable as that formal claim, right? The other thing that's useful here is this structure, right? This is a proof. in a particular logic. And so our prototype actually builds this structure, right? And this is why we are calling these trustworthy, because this is something that gets persisted into, oh, you compiled the program, you used this spec in the tool. There's evidence of this remaining in the compiled output from the proof assistant that someone could go look at later as a certificate. So we took this and we crammed it into lean type classes. Somebody was talking the other day about abusing type classes in Rust. Well, we did bad. So recall that type classes are, in general, this way of getting the compiler to provide implicit arguments, to come up with certain arguments for you. It draws heavily on logic programming, right? Prolog, Datalog. It's quite popular in Haskell, Scala, although probably some Haskellers in the crowd have done worse than we did. So the core idea here is we've written something that's effectively this, and I think that might have come out smaller than anticipated, so I apologize to you in the back. I was one of the people who had to reformat their slides, and it seems to have not worked great. So the core idea is we've implemented the moral equivalent of this function spec that takes a list of strings, basically a sequence of words, and then in brackets, there is this declaration that we want the compiler to provide a synth, that sequence of words, sentence instance. So come up with evidence that this sequence of words is a sentence. So when we ask, when we write code like spec 3 is even, lean will go off and it has some algorithms to try to figure out, okay, can I find something that shows synth 3 is even s, that this parses as a sentence, where that synth sequence of words and some category corresponds to just the left half of that judgment we were seeing on the previous slide. So it's just saying this sentence fragment has this grammatical type. And then the semantics just become a member of the type class. So if you can see, or if you can't, the definition of that function, the body is just returning the semantics member, the sem member of whatever the compiler finds for us. So each rule then becomes an instance for synth, and this part is not, the fact that we're doing this in lean and doing this with categorical grammars is the novel part, but the rest of this is sort of how type classes work. So we can write that write application rule by giving an instance that says for any gamma delta AB, if you have gamma that has category B/A, delta has an A, if they're in the right order, you get a B, and then the semantics is function application. So lean searches through possible ways to combine this instance and all the others to find something of type synth 3 is even s. And then of course, you can imagine writing sentences as lists of Unicode strings everywhere is kind of annoying, so there's a macro so we don't have to do that all the time. So what does this look like? Basically, whoops. We'll see if that actually, there we go. Nope. All right, it has tried to disappear from the screen. All right, the one thing that I did not test on multiple monitors, of course, will fail. All right, so we'll come back to that at the end when I nix the slideshow. So what was supposed to happen was you're supposed to see that it was pretty fast. You'll see later, right? And part of making it fast is part of the work involved here, and this relies on a couple things. One is specific implementation choices that Lean made. So Lean actually went back and said, well, you know what, this is literally logic programming, these type class things. We're gonna bust out classic Prolog optimizations, like we're gonna memoize everything when we search for these type class instantiations. And so then the other part of that was us rating some 1980s Prolog optimizations, like difference lists and interning things as numbers, because of course, looking a number up in a memoization table is a lot faster than looking up lists of Unicode strings. But with a couple of these tricks, the thing actually ends up pretty responsive, and I will show you in a minute. So we evaluated this. We grabbed a few specifications from Verified Functional Algorithms. This is one of the Software Foundations books. Focusing on just the early chapters for now. We tried to write English as close as possible to the descriptions of basically proof exercises from the textbook as close as we could get. And in places where we deviated, we noted why. So in a couple cases, the spec was actually ambiguous. We made it a little more explicit. In a couple cases, there are limits to our grammar coverage. We have not had time to encode all of the thousands of words in the English language yet. So I know, right? I'm being lazy. And so we ended up translating this range of specifications. So most of these are quite similar, if not exactly the same as the original. There were a couple where we had to propose some English because the book actually just said, prove this, and they didn't really say what it was. So we filled in those details. And one of the things that's interesting here is almost all of these, the translation we got out of this prototype is alpha equivalent to the exact thing the textbook hand wrote and said, prove this. So that may be less true as we go on and tackle more and more sophisticated things, but it was true for us so far, largely true. These translate in a range of times from a little over a second to a little over 7 seconds, depending on the linguistic structure of the specification, not the length of the string. And there's, if you look closely, row 8 has an asterisk, because even though I can construct the type class instance by hand, Lean does not find, hey, there's a dictionary entry for this word, is basically the step that does not resolve, but it doesn't resolve on my computer. And so this was in the submission, and this was in the camera ready. And then a few weeks after the camera ready, we have a new student, Chris, who started a few weeks ago, and he says it works on his computer. So there's a little bit of cross-platform questions happening here, so we'll have to dig into that a little bit more. Along the way, we found some interesting stuff from the linguistics side. So there's one spec we didn't translate, which if you pay attention to really what it's doing, it's not talking about the mathematical property. It's talking about the syntax of how you would write the mathematical property. So I don't know if you can read it in the back there. It says, multisets in a nested union can be swapped. So think if you know what that means, and how sure are you? So it actually means this. It means the union of A and the union of B and C is equivalent to if you swap something in the nested union and the thing in the non-nested union. So this is interesting because the whole notion of nested union, that is a very syntactic notion, right? This is talking about the syntactic structure of how you would formally express this in logic, not about the mathematical property. So we didn't translate this. We could have made something work, by hacking along, but we want to do a deeper dive into what does this look like more broadly. We expect we're probably going to see more of this as we keep going in both proof assistance and other broader mathematical literature. Also, it's slightly vague because maybe it was talking about swapping B and C on the left there. The other thing that's interesting is we ran into some type theoretic puzzles as well. So I sort of hinted earlier that there's a function from these grammatical categories to a Lean type. And of course, we have implemented that function in Lean. And the thing that's difficult here is that once you start dealing with talking about things in multiple universes at once, we run into problems because even though all of our machinery is universe polymorphic, so you can kind of shift it up and down in this infinite hierarchy of universes and these type theories, it doesn't really deal well right now with the fact that some things are up here and other things are down here. Like if you say every BST, that's actually 3 quantifiers, not 1, because it's actually saying for every key type and every value type and every tree of that previously quantified key value type choice. So there's a lot of interesting stuff going on there that we're going to dig into in the future. So wrapping up, we can support natural language specifications in current proof assistance with evidence because we construct it during parsing with good extensible linguistic coverage. I didn't get into like the linguistics of how do we treat certain language constructs, but everything we've done is literally read directly out of the linguistics literature. We have not had to be creative with anything yet. So this is also extensible both because of the formal foundations we picked and because we were doing type classes. So if you make up your new word in your next paper, you can just add a type class instance and ship it off, right? And that word will work. And then we found some interesting stuff for future work that I just talked about. There's more details and nuances in the paper, but now that we're done, let me actually get this on the screen. Apparently, it does not let you drag it onto the other screen if something is full screen. So this is the intended usage model. So here we have the manually proven spec, basically the one that we read out of the textbook and somebody proved. And then this is basically what we've implemented. So we have dspec, and then in these brackets, sort is a sorting permuting algorithm. And Lean has figured out, hey, that parses. That is actually a proposition. And so if we hop in here, we can see that it's asking us to prove that the original spec implies this English spec. And this is building that connection between formal and informal that we were talking about. And if we step along, we can see, oh, actually, yes, there is semantics there. So simplifying once unfolds that definition, and we get a formula. Don't worry about the details. And we can keep going, and the rest is proving a formula that, in this case, turns out to be pretty easy to prove. This is about as far away as we got from the original textbook specification. And it's mostly because that use of a in the middle of a sentence turns into an existential quantifier, because you're saying something is a, as in there exists a thing with this property. And then we just sort of rearrange some ands and ors there. And the thing that I wanted to show you, since I said, oh, you'll see that it's fast. So there's yellow stuff because it's recomputing. And this is one of our slower examples, but it's done now. So it reparsed it. And that's it. Thanks.
All right, we have questions already. Nice.
Very interesting talk, thank you. So I was wondering if you also thought about the reverse mapping of having existing specifications and generating natural language descriptions.
Yeah, so this is a really good question that we wrote quite a bit about in response to the reviewers asking about the same thing. And it turns out the reverse direction in theory works, because in theory you can just unify everything, right? But in practice it's actually extremely difficult, because without the simplification step, after I parsed that specification, you basically get a giant pile of function applications, right? But that's not how people actually write their specs. People write basically the normalized form. So going the other direction basically requires a lot of guesswork on like how, what series of reductions produce this, undo them, and then unify backwards with those rules. And that's why the people who have worked on using this technique to go the reverse direction support very restrictive fragments like and or, and not even quantifiers. So that reverse direction is legitimately theoretically harder.
So really interesting stuff. You mentioned ambiguity, and you said you were very careful with saying that this is a possible meaning of 3 is even.
Yes. So good question. So yeah, so we didn't run into any problems with that in this case. So the lexicon's still relatively small, so there's still plenty of room for that to happen. Our stance on that is basically, if it's ambiguous, is that really how you want to word your spec? And so the Lean prototype doesn't do this. It doesn't tell you, hey, I have multiple parses for this. We had an earlier Calc prototype where this was possible. Calc type class machinery has a feature where it can warn you, hey, I found multiple derivations of this, and treat that as an error. So that's something you could, in principle, add to Lean. It would base some engineering work, but it's not. It exists in Calc, so clearly it's possible.
I wanted to say this is a really interesting talk. I just had a quick question.
Sure.
Have you tried, so MATLAB 4 has a bunch of formalized undergraduate theorems with formalized statements.
Yep.
Would you think, have you tried perhaps translating some of the statements you might find in an undergraduate math textbook into and comparing them with what?
So we haven't tried that, but here's the first thing I know we would run into with that, and that is the heavy use of type classes in MATLAB itself. So that is actually one other thing where the use of these ideas in linguistics so far has not gone that direction, because why would you have type classes if you're just writing lambda terms on paper, right? So this is not a thing they worry about, but it is a thing we would have to adapt. And so I have some thoughts on that, but nothing is implemented.
Thanks, very interesting work. I was wondering about error messages. So what happens if you write sort is a 3, for example?
You get one of several possible outcomes. One possibility is it just says, oh, there's literally no way to do this. Sometimes it proves exhaustively this is not correct. It doesn't give you any guidance on fixing it, because it's just type class machinery. So there's room. One thing I have thought about but have not seriously investigated yet is there is a way to do plugins for lean. So maybe intercepting for this particular type class and trying to do something clever there would be useful. The other possibility is it just says, couldn't do it because we ran out of time. So something that you'll see here is I cranked the number of things it will try for the type class machinery up quite a bit. I think these are normally set to like 400 or something. Because it's not intended to be used for this kind of search space, really. So this is why I joke about doing terrible things with type classes, because it's not really meant for this. But, I mean, the implementation's really robust. So it works pretty well, actually.
All right. Thank you. I don't want to keep anyone from Portuguese tarts and tea, so we'll finish. Thank you very much. And, yeah, thanks, Colin.
All right, good afternoon. Welcome to our first session of Onward Essays. I'm honored to be able to chair it today, particularly since this is my first session of Onward Essays as well. We have two talks this afternoon. Our first is from Advait Sarkar from Microsoft Research. And he's talking on a subject that I'm very interested in, as I've been an advocate of text-based programming modalities for end users for quite a while. And of course, the advent of large language models makes us wonder whether or not we're going to continue to do that. So today, his talk will be on whether or not code will remain a relevant user interface for end user programming with generative AI.
Thanks everyone for coming to the last session of the day, and hope you've rejuvenated a little bit with some Pastel de Nata. Actually, I didn't spot any. Maybe there weren't. Maybe there was some simulacra of Pastel de Nata. My name is Advait Sarkar. I'm a researcher at Cambridge, at Microsoft Research Cambridge, and a lecturer at the University of Cambridge and UCL. My background is quite different. This is my first ever Splash, so I'm quite excited to be here. There's a new community, new audience. My background is in human-computer interaction research primarily, so most often you'll find me at CHI or the end-user programming conferences like VLHCC, but I'm excited to be here at Splash with many of my colleagues have roundly endorsed for multiple years. So I'm curious to see what all the fuss is about. There are some links down there. If you want to yell at me on the internet or just say hello, please go ahead and find me. So let's get started with my talk, which is about will code remain a relevant user interface for end-user programming with generative AI models? And this is quite a long title because I'm kind of bracketing a lot of words so that I'm just to be a bit more precise about my claim. But if we're going to be a bit loose about it, get the essence of it, what am I asking? I'm asking, is code going to still matter for end-user programmers in a world with generative AI, right? So what is end-user programming? If you've not come across this concept of end-user programming before, it's similar to the idea of citizens that we heard earlier today. An end-user programmer, quite simply, is somebody who writes programs for their own use. They're not professional developers. So somebody's writing a spreadsheet formula for their own use, somebody who is writing a bit of a script to help them with an office task, somebody who's doing budgeting, data analysis at home, a scientist who is working on some sort of code to analyze their experimental data. These are all people who are not producing software for consumption by others. They are consuming the code themselves, so they're end-user programmers. Now, one nuance that's not always the case for end-user programmers, but it's typically the case, is that they typically don't have programming expertise. So they've typically not taken any courses in programming. They've not obviously typically got a background in computer science. Whatever they know about programming, they've maybe cobbled together expertise by trial and error, by learning from colleagues, by going on some short courses maybe that they're offered on the job. So they're not trained to think like computer science, they're not trained in programming. And this causes a lot of challenges because then they try to program, they try to use the apparatus of professional programmers to get their jobs done. And so end-user programming research, by and large, aims to bridge these gaps in expertise. And so the aim of end-user programming research, by and large, can be described as we want to improve the ability of non-experts, end-user programmers to use formal systems. And by formal systems, basically I mean code. There are other elements of the system that might be also formal, but they might be graphical and visual. So for instance, in the spreadsheet, the grid is an essential part of the language, but it's not necessarily, you wouldn't describe the grid as code. But effectively, you can just replace formal systems with code, and you'll get what I mean. And there's three approaches to help bridging the gap. One is to help users learn. So this is where there's an overlap between computer science education research, so developing new tutorials and so on. Another way is to help reduce the expertise requirements. So you have a visual language like Scratch. Scratch has features that help people avoid type errors, so you can't have a block of a certain shape going into a hole of a different shape. And finally, you can try and reduce the programming requirements. And what I mean by this is reduce the need for people to actually write literal code statements, so things like programming by example, programming by demonstration, don't necessarily eliminate programming requirements, but they aim to reduce how much code you need to write, how often you need to write it, and so on. So this is the status quo for end-user programming research. This is what most of the papers at a conference like VII HCC will be about, for instance, right? Now, what does generative AI do to this picture, right? And by generative AI, it's a very sort of muddy term. In this paper, I'm just talking about end-user tools, that's stuff that people actually use, not something abstract like the transformer algorithm or whatever, and applied to programming, so not ChatGPT for text generation, but talking about it in the programming context, based on generative deep learning, so the sort of current generation of AI technologies. And this is interesting because because there's, unless you've sort of been really focused on something that's not generative AI, you'd be aware of a significant leap in capabilities, as measured by benchmarks as well as by practical use in a number of categories of programming. So authoring code that does some task based on a natural language prompt, debugging some code that has an error in it, reusing code and reappropriating some code in a different code base. All of these kinds of tasks are tasks that with generative AI has seen a significant leap in sort of benchmark capabilities in the last couple of years, right? And so what is this going to do, or what might this do to end-user programmers? So I'm going to posit this hypothesis that we'll see a sort of a shift, a leap, which would be a radical widening in the scope and capability of end-user programming due to generative AI. And you can think of it as 3 dimensions. So end-user programming will be applied more deeply to existing tasks. So people are currently maybe writing formulas and spreadsheets to do certain simple things like sums and averages and so on. And maybe we'll be seeing formulas to do much more sophisticated things in the future. I mean, some people write those very complicated formulas, but more people might. There's an extensification, so people might apply end-user programming in more tasks that they weren't applying it before. So, for instance, automating things across multiple applications. And then acceleration. So people will apply end-user programming more frequently across all their tasks. And this is especially going to be the case. It's especially going to be the case that that the cost of applying end-user programming is going to go down because it costs very little to just try to automate something in comparison to what it's been. So I'm not going to. So what evidence do I have that any of this is going to happen? I don't have any evidence, right? This is speculation based on sort of nascent trends. The rest of my talk is going to try and analyze, well, okay, in a world where people are doing a lot of end-user programming and primarily doing it using generative AI, what remains the role for formal systems, for end-user programmers, right? What could be still the value proposition for engaging with code, writing it, reading it, and so on directly, as opposed to through a large language model, for instance, right? So I just talked about this slightly. Will code remain a relevant user interface for end-user programming if people can code with natural language? Right. So here are some reasons why code might still matter. And I will say that I'm not the only person to have asked or tried to answer this question. There's like many viewpoints here. This is my perspective, which comes from the research that I've been doing with my team over the last 10 years, studying particularly end users doing data analysis tasks in spreadsheets. So that's the kind of small world in which I'm located and how the world looks from where we're standing. Okay, so AI makes mistakes, right? It can't automate everything. And if AI makes mistakes, what better way to understand and rectify those mistakes than to learn how to code, right? So this is a good reason that code might still matter, or learning to code and engage with code might still matter for end-user programmers. However, we might say that this is a problem that sort of steadily diminishes over time. As generative AI improves, it might be able to do things much more accurately than it can today. Indeed, that has been the trend. But a counter-argument to that is, as AI improves, the demand for what we want to make it do also improves, right? So there's a kind of, this is known in economics as as Jevons paradox, or a rebound effect, where basically, for instance, if you think there's a traffic, if there's a road that's like jammed with traffic, and you think widening the road is going to help with the traffic jam, you widen the road and all that does is increase demand for traveling between the two places, and so you end up with, you know, the same kind of latency or whatever on the road as you started off with. And so the same thing is likely to happen. Indeed, we see this with many end-user programming scenarios. As soon as a capability improves, the demand for what you want to try to do with it also improves along with it. So this issue of limited abilities may not ever go away, even if generative AI continues improving. Right. Yes. So the second reason is that code offers really fine-grained and direct steering of things. So for instance, if you don't want to use a particular API because it's very slow or it's deprecated or it's insecure, if you're writing code, you just don't use that API. But if you're writing code via a large language model, you have to try and prompt the large language model not to use the API. It may not honor your prompt and so on, right? So there is a sort of indirectness to coding that we don't, to using LLMs that you don't have when you're using code directly. But you can give control to end users or increased levels of control without also interacting with directly with code. So interacting using faceted natural language, for instance, which is mentioned in the paper, is one alternative. And I don't think this is a solved problem. I think this is an important area for future research. A third reason code might still matter is agency. So agency is related to control. Agency is like the perception that you are having an effect on things. It's a sort of psychological construct. It's the feeling of being in control, of being able to effect change. And numerous studies have shown that when people have a perception of agency, they have an overall better experience using a computer and carrying out their tasks, right? And also, coding gives people agency, so also borne out in studies. But the other thing is that agency is multi-level and it can be easily manipulated. So for instance, like a notorious example are these placebo traffic light buttons where when you cross the street, you press the button to change the light. And in many cases, these buttons don't actually do anything. The light is just on a timer, but it's there to give people the feeling that they're in control of something. So you can manipulate agency, and it's also multi-level, right? So if a user can write code that they couldn't without an LLM, if they find that over the long term they can actually get a lot of their tasks done, that might give them a sense of overall agency, even if in one particular task they feel like they don't have fine-grained control over the output of what's happening. So it's a multi-level phenomenon. Okay. So another reason is that is called awareness of the possible. So learning to code gives you a language with which to think about what can be automated, how to achieve something, right? So for end user programmers, think about somebody who's trying to automate an office workflow. It must even occur to them in the first place that this workflow can be something that is automated, right? And this is something that you often, informally you might have this experience of seeing people do something manually that you know can be automated, but they don't know it can be automated. The reason you know it can be automated is that you have this language of thought about the possibility of what can be done, and coding gives people that possibility. It's no use having a large language model that can write code for you if you don't even realize that you can solve your problem with code in the first place, right? Again, you can try and get this without code. So there's research into sort of proactive systems, early systems on programming by demonstration, and mixed initiative systems try to help people identify opportunities. So this is also something you can get without code, and I think also another area of research. So I'm not necessarily sure that this is, for instance, each of these is like an unassailable bastion that will mean that code is always going to be important for end-user programmers. Similarly, explanation, interpretation, and debugging code can be useful. So for instance, take something as simple as an off by one error. It might be really difficult to diagnose that you have an off by one error unless you literally look at the code. So code can be useful, and formal systems offer a very predictable route towards debugging and fixing errors. The problem is that it's already really challenging for end-user programmers to debug code, right? There's so much research on making program visualizations, making debugging aids, and as code becomes more complex, as the generated code becomes more complex, this problem that debugging is a challenge will get even worse. So I'm not sure that relying on code to be a direct interaction with code as a debugging support is necessarily a long-term sort of effective strategy. Another reason is that code might still be useful is trust. So when somebody writes equals sum in a formula in a spreadsheet, they trust that the output that they're getting is a sum because they trust the named entity of sum has been implemented correctly by a responsible third party or by a responsible party, in this case Microsoft, right? And so being able to directly kind of correlate names and identifiers with verifiable procedures has its own value. There's a strong value proposition there. And I'm not sure this can be entirely supplanted with large language models, because you can ask large language models to explain code in naturalistic language, but there's always this error of hallucinations. This possibility of hallucinations. I think it may be possible to constrain explanations to refer to trusted and verifiable procedures. And this is, I think, an interesting research area that would require collaboration from programming languages researchers, design researchers, and end-user programming research to sort of tease out, machine learning research to kind of tease out how do we constrain a large language model's explanations to provably refer to verifiable procedures. Sorry. So this final meta-level observation is that in this view, which we've noticed in our studies of people who use Copilot and similar tools, is that in this view, code isn't going away. It just looks different. It's the prompting language that it takes the place of code in this new world, right? Because prompting is hard to learn. It's kind of quite specific sort of tricks and craft practices required to coax an LLM to do what you want it to do. So there's actually quite a lot of expertise and sort of formality there as well. But this characterization that it's just one level of abstraction higher than code, it isn't satisfactory to my mind. It's not a satisfactory characterization of what is going on here. Because I think you can't actually deny that there's a huge increase in the flexibility of the expressions in prompting language in comparison to a formal system like a programming language. And it's not clear whether, as generative models get better, and what I mean by get better is made clearer in the paper, whether this prompt engineering will remain a form of skilled craft practice that is distinct from ordinary communication skills, or whether we'll have generative models that reach a point where they can interpret sort of truly natural language at human proficiency. But a counterpoint to this is that the whole imprecision of natural language, particularly when it comes to mathematics, philosophy, logic, and science, the imprecision of natural language has long been seen as a drawback of natural language, right? Since sort of probably the 1500s, people have been trying to make sort of perfect natural languages, artificial languages in which you can only speak logically correct truths and so on, right? And the program of the most sort of recent iteration, the 20th century program of analytic philosophy, which was born out of such concerns, eventually gave rise to our modern programming languages. So it is interesting to see that generative AI is bringing us back full circle to natural language. So what I think is more likely is that rather than prompt engineering remaining like programming, but at a high level of abstraction, we'll see the application of language formality for, say, precision or brevity in future systems. We'll see it become a bit more social and discretionary. So what I mean by that is that language for instructing generative models may develop much like a scientific or like a legal language has developed, right? So if you think about, these languages are ways for scientists and lawyers to develop, to communicate more effectively. They're extremely structured, although they have quite a lot of flexibility also. They have a lot of specialist terminology in them. But these languages have developed kind of organically and through sort of power relations that are enacted by individuals and groups and institutions. And I think a similar way of development of prompting languages is going to be what happens. So what are the implications for end-user programming research, right? I have sort of a set of implications in the paper, but I'm only going to talk about 4 or 5 in detail. So the first is this issue of learning to fish that people ask in the end-user programming community. So if you've not come across this before, there's a parable of the man who is being taught to fish or being given a fish, right? And the parable goes, give a man a fish and you feed him for a day, teach a man to fish and you feed him for a lifetime. So the moral of the story, the implication is that learning how to make somebody self-sufficient is better because then they can always kind of satisfy their own needs. And the question with generative AI is, does it still matter? Oh, sorry, that is too early. Does it still matter for this man if he can get a fish whenever he wants, basically, right? Does it matter that he doesn't know how to fish for himself if whenever he asks for a fish, he gets one, right? That's the kind of position that we might be in. And while code still has these benefits, I think we might have a more nuanced analysis of what actually are the trade-offs for people to learn coding in the end-user programming scenarios. And I think a really good, because for end-user programmers, the task comes first. They're not trying to write code because they're interested in making a beautiful reusable program. They're just trying to do their budget or whatever, automate their workflow. So the task always comes first. They're not interested in programming or learning how to program, except for some categories of end-user programs. But this is generally the case, right? And I think one of the really interesting papers of recent years has been written by Pothurst and others called The Dilemma of the Direct Answer. And they talk about this tendency in search engines. Rather than giving people a list of result pages, they try to answer the question directly, just by providing a paragraph of answer of what the question you asked is. And so Pothurst do a really nice analysis of the trade-offs, both on the human side as well as the system side. Like, what are the benefits of being able to read multiple pages and come up with your own answer, even though that takes more time and so on. And I think a similar kind of trade-off is at play for end-user programmers here. The second implication, I don't know how much of a concern this is in this community, but it's a big concern in the research communities that I told you about earlier. There's this pattern of publications which has been called Bertology, where people basically try to publish a paper where the whole point of it is, can a large language model do X? We made a benchmark to see whether a large language model can do this task. And we found that yes, it can, or no, it can't, right? So this kind of Bertology is a really common pattern of paper publication. And I don't think it's very helpful because firstly, it puts researchers in a passive stance. It sort of makes us not the people who are actually building these things. We're kind of probing it from the outside like a black box. And so it's kind of, exciting to even know whether this black box can do something or not, right? So this is a little bit ranty, and you might disagree with me on this, but I don't think this is very productive. And the other reason it's not very productive is that it's very quickly sort of outdated as well, right? This is not an enduring contribution that can a large language model do something, yes or no? Well, maybe 6 months down the line, the answer is yes, or maybe still no. I don't know. It's hard to justify that as an enduring contribution. What I do think we need is standards of rigor for prompt development. So people are already starting to say, so I think large language models are powerful, and we should be using them in our research, but we should be trying to answer more interesting research questions. And what we need is sort of more reproducibility. So people are already starting to publish in appendices what their prompts are and so on. But I think what we also need is more rigor for what it means to develop a prompt for a large language model, right? How many times do you try something? Is it trial and error? What kinds of patterns of language are you exploring? How many people are involved, and so on. And we have standards of rigor like this in other parts of qualitative research practices. So I think we need that here as well. So this one, end-user software customization, again, I'm taking this idea of substrate from Tomáš Petříček, and the idea of a programming substrate is easily illustrated in Microsoft Excel. So a substrate is a programming environment that allows you to make some changes to your software. So Excel has 3 at least substrates: the formula language, which is relatively easy to learn, but you can't actually change a lot. You can't do a lot within the formula language. You can do calculations within the grid. Contrast that to, say, VBA, right? With VBA, it's a little bit harder to learn, but the scope of change is greater. You can do more stuff. You can change more stuff in the interface with VBA. And then finally, a third substrate might be the C++ code base of desktop Excel itself, right? It's much harder to get into. It's much harder to make modifications in terms of the expertise required, but in terms of the scope of what you can change in Excel, it's pretty much arbitrary, right? So these are the different programming substrates. The ability of generative models to target different languages might mean that we find some sort of universal substrate. So Petříček has this hypothetical universal substrate that we can make any change, but it's also really easy to learn if you just want to make a small change, right? So I think this might be a potential application for generative AI, where you use the tool to achieve a task, but the tool sort of federates the task out to the appropriate substrate. So if you need to do something that can be solved using the formula language, it generates a formula. If you need something that requires VBA to solve, it generates VBA, and so on, right? But this makes a really interesting question about what is the status of the application. So the sort of theory of application in human-computer interaction, like why are apps what they are? Who's decided what a feature set of an application is, right? It's a negotiation between developers and communities. Maybe there's like some nucleus of activity or some file type or something that starts like, this is the kernel of what this application should be about, and then we add features as time goes on and as the community develops and as needs develop and so on, right? But if you can arbitrarily script your application, what does that mean? How do applications relate to each other when you can write scripts that automate workflows across applications? Do we still need that same relationship with developers who are trying to pack something with features if quite a lot of bespoke functionality can be generated on the fly by the end user? So this field of end user customization, software customization, which is a subfield of end user programming, I think is really going to be transformed. Because what applications might look like will be quite different depending on how much of the feature set can be kind of dynamically generated on the fly. Right. Okay, I'll skip over the cognitive dimensions point. The final point I want to make is this question of attention investment. So Blackwell's attention investment model is a sort of core part of end user programming theory. And it explains the behavior of programmers in deciding whether to automate something i.e. to write a script, or to try to do whatever they were going to do manually, right, by hand. So it's a cost-benefit analysis. People are likely to pursue automation if they think that, that they're going to save time and they're going to succeed at writing that program to do whatever it is. Right? But what happens to this model when the programming costs kind of tend to zero? So it doesn't cost anything to ask a large language model, or very little to ask a large language model to try and write a program to do something, right? So when these costs tend to zero, there might be other costs that dominate the automation decision rather than simply people's perceived cost of how much time is going to take me to write this code and whether, whether I'm going to do it correctly or not. So other things might dominate this. Some things like whether people feel that they have the agency to write this LLM prompt, or whether people trust that the LLM will do the right thing in a particular scenario. Right? Or maybe there will still be a cost-benefit trade-off in terms of attention, but these attention will be spent on new categories of activities that don't currently exist. So these are some other implications that I won't be able to talk about, but they are in the paper if you're interested. So just to conclude, so this generative shift moves the focus of end-user programming from helping people use formal systems and learn formal systems to new issues around control and explanation and agency. And I do think that this if something like this happens, it will affect many core theories and concepts of end-user programming, such as end-user software customization and attention investment. So I think it's worth anticipating some of these changes and trying to get ahead of the curve in terms of planning our research agendas for like what kinds of design interventions might help the end-user programmers of the future who are not necessarily engaging with code to the extent that they do today. All right, thank you very much.
Thank you for your talk. So one of the questions I had, some of the work that I've done has been in talking about, when you were starting, you talked about some of the needs that we may still have for code, why it's good. And so one of the things I've worked on is the code as a mechanism for explaining a procedure, how you do something, not only to the user themselves, but to others, to share knowledge, problem-solving knowledge. Can you give some thoughts about when we move into a prompting model and we start using generative AI, how that may evolve in this model?
Yeah, I mean, so using code as a way to communicate with others, right? Communicate your ideas, communicate your intent. Again, I think the aspect that perhaps touches upon that question most is the idea of how prompting languages will evolve in the future, right? So we've done multiple studies of multiple different kinds of systems that generate code from natural language descriptions of what the code is intended to do. And it's interesting that in each case, the end user programmers who are participating in our studies, they really want to see the natural language prompt that generated a formula. They want to keep it, they want to use it as a bit of documentation, and in some cases they want to use that instead of the formula that was generated, right? It's a really natural tendency to want to take the prompt and say this is actually a stand-in for the formula that was actually generated as a result, and use that as a communicative resource. So I think today there's two big challenges that sort of stop us from using prompts in that way. The first is that because of the way that large language models work, we have no guarantee that the prompt actually describes what the code does, or vice versa, right? So that is something that is going to take some research effort to figure out how can we not only sort of improve the likelihood that there's a consistency but also maybe even guarantee that there's a consistency. One approach that our team has explored is by taking the prompt language, the prompt that the user, and that was published at CHI earlier this year, taking the prompt that the user has written, taking the generated code that the system produces, and rewriting the prompt that the user wrote very slightly, very minimally as possible, so that it actually corresponds systematically to the code that was written, so that it becomes a useful thing. So that is one way in which one direction. The second thing is that the prompt, it has this weird dual characteristic. It's both an instruction to the system as well as an explanation of what the code does. And I think that is a tension that in some cases leads to, there are examples on a CHI paper from earlier this year, but it's a tension that sometimes leads to like a worst of both worlds scenario where you've got an instruction that's not very good at being an instruction, and it's not very good at being an explanation either. So I think if we can find a way to sort of either separate or unify the concerns of instruction and explanation in the prompting language, that would be really valuable. And it might be the case that something like that will evolve organically, much in the way that legal language or scientific language evolves. I don't really know. Those are the two kind of issues. Yeah. Oh, more questions.
Great talk, thank you. I was curious if you have observed in your research already if the new wave of possibilities have also created maybe a false sense of trust with end-user programmers, wherein since the computer said it, it must be correct, and as such they start using things a lot more confidently, which may result in much worse errors as people also trust larger chunks of code for more critical opportunities.
Yes, indeed. So over-reliance is an issue, and the way to solve that is to help people debug their code, identify bugs, and so those are the kinds of tools, like debugging tools for generated code that I think are really important to try and develop.
But then we are back at code, yeah.
That's right. That's right. So if you want to, when you say we're back at code, I think code is not disappearing entirely. The question is to what extent do we need the end user to read and engage with the code directly. And many of these debugging tools don't require necessarily the code. So the code might be represented in some other way. It might be represented as a sequence of examples, for instance. Which don't require direct engagement with that formal system. Yeah. But it's really important. Yeah, I agree.
Good ideas. Thank you.
Thank you. I feel that end-user programming could be related to computational thinking skills in some sense. If end-user programmers change behavior, do some computational thinking skills become irrelevant?
Well, that's really interesting. I think, so CT has always, certainly Jeanette Wing's sort of motivation for it has always been trying to distinguish computational thinking from programming, the act of engaging with code, so computational thinking in terms of understanding modularity and sort of strategies for problem solving. And I think that is kind of what I was trying to get at with the awareness of the possible bullet point. I don't think computational thinking skills, particularly the skills that for an end-user programmer make them realize that there's an opportunity to automate something and improve their workflow. I think that is the really key thing that remains important with large language models or any kind of technology that allows them to improve their use of computers. It's that conception, that first step of figuring out that something can be done. But in terms of solving a problem concretely by using some sort of decomposition strategy, I don't know. I don't know how important that is for end user programmers to get their tasks done. But often, actually, people will write code in extremely sort of poor and inefficient and redundant ways that show a real lack of computational thinking background or skills. But it doesn't really matter for end user programmers as long as it works and gets them like further along their task than they were without doing it. Yeah.
Thanks for your talk. I'm Arjun Goa at Northeastern. So you brought up sort of formal natural language as is used in scientific communication and law, and suggest that there may be an analogy between sort of high quality prompting skills and that. I guess I worry that. So firstly, if that were the case, that would be fine. Lawyers write well, even if it's hard for some of us to understand it. I worry that that isn't actually the case. For example, you can get away with some extremely vague, imprecise prompts. Like, for example, you can say, I don't know, write a function that removes the crap at the front of the URL, and it'll do the right thing. It'll strip off the HTTPS:// stuff. So any thoughts on that? Like, I worry that this may in fact lead to like a sort of stagnation where you can get away with sort of imprecise language for the problems that we already know how to solve, but to make that jump to new problems, additional technical skills are required.
Yeah, so I think if people can achieve what they need without having to also learn a very complicated prompting language, then people will gravitate towards it. It depends on what they get in return, right? So, for instance, in our experiments with restricted prompting languages, we've seen that this can give people a greater sense of control and predictability about when they can make the system do something and when they can't, right? That could be a valuable motivation for people to try and learn a more constrained language. It might also be a valuable motivation if it turns out that when you ask the large language model to explain a piece of code, the language that they get back looks very similar to the language that was used to generate that piece of code, right? So that is another motivation if you can ensure that round trip sort of property. So there are reasons why people might seek out developing these sort of prompt engineering techniques, but yeah, again, it's end users are kind of fickle, and they will do whatever is the sort of, to them, the easiest path to getting their job done. So it may or may not entail developing a prompting language. Yeah. Cool.
Let's thank our speaker one time.
Thank you. I didn't earn from people coming in for the next person's talk. Thank you guys anyway.
Okay, and so now we'll move on to our second talk this afternoon and our last talk of the day. And if this is anywhere near as entertaining as the paper, it will be a great way to motivate discussions at the reception next. So we have now James Noble and Robert Biddle, who are going to talk about programming language as language.
Yes, yeah, one of us, thank you for that introduction. If it comes down to saying, yeah, you actually have to be drunk to understand our talk, well, it'll make it more fun, I can guarantee that. I have to push the left button. What happens if we push the left button? What happens if you press the right button? If you press the right button, it'll switched off. I pressed the right button. Or was it the left button? No, I pressed the left button. Which button did you press? It's green. That's a good thing. Yeah, I'm holding this so I can present it to you. Languages, programming language. It is wonderful. It's almost like a large language model. You know, To quote Alan Perlis, if I ever ask for a programming language where I just need to say, where someone just wants to say what they want done, give them a lollipop. Alan Perlis, Epigrams on Programming. It was in SIGPlan Notices. Anyway, the most highly cited journal in programming languages and computer science. Anyway, as we know, language was invented by Noam Chomsky. Here you see a diagram of the cat sat on the mat. There are noun phrases, there are verb phrases, and prepositions, and determinants, and it's evening, and it's morning, and it's a new day.
And that is why children in primary school, the first thing they must do is learn to build push-down automata. And when their language recognizers begin to work, they start to infer the role of word order and token order in order to build up the trees and recognize the language.
Or as we say, they're just big Elizas. But anyway, different languages, though, different human languages have different word orders here. So for English, clearly, it is natural in the entire world to say the cat sat on the mat. And, you know, for how long was it? 500 years, the British Empire ruled the world with the insistence that anybody who thought the word order should be different was wrong. Or not just wrong, but actually evil. And many of our favorite television shows today are dedicated to this, to that particular view of the world. But in practice, of course, there are all kinds of languages that have all sorts of different word order. So subject, verb, object, cat, sat, mat, verb, subject, object, verb, object, subject. Where things get strange is, in fact, an awful lot of blood has been spilt and an awful lot of papers have been rejected from Poplar and apparently from Uppsala, although that doesn't seem to happen, at least not for these reasons anymore, over whether you wrote your program with the correct word order. So, for example, I think the first one is postscript or fourth. It's a subject, object, verb. It's, you know, cat, sat, or cat, mat, sat. We say, here's the string, and we're going to search for it, and then we say search at the end. The verb, the name of the procedure goes at the end. On the other hand, Java, of course, well, it's not English, but, you know, some string, index of M is Java, or Smalltalk, or APL have actually the same word order, which is subject, verb, object. Okay, and people are nodding, they probably speak languages that also have this word order, and clearly this is the best one, because that's basically object-oriented programming. What's left for the English? Well, clearly, oh no, it's not really English. Anyway, sorry. Functional languages. What I love about this is that C and OCaml have exactly the same word order. I know there's been a lot of blood spilt about which language is best, but in some ways, if you think about the organization of the program, programs are organized. They're modular programs, very much like VII's modular, and you know, they have the same verb order. And Haskell is out on the end. Haskell has this really weird word order where you go verb, object, subject. Because, let's think, I don't know, 8 curry I. Yeah, Haskell, you'd say 8 curry I. Because if you're going to curry your program, you can then apply the 8 curry bit to other people to find out whether they ate their curry or not. Okay?
And so the real story is that in object-oriented programming, the object is the subject. Oh, goodness me. Who did I ask about this?
I don't know, who do you want to ask about it?
I asked
Brad Cox?
No.
Yeah, Brad Cox is dead.
I asked the king of the Smalltalk world, in fact.
All right. Peter Deutsch.
And the story was...
Alan Kay.
Yes. And so I asked Alan Kay about this, and he said, "Who are you? Get out of my house." No, he said... what he said was that he wasn't thinking of the linguistics terms. He was thinking of biology. And when biologists study their specimens, they refer to the specimen as the object. and hence the biological model of programming was object-oriented. But we can move on from that.
Well, we're going to whether we can or not. If you're English, and if your first language is English, as it was for mine, you probably got to ignore most of this stuff unless you were forced to learn Latin or Finnish, particularly Finnish, Estonian, German, and many other languages.
The most important thing is that when you were forced to learn Latin, you learned little word games to remember all of these lists you had to know. And one of the most important you had to learn was this one for noun declensions. Never go down a volcano alone. Or as we say in New Zealand, never go down an active volcano. This turns out to be important advice.
Yeah. And just because even it's New Zealand and someone offers to take you down an active volcano, you know, say no to volcanoes. Right. Anyway, so in Latin, these things, for example, will be typically indicated by the endings of words. I believe there are languages, possibly Hungarian, you learn Hungarian with the lead of speech of some light, where it's actually the Finnish, probably the middle of the verb or the noun used might actually change depending on whether you are actually referring to the subject. You know, this is a chair, or genitive, my chair. I'm trying to think of this. There's not really an English version for that. Dative, the indirect object, or that chair in English. These kind of things typically happen via prepositions. Oh chair, that would be accusative. Oh chair, where did my USB stick go?
Oh chair is vocative.
Oh chair is vocative, yeah, I'm sorry, I meant vocative.
I learned Latin before you did.
You did, yes, well I never really learned Latin. Now, I know lots of us like the programming languages whose names begin with R, but, you know, really, it has reintroduced the need for precisely these kind of noun cases in our programming language. So if you want to talk about yourself, the object yourself, well, you write and self in Rust. Genitive things in Rust, you just say, well, it's some list, but it could be, well, in fact, that means my list. Dative, you've got to say, we've got to put this list in a box so it can be referenced. If I'm talking about a list that I've got a reference to, again, all those things. Vocative for their macros, I want you to print it, and I really don't care about how you do it, and all that functional, you know, the people who say, Rust is a functional language. Well, sure it is if you never write an exclamation mark. But go off and run one of your macros. So those things really correspond to parts of speech. And we can see them in programming languages in as much as we can the natural languages that do these kind of things. Not every natural language does. English does the same thing in different ways.
Well, I was just going to say, in written language, we separate them. But of course, in spoken language, a lot of those things, of this, at this, whatnot, could be regarded as annotations on the words themselves. Because when you break down on the basis of pauses, those often disappear. But in written language, we basically separate them.
Right. And once again, there are lots of language, even English. The written language, which was in the paper, which was written by ChatGPT-3 from the actually it was Otter.ai, from the transcript of the talk, a version of this we gave at Hopple a couple of years ago. Just anyway, never mind. A dark period in my life, but anyway. The written language and the spoken language differs. There are other languages, other human languages, where that happens, and even more to the case. And so the way that things are written and the way they appear don't necessarily correspond to the way you might say them or the way you might think about them. So, you know, there is, as we say, a European language, which has one word for tower, and the word for tower is le tour. And then it has a word for tourist, isn't it? I can't remember. Tour, la tour. Tour.
One might go on a tour to the tour.
Yeah. La tour. Other way, it's the other way round. Excellent. Good. Someone can speak French. Anyway, right. For English.
We're not saying that programming languages should have gender. No, that wasn't the point at all. No, just pay attention.
Well, who knows? I mean, you know, there was a lovely talk by Philippe Hammonds there, and quite possibly for languages, if you want to, you know, there is certainly a question raised by several of the talks. If you do really want to suit your language to the end-user programmer, perhaps it's to a student who speaks an indigenous language, how many of these features should you actually intentionally incorporate into your programming language? Because the catch with this gender thing is, or noun classes, because, you know, John McWhorter, a linguistician who was apparently a friend of mine, famously says, yep. Do any of you remember Women, Fire and Dangerous Things? No, you're not that old. Yeah, some of you do. There's a book by George Lakoff, Women, Fire and Dangerous Things, that, you know, basically says, yeah, well, there's this country somewhere, probably Australia, where there's an indigenous language where women, fire, and dangerous things are all in the same grammatical class. You might say the same gender. And John McWhorter says, yeah, right. And then he points out that,
Who do you
yes,
suppose
that's
made
right.
up that class?
And there is, you know, a language well, there's another language where, you know, the feminine gender is used for things like bridges and railways. Meanwhile, there's another language where an awful lot of the terms of food are masculine and, you know, blah, blah, blah. Okay. Now, the one where all the engineering stuff is apparently feminine is French. And the one where all the food is masculine and staunch is German. What does this mean? Well, John McWhorter will say these things are arbitrary. This doesn't actually control the way that you think. You can't really generate assumptions from the shape of a society or the shape of a community or even the shape of a bunch of people using programming languages by what may simply be accidents of the noun class that particular sets of sounds were assigned to when, well, I guess at some point when the language was being written down first 500 years ago. We don't have noun classes in programming languages, do we? Because, I mean, they're pretty annoying. I mean, if you're English, and I guess this also goes to people who speak Chinese or languages that don't do this so much, it seems really, really annoying. Because the problem is, you know, if you want to put la tour into a sentence, you've got to make sure all the verbs line up so that they're all masculine. Or if you want to talk about la tour, you've got to line up the rest of your sentence so everything is feminine. So we've got these kind of pretty arbitrary categories, and that they sort of infect everything we have to do in our language.
That's what you're talking about.
Close. Well, in fact, I am actually talking about monads. This is the programming language I first learnt from a book called ZX81 Basic Programming. And yeah, you know, if you could, I'm lying, this is actually BBC Basic. If you wanted to make a variable that had a floating point number in it, you could call it X. And if you wanted to make it a string variable, you had to call it X string. And if you wanted to make it an integer variable, 32-bit, it had to be X%. This is basic in more ways than one. That's a joke I've already used at a different talk in this conference. What does this mean? This means, are you saying basic is a statically typed language? But it's interpreted, it's dynamic, isn't it? Well, how can I put this? No. Basic is a statically typed language, and the types are encoded in every single identifier. So what else have we got? Noun classes. And, you know, it carries on there. If we want to do different operations, we have to just keep flowing all those things through. And you can actually look at certain things in languages. So, for example, Basic's heritage in, well, coming from Fortran and doing mathematical stuff, you can say because the unmarked term here, this is not about arbitrary classes, but actually the shortest term, the term that isn't distinguished, is typically the thing that we want to do most often. So Basic, the code that handles floats, is shorter than the code that handles strings and integers. And not just shorter, it's shorter in a particular way, which is that it's the unmarked term. But the good thing about programming languages and types?
It's him.
It's him.
Elon, look, we've explained it before. You don't own the letter X. No, look. Yes, we don't mind if you name all of your children X. No. Okay, and I hear you have more. Yeah, so, yeah, congratulations to you and oh, she's now called X too. Oh, I see. Okay. Don't bother us again, Elon.
She's his X. if, languages didn't exist, we would have to invent them. If type systems didn't exist, we would have to invent them. And sometimes when type systems do exist, we invent them anyway. So this is Hungarian notation, Charles Simeoni, and you say that a variable is floating point in order that you can see the FPX in your code. Yes, this was certainly the days before Visual Studio Code where you could just point at a variable and get its... Can you actually just point at a variable and get a magic pop-up of its type? Anyway, but you couldn't do that, so to be sure you remembered that what the type was, you would put the type directly onto the variable. And it would be sad, but at this point you have to think that this is pretty much the Hungarian dialect of C. Because, if you write code like this and you try and write code leading those things off, people will yell at you, they'll tell you that you're not doing it correctly. One of the first projects, well, it wasn't the first project, one project I hoped to do to send into SIGPLAN notices when it was still running and was really disappointed that I never got around to doing was the Hungarian notation checker for Java. Because it seemed really bad if the Hungarian type annotations you put on your variable names didn't agree with the actual declared types of the Java program. It is all kind of pointless, but you could certainly do that because this effectively is a type system, this effectively is another bit of a language, and what's interesting, if you look at the way in which human languages evolve, you can actually see this kind of stuff happening in quotes, natural languages as well. People will change the way they pronounce words, they will add in various suffixes, they will add in various prefixes. You leave that for a few generations, and then you find yourself with a new natural language that just happened to evolve.
So if you're Australian and your name is John, people will rename you to
Jono.
And if you're Australian and your name is Jane,
Jingo and Chazzo, and if you're a cricketer especially. To the point where when I was last in Sydney, there were ads on the TV and on the street for things like, get down to Macca's, and get your rego, Jono.
Yep. So registration was masculine, but McDonald's was feminine.
Yep, that is true in Australia, but they're a bit strange. They have too many spiders, I think. How are we going? You're not going to make me sing. This is the slide of Te Reo Māori, the indigenous language of New Zealand, of Aotearoa, I should say, which you may know as New Zealand. And what's interesting is that this has 3 numbers. There is a song, I don't have my ukulele, I'm not going to attempt to sing it. You really want me to sing it, don't you?
And play the ukulele.
Air ukulele. Tēnā koe, hello to one. Tēnā korua, hello to 2. Tēnā koutou, hello to 3. More, sorry. Haere mai, everyone. We don't have enough time to teach that, do we?
No, we don't. We don't have enough time for a lot of the things you've just said.
So that is a thing which I was kind of taught at school. Certainly people are taught at school as part of a ukulele class these days. That language has 3 numbers, and syntactically, you distinguish between you're talking to one person, to 2 people, or to some wider things. You know what I'm going to do now, don't you? That's another stupid idea. Especially if you're English, you look at this and think, well, that's kind of dumb. We wouldn't put that into programming languages, would we? We wouldn't, would we? But we did, and what's more, if I phrased the question correctly, almost everybody in this room would say, and that's a good thing, that's great. Who thinks non-null types are good? Excellent, so it might not be 1, 2, and more. To quote, the only reasonable numbers are 0, 1, and infinity, which I believe is a quote from Bruce McClellan's Principles of Programming Languages. It's still a good principle. 0, it's nullable or it's not nullable, 0 or 1. Or maybe if you want to have more things, you have a collection. I'm not sure if Friedrich Steinmann is in the room, but he's certainly done work on embedding this kind of context a little bit further into programming languages so you can do more things with plurals. But we have these things in our programming languages. We just don't see them because we don't look at them in the way in which we tend to produce other kinds of languages.
So we've got case. We've got something that isn't gender, but really involves a lot of matching. And
Noun
we've got
classes.
number.
We have verb classes. We've got number.
What else happens in natural languages which might transfer to programming languages? I mean, there's a lot of stuff to do with human culture in natural languages. Surely those wouldn't appear in programming languages.
Well, you mean the story of apparently which Richard Feynman tells about his father in one of his books, how he went to Japan as part of the Army of Occupation. No, it must have been after that, but he was using a phrase book from the American Occupation Army of Japan. And he said everyone was really super nice and really just jumped whatever he said. And it turns out, because this was written for the occupying military power, the register of Japanese that was used in this book was the one that would be used by the emperor talking to a peasant. You know, so instead of saying, "Excuse me, please, would you possibly just check that the camera is aligned?" It would be, "You peasant, align the camera!" Yes, right, fine. We wouldn't do that in our program languages, would we? Would we? You know the answer because it's this talk, right? Oh, no, that's the French example. We can skip that. Anyway, French. Anyone do Java?
Politeness.
This is in Java, though. This distinction, the tu-vu distinction, the TV distinction, the I-thou, for those of you who are Oxford Movement Anglicans. If we're really close to an object, to a field, we can just write x equals x plus p. For a bit further away, we can write OX, we have to mention the name of the object. Why? Well, I could give you all kinds of computer sciencey reasons for it. But linguistically, it's like, well, you know, we're closer to the object, and so we have to, if we're really close and intimate with it, we can speak quickly and rapidly, and the further we are away, if anyone, they're not called Enterprise Java beans anymore, because I think Sun was ashamed of them. I think they're now called Jakarta Enterprise beans, but the abbreviation is still EBJ. You ever had the misfortune of programming in them? You get to be, the people who I'm nodding, you have to be extra polite. You can't say just x equals x plus p. You might have to do something like this with all these kind of accessors. And anybody who knows, you know, again, there are software engineering reasons for this. There may be good reasons for it, but fundamentally, it's not really doing any different to what the top line of the slide is doing, except it is doing it in a different register. It's doing it, you know, with a lot more characters, and this is one of the reasons why apparently lots of people in the real world think Java is basically a kind of fucked up language.
I thought you were going to say corporate language.
I did.
I think the alternative for Enterprise Java beans was Imperial Java beans. I think they rejected that for a good reason.
I did say fuck. I'm not in America. I figure I actually lost. Jan Vitek told me I once lost a job offer by swearing out of class in America. But I'm not in America. But you wouldn't swear in your programs, would you? Especially not if you're a Haskell programmer. If you think that you would never swear in your Haskell programs, I encourage you to go and read what the Haskell language manual says about unsafe perform I/O. You know, it is exactly what a phrase book for someone coming from outside to English might say, because, you know, well, we really do need to, you know, the tourists do need to understand what happens, especially in Texas, if someone tells them to fuck off. Because if they don't understand it in Texas, they could be shot. Okay? You really have to understand what this means. But also, again in Texas, and especially if you're a tourist and visibly different, you don't want to use that because you might get shot. So the guidebooks basically say, here is what this thing means, here is what it does. You should never, ever say this. But this is what it does. That wording, almost without some of the hyperbole and slightly more Anglican once again, is what is in the Haskell standard about unsafe perform I/O.
Couldn't they have said unclean? Don't you think that would have transmitted the message?
We all know that's what it means.
Right. So that's the operational low level. That's the level at which we start at. But we want to go up in the level. And this means we want to think about programs as a whole. So if you're an outsider, if you're one of the people who's contemplating end-user programming, or if you're one of the people basically reading a very introductory article in the news, you might have an explanation of what a program really is. And these two come from the OED. A program is a sequence of operations that a machine can be set to perform automatically. Or it's a series of coded instructions and definitions, which when fed into a computer, automatically directs its operation, performing a particular task. So, we've been programming a long time. We've been programming at least 4,000 years. And this was a point made by Knuth in his wonderful paper on ancient algorithms. So clay tablets, like the one at left, which were produced in abundance 4,000 years ago, typically encoding the Akkadian Sumerian language, certainly at the time, for instance, of Hammurabi coding his laws that were given, you can go and see in the Louvre. Basically, aside from setting laws and horrific punishments for those who break them, they typically encode relatively simple things in the operational world. And this particular one, Knuth is aided in translation from Sumerian Akkadian, which was the sort of lingua franca, actually technically the Sprachbund, the federated language of more than one language, in fact as many as 4 at the time, said things like, when you are digging a well, in order to basically find out how deep to dig it or how much water it's going to store, you should take the reciprocal of the height, 320, obtaining 18, they worked in base 60, multiply this by the volume, 274640, obtaining 820. Now, Knuth says this is an algorithm. The title of his paper is Ancient Algorithms. Now, am I allowed to disagree with Knuth?
No. You're going to anyway.
Yeah. Well, this is enemies I've made. Number 1, Alan Kay. Number 2, is Donald Knuth in the audience? No, I hope not. So he says it's an algorithm. I say it's a program, because it's really very specific. It's literally a set of instruction. Now, presumably, the people who read this weren't always going to dig exactly the same size well. But this was an example from which one would learn. So I'm going to say this is a program. My point is, we've been programming a long time, and those are instructions. Now, at the time, the only people, the only things, the only entities worth giving instructions for were people. But when we started having computers, we thought of basically how to give instructions to computers. And so this is Seymour Papet's logo, in fact it's turtle graphics. I taught this to primary school students many years ago in New Zealand. We didn't have one of those actual physical turtles. We made do with a little triangle on a screen. But the thing is, these are instructions. A program here is instructions. In order to make a petal, this is what you do. In order to make a flower, this is what you do. So, as the OED says, we do have programs that are instructions. But we sometimes want more. So, for instance, in COBOL, if you're programming back in the days of the Johnson Wax building there on the left, you will have something which will be very much instructions, here as in the procedure division at the bottom, but an increasing amount is also spent on the data division at the top, where you describe the records that you're working with. And COBOL, a common business-oriented language, was working with records almost all the time. This is what it was for, and this is what it is still for, and is still used now in 2023. So now we've got a bit more. It's not just instructions, it's descriptions and instructions. But I think a change happened a bit here. So this is similar, and I learned similar from Graham Birtwistle, and it was the era of that book over there. And similar starts to look like this. So it's talking about a car washer. And basically, it's a description of the life of a car washer. Now, this car washer doesn't have a particularly exciting life. I understand real car washers have much more entertaining lives. But here, this says the car washer basically repeatedly waits for a car to be washed, waits for it, and when the car is washed, basically moves on and waits here in Graham Burt Wilson's example of the tea room. So in reading these kind of programs, my claim was that this was more like a narrative. This was more like a story. We were talking about the life story of a car washer. So what I'm saying is this is a bit different from instructions and description. And we moved on. And at this point, I want to invoke some early discussions of the way stories are told. And there was a lot written by Socrates, although we only have this through Plato and Aristotle, and by Plato and Aristotle themselves. In the painting by Raphael, Plato there, the senior, on the left, and Aristotle on the right, had this argument over time between two different ways of telling stories, and they were mimesis and diegesis. And the idea of mimesis is that it's imitation, and the idea of diegesis is that it's a storytelling. And the argument began with Plato, who was strongly against, in ancient Greek theater, mimesis. He regarded it as problematic that someone pretended to be someone else, that it imitated something that it really wasn't. So that in the Republic, he regarded this as a kind of deception that was necessarily bad. And so following up some years later, in the Poetics, kind of criticism by Aristotle, he makes the point that in the theater, mimesis has a point, because when actors are imitating, one begins to empathize with the actors. You understand a bit more of the thing from their point of view. You begin to understand their intent. And so Aristotle says that mimesis has a place, and we don't just want dispassionate narration. And at that point, I began to think of my claim that object-oriented program, a la Simula, was just a form of narration. And it occurred to me that in writing, back in the late 80s, early 90s, this was talked about a lot. So in this paper, we talked about the nature of an object-oriented program, and so Christian Nygaard was this, so I will pass over to my colleague who is a Nygaard laureate.
A program execution is regarded as a physical model, simulating the behavior of either a real or an imaginary part of the world.
And so when we think about creating these models, one of the influential papers is this paper by Kent Beck and Ward Cunningham, a laboratory for teaching object-oriented programs. So this is the birth of CRC cards, so that when you're generating a design, and this is some of our students, James and mine, back in the day, you start by thinking of the objects in the domain, and you start walking through what needs to be done, what these days we would call use cases. And the way you do it is that each person takes a card and pretends to be that object. So this is clearly mimesis. You act like it. And basically, this is what goes on, for instance, in table reads in Hollywood and theater. No one is wearing costume. No one is blocked and walking up at their mark. One simply walks through the script, pretending who you are. And the reason that they have table reads is that so that everyone can understand the interaction, everyone can get into the simulated world. And this is exactly what's going on, we claim, with CRC cards and CRC roleplay. So we claim that this is mimesis as well as narration. Which leads us to this famous book, or the follow-up that we think should have been existing. Nicholas Verrett's famous book on the left, Algorithms plus Data Structures equals Programs. Gosh, that's almost a program in itself. Don't you think it should be Algorithms plus Data Structures is assigned programs? Or what was that language that we learned about earlier on today? BOSC. Basically, algorithms lead to programs. But you think that the book should be rewritten for today?
Well, it could well be. Well, it's a great book. You can get it online. But he deleted the equals programs from the book. Yeah, but Nicholsworth, clearly verbs plus noun phases equals stories, is what we could call it today, the Prentice-Hall steric and autonomic recitation. And its systematic and lucid and penetrating treatment of basic and dynamic story structures such as sorting, recursive narratives, language structures, and plotting.
So this is our claim. Programs are really stories. Even functional programs are stories. Even in natural language, look at the works of Virginia Woolf, look at the world of Emile Zola, there are programs, there are stories that don't necessarily have plots or side effects. Oh, this is my line, isn't it? Yeah, if it wasn't for side effects, we'd have no effects at all. Right. So we think programs are stories. Now, if they are stories, we have things to learn about stories. So this is the work of the narrative semiotician Grimas. And he talks about models of stories. And one of the models he liked is based on these actants, as he called them. And he talks about a standard template for a story involves a subject trying to accomplish an object. There's those words again. But typically, to make a story more fulsome, more elaborate, the subject will be sent on a mission by a sender, will receive help from various aides, and that the object is often to satisfy a receiver, but importantly, in typically stories, the accomplishment of the object is impeded by an opponent. And this is a typical model. So our question is, are programs like this? What do we have to learn from this? Do our programs have opponents? Do our programs have helpers?
Sadly, yes, I think they do.
And so the important thing, if you're a writer of a story, is to understand your toolkit of actants in this, and we think that we might learn as programmers in understanding this. Now, going a bit further, this model in discourse analysis, done by Van Dyke, discourse linguistics research, in fact, the person who chose the word discourse, basically, along with Kinch, talks about stories, about all discourse, in fact, being related to a more abstract model. And they call this abstract model a situation model. And their point is, for instance, this is what's going on when novels, when poems can be translated from one language to another. It's not word for word, it's not grammatical. Basically, in understanding a story, they say, one forms a situation model, and then from the situation model, expresses the best they can in another language. And so this is a model of translation, but also a model of understanding. And much more recently, another discourse analyst and a psycholinguist, in this case Von and Radvansky, do empirical work. And they say that there are 5 dimensions involved in making this work. And this relates, again, to papers I've seen presented today. One is time, one is space, another one is causation, fourth one is motivation, and basically there's the actors, the protagonists. And so what they're claiming is, this is the software that we use to both create and understand stories. And so if we're right in claiming that programs are stories, maybe we have something to learn by these being critical elements in creating and understanding stories. And the question there is, what leads to this? And our line here comes from other linguistics research. So this is Clark and Wilkes-Gibbs going on at the same time. And they emphasize conversation. So this is a line from one of their key papers. Conversation is the fundamental site of language use. For many people, even for whole society, it is the only site and the primary one for children acquiring language. So basically, you've probably learned that spoken language, audio language, precedes written language, and their claim is that conversation precedes storytelling. Conversation is interactive. This is the genesis of language. And so we thought, oh, if programming languages are languages, how does conversation work? And we thought, what programming is like a conversation?
So this is an actual picture of me, but live coding, if you've come across this. I do actually do this from time to time, occasionally even for money, with either a laptop or a modular synthesizer, where I will sit down and perform generally sort of no-wave, noise-based, I'm not going to say music, but audio, sound art, yeah, which you do basically by coding and as a performance. But then, I mean, I don't think that's the only kind of live coding we have. When I was teaching Daphne, which, well, you know, if you want to find out about that, come and buy me a drink afterwards. We actually taught Daphne fully live coding in classes because we flipped the classroom, we pointed people at Rust and Lino's book, and we had 120 third-year students who couldn't fail the course without doing an extra year on their engineering degree. And we would basically give them Daphne problems, and then they would come to the class, and I would live code in front of them with Daphne and swear at it and have all the kind of fun experiences you have in this sort of thing. And then students would submit their assignments, and when they got their assignments, the assignment system would basically automatically test it and give it back. And so these kind of techniques aren't just for formal systems like Daphne. There's now quite a bit of research showing the advantage of having rapid feedback from a kind of system when you're teaching people to program. Why? Well, if programming is conversation, then maybe we need to have those conversations when they're learning to program. Do you want to talk about that?
No, I'll take over.
Oh, I'll do the next bit then. Here's another conversation. I don't know if anyone had this conversation. This is a conversation I don't particularly relish. This is my conversation with the Rust compiler because, you know, the Rust compiler is kind of opinionated and you're not allowed to have parentheses around your ifs and your whiles. Why? Well, because if you're more than 30 years old and if you've basically learnt to visually search for if and while statements by looking for the keyword followed by the parenthesis, you're clearly too old to learn to program in Rust. It does have very good error messages. It's sort of like ChatGPT-3. It's really good at apologies. And again, when you think about it, if programming is a conversation, then maybe being good at apologies is important because it keeps the conversation flowing. What are we going to say about that?
But in fact, every REPL is a conversation. The reason that we love REPLs, I program in R a lot, and basically in my data analysis, I do a lot of exploratory things. It's certain that I write code, but I spend a lot of time in the console basically playing off. What if? What does this data look like under these conditions? What happens if I run this test? What if I filter out these pieces of data? REPLs, read, eval, print loops, are wonderful for this. But in fact, they go further. This is perhaps my favorite programming ever. This is the work of the wonderful Adele Goldberg in her system called Learning Works, used for, I think, what was at the time probably the largest introductory programming course in the world, done by the Open University in the UK, who used this system. And her system here facilitated a REPL. Yes, it had a console, but you could do refactoring, you could do substitution. And so basically, the console was how you built up your program by taking bits of what you typed in, saving that and parameterizing it and turning it into functions, and you're creating your program in this way. In other words, you had a conversation that built the story, and this is what we love. So our claim here is that programming is conversation, and that's how we make up the stories. James, it's 5:30.
Oh, we need a drink. I need a drink.
Should we stop here and invite questions?
Sure. If you've ever been in a band, you always want to do this, so that we can send it to the funding body and say people came to our tutorial.
Yeah, it's useful to have for the police inquiry later.
I was going to be referring back to not Colin. Was it Colin Gordon's talk? But I really shouldn't. You know what those things that Knut had?
I think you're just trying to avoid Marco's question.
What's Marco's question?
I thought you were calling for questions. So.
Yeah, we're calling for questions, but I'll just wind up and keep going, until I collapse. Otherwise.
You have lost an incredible opportunity to mention the best name type ever, an exception type in GWT. What a terrible failure.
Yes, there were lots. In the programming language originally called AEH, a Canadian language, that later was rejected for publication, but was largely the work of Dave Cheriton, after whom the whole
Computer Science Department is now named.
Yeah, that's right. They had puns, and so they had twits, they had puns, and they had errors. So puns were basically type conversion, because one thing could have two different types, and that was basically a play on words. Twit was the window into trouble when you basically just needed to get at machine code. And errors, and that was all done so that basically at the end of your program it could give you a result as how many twits, how many puns, and how many errors, because Sheridan was a baseball fan. Someone other than Marco, please. The first time we gave this talk, what everyone wanted to know was, so what? What are the takeaways? Now, in New Zealand, takeaways means...
Takeout.
Takeout.
Macca's.
So,
in Australia, it would be Macca's.
Yeah, so James brought in fried chicken to show him what our takeaways
So we got the takeaways. Yeah, Kentucky Fried. Yeah.
Okay, so there are good conversations and there are bad conversations, and there are good programs and bad programs. Can you talk about the relationship? What can we learn from conversations to write better programs?
So the one thing about conversations, and this was one of the points that Clark and Wilkes-Gibbs was talking about, is that they not only allow, but encourage participation. So if you need to know more, if you want to explore, if you want to check your understanding, basically conversations are great for this. So when you're reading a story or telling a story to a small child, you learn very quickly that it takes several minutes to read every sentence, because you have to answer questions like, what was the name of the bear? Why did the bear like the honey? Is this the same bear as before? Where is the bear going? Does the bear spill the honey? So it has clarification. So we've talked about this, and we've actually seen examples of this today. So this is one important thing about conversation. Conversation allows clarification. The other thing, which is a little bit more sophisticated, is that conversations are epistemic. In other words, in that conversation, you can reframe what you're talking about. There's basically famous work through this throughout science, where basically you take opposing positions with one of your colleagues in order to figure out basically what could be going on. Now, you have to be very disciplined in this. Basically, you can't swear and start throwing at things, but conversation has this epistemic thing. So those are two values of kind of good conversations that I'll give. I think the good and bad programs as stories, my best answer for that is remember what the discourse analysts and linguistics talk about the understanding of stories. Now, it doesn't always mean when we're doing literary stories that you want to make it easy for the reader, because actual writers are basically telling stories in order to achieve various kinds of effects. So you're probably familiar with things like unreliable narrators, where basically they are telling you things which later turn out to be true, but this has an effect. Now, whether we want effects like that in programs is worth considering, but it's also worth considering where we're doing that by accident. In other words, there's a lot of knowledge about telling stories which can be super useful to us. And that's our claim there.
Yeah.
This is a bit of a meta question, but I guess some people in the audience would say proofs are programs. So does this give us any insight into how to better frame and present our proofs that we write down in these papers that we show to these conferences?
So James mentioned the earlier book by Lakoff, Women, Fire, and Dangerous Things. So I'd actually refer you to Lakoff and Nunez's more recent books, where basically they claim that mathematics and mathematics notation itself is embodied in the same way natural languages are. So in the logic in that book, they would claim also that the proofs are stories. And in the same way, for instance, we have languages now where you can change the order of lines and accomplish the same effect. And that's often true in a lot of mathematics. But the question is, you don't do that when you're writing a program or writing a proof. You carefully present the proof in certain orders, and the question is why, and that will give us insight as to how we can be writing our proofs in order to be more understandable, in order to help us reason better.
Yeah, what would I say? I probably agree with everything there and say, for better or for worse, I think, well, as things like ChatGPT or things like Z3 get better, then increasingly that is coming to the point that, you know, in some sense our programs really are proofs. Also, of course, as computer scientists, we're eating mathematics. So, you know, in 20 or 50 years from now, proofs will be programs. In some sense, proofs really are programs.
They are now.
They are now, especially if you're trying to get your paper into Popple, frankly.
Yeah.
You know, you can't get it. If you haven't got the cock or whatever it is, then, you know, it's like, well, send it to Uppsala and let it get 1,000 citations or something.
At the Dynamic Languages Symposium yesterday, I really noticed how many times several people talked about the expressiveness of dynamic languages. It reminds me of what mathematicians say, and I was first educated as a mathematician, which is the elegance of your proof. I'd like us to think a little bit more careful about what those words like elegance of a proof or expressiveness of a language actually mean. Because although we have some insight, and we've used those words for centuries, if not millennia, we need to think more carefully and basically read the work of some of our humanities colleagues to basically understand better what's really going on there. Because basically, we're hand-waving when we just use those words and assume we completely know how they work.
I mean, if we really believed that programs were proofs, that would mean every program was a proof, not just every COP program, but every program. And it would actually mean the question then is, well, what's it a proof of? Which, under that Hakai Hard comes out of, well, what does it do? And, you know, I don't want to say these are the kind of things that quite possibly ChatGPT-4 will actually do for us. But I think thinking if programs are proofs and proofs is piles and piles of functional COP code, it's like thinking, well, programs are machine code. And, you know, instead of ChatGPT, wouldn't it be great if we could write? Wouldn't it be great? No, I was just thinking we've got to automate our finance department and we've got to write all those programs. Wouldn't it be great if we could describe what the records were and kind of describe what the processing was in a way that the managers could read it? Okay, which of course is what Grace Hopper and Joan Summit done when they designed COBOL. So there's this distinction between the program as the high-level thing which we read and the machine code. And in the same way, I do not ever want to have to look at machine code if I can possibly avoid it. I don't really want to look at the fine details of the proof, and for precisely the same reason. Not because it's a proof or a mathematical, just it's a really low level of abstraction.
When I think of, the reason I included the picture of the Johnson Wax building there with rooms full of clerks is that the language that COBOL imitates was very much similar to the language at which the processes or the procedures that clerks should follow were given to them when they started. In other words, where you started as a low-level clerk in a program, you would have a list of the procedures that you followed in order to process the records. So basically, it was a direct imitation because basically, before that, the managers were programming the employees. In talking about the consistency, in talking about the proofs, the question really is consistency. Now, at a conference like this, we're great about consistency. All of the type theory is largely about consistency, and it helps us enormously for the consistency checking things that we were talking about. But while it's great to know that something is consistent, you still have to look to see whether the thing that it's consistent with itself is consistent with what was needed in the domain. And eventually, you run out of formal notations.
So my guess to answer the questions from the previous session and finish my talk from yesterday is that a world where we do have all this AI stuff, because in fact we already do have a hell of a lot of AI. I mean, what's behind Daphne 20 years ago, SAT solvers, SMT solvers, all of this stuff was AI. What a JIT compiler does is AI. We just don't call it AI because, I don't know, we're aesthetic and we don't like the funding, basically. But something that Hotspot does, if you think about the kind of analysis on complex knowledge-carrying correct structures that something like Hotspot does, well, if it's not AI, then what is it? Oh, it's just all these little rules that run around. Well, it's still more sophisticated than perceptrons. Sorry. I think the world where we have that is going to look more like the world where you were programmed in Smalltalk or COBOL than it is where you are super, hyper mathematical, for exactly the same way that the world we want to build is this world where you are operating at the kind of level we're talking about. You're operating in this language, and this language is designed to let you express the things you need to say, express the stories that you want. And, you know, whether it's the compiler people or the proof people, all that stuff happens under the hood.
Under the bonnet.
Under the bonnet, sorry, yes, under the bonnet. Yes, you've been very patient as well.
Thank you. A very stimulating discussion. When you presented your conversations, they were, I think, effectively dialogue, two-party conversation between you and the compiler, or you and the REPL. How would you generalize that to a multi-party conversation in this analogy?
Well, obviously it would be by multi-party session types supported by separation logic.
Yeah, I'd like to point out that that's actually a difficult problem even for humans in natural language. But we have ways of doing it with different groups of people. It's complicated. There are study methods for doing it, but it requires great discipline, in my experience of roundtable epistemic discussions. Richard Feynman talks about that too, right? He talks about some of the managers basically staying out and writing down all the sorts of key ideas, even when people disagree, and then come back to get agreements on them. I mean, the problem is, as I talked about the epistemic conversations between people who play devil's advocate, basically, part of the regime is that you have to be willing to let go. This is the kind of thing that as scientists, we get better at, and our politicians, unfortunately, don't seem to have learned the trick of doing.
Well, it's worse, but that's another talk.
Yeah.
You know, remember all that stuff that...
Is the reception started?
Yeah, the reception's about to start. You know, all that stuff that was banned. In fact, it probably is illegal to teach in Texas. You know, French philosophy and the idea that everything is relative and that there is no objective truth. Well, it turns out, of course, that a whole bunch of political hacks were listening. Sorry, I shouldn't make these sort of comments. There is a talk on postmodernism and relativism in computer science. That's not it. You can find it on YouTube, where you should give us a like. If you're watching this on YouTube, you should give us a like, and you should click subscribe on the SIGPlan ACM channel. And you should come to Splash next year in Pasadena, where it's being organized by Alex.
Yeah. You know, when our talk began, I looked to see, and the subscribers are listed as everyone in ACM, which I think was something like 300,000, and the people actually watching at the beginning of this talk was 8. I hesitate to think what it is now.
Thank you for your time and patience.
Yes.
I understand there is actually food at the reception. There may even be spirituous liquors as well as just high sugar drinks. I'm around, I think Robert and I are both around for the next couple of days.
Yeah. Thank you for your patience
Indeed.
with this chaotic talk. We hope there was some value for.
Thank you.